dynamic programming. So this is one algorithmic approach in order to solve the programs or problems. So in our previous sessions we have seen the greedy method and divide and conquer, and now we are moving on with the next concept, that is a dynamic programming. So this is similar to our divide and conquer method. So usually the divide and conquer method is represented as DAC, divide and conquer, and this is represented as DP, so which is abbreviated as a dynamic programming. And the main goal is this dynamic programming approach is used to solve optimization problems. I think we have seen this in the greedy method. So greedy method is also used to solve the optimization problems, and here also it is used to solve the optimization problems. So we know that optimization problems are the problems which are having a multiple solutions, and we are selecting the optimal solution based upon the constraints, right? So that is an optimization problem. And so working is similar, not equal, right? It is a similar to divide and conquer. That means here also the complete problem will be divided into sub-problems, similar to our divide and conquer. But only one thing difference is, so the division should be with overlapping sub-problems. Okay, with the overlapping sub-problems. So overlapping sub-problems. But in case of divide and conquer, okay, in case of divide and conquer, so the sub-problems will be divided without any overlapping solutions, right? So let me explain what is exactly the overlapping sub-problems and the not overlapping sub-problems. For example, so in both the cases, I'll write the steps and then I'll differentiate these two things. Okay, so the first step 1, the first step, the complex problem will be divided into sub-problems. The complex problem is divided into sub-problems. So either it can be a complex problems or a large problems. Okay. And step 2. So this is common with the divide and conquer. Next we have to find out the solution for these sub-problems. Here also find solutions, that's also optimal solutions. So here that is important. Find optimal solutions for all sub-problems. Okay, here this is also common. And step 3, this is the most important and a unique among the remaining algorithmic approaches. So store the solution of sub-problem in the memory. Okay, so stores or save solution of sub-problem, so that if it requires to get a solution for the same sub-problem some other time, so in order to avoid that one, so we can get the solution from the memory. So we have to find out the optimal solutions for all the sub-problems, and we have to save the complete solution in the memory. And before solving the sub-problem, first we need to check in the memory whether there is a solution for the sub-problem. If it is there, then automatically we can retrieve the value. Otherwise, we have to solve the solve the problem and get the optimal solution and again save the same thing in the memory. So this is a unique thing. Okay. For example, consider the Fibonacci series. Okay. See. So I'll write the step 4 also. The last step. So what is the last step? So finding the complete solution for overall problem. So based upon the optimal solution. So from all optimal solutions, from all optimal solutions of subproblems, find out overall solution. Find out overall solution. Find out overall solution. So these are the main steps that will be followed in this particular algorithmic approach. The first one, complex problem, will be divided into subproblems, and second, find the optimal solutions for all the subproblems, and the third, stores or saves each solution of the subproblem and for the future reference. And step 4, from all optimal solutions of the subproblems, find out the overall solution. See, now I will tell you the example of overlapping subproblems and non-overlapping subproblems. Example, let us consider the Fibonacci sequence. Fibonacci sequence. Alright. So, we know that Fibonacci sequence means the element is nothing but the addition of previous two elements. The element is addition of previous two elements. For example, so if the first element is 0 and the next element is 1, the next element will be 1 plus 0, it will be 1. Next element will be 1 plus 1, 2. Next element will be 2 plus 1, 3. Next element will be 3 plus 2, 5. Next element will be 8. Next 13, 21, etc. So how we got a 21? So 21 we got with the addition of 13 and 8. How we got a 13? 13 addition of 8 and 5. How we got a 8? Addition of 5 and 3. So n is equal to n minus 1 plus n minus 2. So if you want to get n minus 1, n, so we need to add n minus 1 and n minus 2. So we can solve this one by using the recursion. Okay, simply we can use the recursion. Fibonacci of n minus 1 and n minus 2. So if you solve the same thing using the recursion, what happens? Let us see. See, if you want to solve, for example, Fibonacci of n, how we can solve? So this can be done with the help of Fibonacci of n minus 1 and Fibonacci of n minus 2. Okay, then how you got n minus 1? Again, Fibonacci of n minus 2, Fibonacci of n minus 3. Alright, and what about this one? Fibonacci of n minus 3, Fibonacci of n minus 4, and the process will be repeated similarly. So here you can observe, so Fibonacci of n minus 2, here we are solving, and the same thing we are solving here also. Fibonacci of n minus 3, here we are solving, and also we are solving here. Similarly, Fibonacci of n minus 4 is solved here, and somewhere else definitely we will solve the same thing. So that means that repeatedly we are solving the same thing multiple times, even though it is a recursion, right? So instead of that one, if you solve the solution, if you get the solution for this problem, that will be stored in a table. Okay, so simply here I will write Fibonacci of n minus 2. So whenever it is required here, I need not execute the same thing, I need not implement the same thing. So I will get the value from the memory because it was already solved and it was already stored. The solution is already stored in the memory. Right? So consider these are all the subproblems. These are all the subproblems. So once you solve the subproblem, the solution will be stored in the memory. Right? And this process is called top-down approach. Top-down approach. And this process is called as memorization. Memorization. So here the same problem can be solved in two different approaches. One is the top down and the bottom up. Okay, so bottom up approach. One more thing, we can write a bottom up approach. So that means the solution will be getting from the base case itself, right? So this process we call it as a tabulation. Okay, tabulation, right? So hope you understood. So these type of subproblems we call it as a overlapping subproblems. So here we are having a Fibonacci of n minus 2 and here also we are having Fibonacci of n minus 2. The same problem repeated twice here. So this process, these two subproblems, we can call it as a overlapping subproblems. So this the one characteristic of dynamic programming is overlapping structure. Okay, so I'll write down here characteristics. So one is overlapping structure. So actually in the dynamic programming we are also dividing the problem into subproblems but without overlapping subproblems. And the second characteristic is an optimal solution, optimal subproblems. That means here also, as we discussed just now, so consider each and every subproblem and we have to find out the optimal solution for each and every subproblem. Right? So that we call it as an optimal subproblem. And these two we can say as a characteristics of dynamic programming. See, I'll write here. Consider this approaches. So we can say this as a top-down approach and two approaches. Another one is a bottom-up approach. So in this top-down approach, we call the process as memorization and here it is called as tabulation. And here we'll use a recursive function. Right? So every subproblem will be solved by using a recursive and here this recursion will be avoided and here it will be iterative. Right? So these are the different approaches to use this dynamic programming, to solve any problem using this dynamic programming approach. And now let us see the applications. So what are the applications or what kind of problems can be solved by using this dynamic programming? So as we just discussed it just now, that is Fibonacci sequence, multistage graph, matrix multiplication, matrix multiplications, 0-1 knapsack, towers of Hanai. So lot of applications are there. So these type of problems can be solved by using this dynamic programming in order to get the optimal solution, right? So hope you understood the top-down approach and bottom-up approach, and overlapping subproblems and not overlapping subproblems. So that's the main difference between the dynamic programming and the divide and conquer. Divide and conquer, the division will be done without any overlapping subproblems, but here dynamic programming will be divided with a overlapping subproblems, right? The characteristics, overlapping structure, and the optimal subproblems. So hope you understood. So let's stop here, and in our further sessions we'll move on with the applications. We'll take some problems and we'll see how we can solve the problem using this particular algorithmic approach, dynamic programming, right? 0-1 knapsack problem. So before going to this problem, first let us understand what is meant by a knapsack and what is meant by 0-1 knapsack. So we know that a sack means it's nothing but a bag. So here the problem is we are supposed to fill some objects into that bag with a highest profit. So let us consider 4 objects, right? Some x1, x2, x3 and x4. And the weight of the bag is W. Okay, so these are 4 objects, and for each object there will be different weights. So W1, W2, W3, W4. Okay, in order to avoid the confusion, let us take the capacity of bag. Capacity is represented as M, some M. Okay. So there is a one bag or one container with a capacity M, and here in order to move these weights into the bag and carry towards somewhere, it requires some profits. So P1, P2, P3, P4. So with this particular X1 we will get a profit P1, with object X2 we will get a profit P2, X3, P3 and X4, P4. Here the problem is we have to arrange the weights into this particular bag that should not exceed the maximum size, and we need to get the maximum profit. That is the problem. And why we are calling it as 0 and 1 means here 0 indicates no move or no insertion. That means we are not supposed to move the weight into this particular bag, or we are not inserting the particular weight into this bag. And 1 implies move or insertion. Move or insertion. So that means if 1 represents moving the weight into the bag or inserting the weight into the bag. Hope you understood the problem. And why 0, 1? So there will be only 2 solutions, either 0 or 1 for every weight. Okay, so this will be 0 or 1, and this will be 0 or 1, and this object will be 0 or 1, and this object will be 0 or 1. So this is a solution, 0 or 1. These are objects, these are weights, and these are profits. Okay, so we need to fill the objects into this bag so that we need to get a highest profit. And for that, moving or not moving is represented with 0 or 1. So that's why we call it as a knapsack problem. Knapsack problem. Right? So in order to solve this knapsack problem, we are supposed to have the 4 things. One is number of objects. Second one, profits, weights, capacity of sack. capacity of sack or a bag, right? So these 4 things we require, right? So if you are having these 4 things, we can easily find out which objects should be moved from outside to the inside, and by representing with 0 and 1. So now we will see an example, right? One example, so that you will be understanding exactly how to solve this knapsack problem, right? Now let us take an example. See, example, let us take objects n as a 4 and capacity as 10. Okay, the sack capacity is 10, and then profits is equal to, so 10, 40, 30 and 50. And weights, capacity, weights, what are the weights? So 5, 4, 6 and 3. Okay, so we need to find out which objects should be inserted into the sack so that the capacity should not reach the capacity, go beyond the capacity, right? So for example, here the sack capacity is 10, right? So we can move 4, 5 and 4, the combination 5 and 4, and similarly 6 and 4, and similarly 6 and 3, okay, similarly 3 and 4. For example, if you go with 3, 4, 5, what happens? The total weight becomes 7 plus 5, 12, so which is beyond 10. So we can't insert the weight, 12 kg weight objects into 10 kg bag. That's the only logic, right? So we need to insert the objects that should not be on the weight. So 10 here, the weight is 10. And here you can get the profit, right? If you move the 5 and 4, the total is 9, so it can be accepted. So 5 and 4, it is 50 profit. In order to carry the weights 5 and 4, the profit is 50. What about the 6 and 4? 6 and 4, it's a 70. And 6 and 3, it's a 80. And 3 and 4, it's a 90. So there are different solutions, okay? So we are having a multiple solutions. So from this we have to find out the optimal solution. So here the optimal solution is based upon the constraint of highest profits. So we need to get the highest profit. Now we will see the procedure how we have to move it. Okay, see, this is a problem, and now we will go with the solution. So let us take first one, the solution, okay, the sack, S of 0. So we are having 4 elements, so we need to find out 0, 1, 2, 3, 4. That means initially S0 is empty. That means without any weights. S1 means insertion of one weight, of weight 1. S2 insertion of weight 1 comma weight 2. Already weight 1 is there, so we are moving another weight. S3 insertion of weight 1, weight 2, weight 3. S4 insertion of weight 1, weight 2, weight 3 and weight 4. That means here we can say S0 comma W1, and here we can say S1 comma W2, and here we can say S2 comma W3. Here you can say S4 comma W4, because S1 is empty. So empty, we are adding W1, and here W1 and W2. W1 means nothing but S1. So S1 comma S2. Here W1, W2 and W3. S1 is having W1 and W2. So adding third one, right? Now we have to find out all these things, right? So first S0, that means empty sack. So we are not moving anything, right? 0, 0. So here we are representing as PI and WI pair, a profit and weight, corresponding weight. PI and WI, profit and weight. So 10, 5, 40, 4, 30, 6 and 50, 3. So if you want to move 5, you will get a profit of 10. If you move 4, you will get a profit of 40. If you move 6, we will get a profit of 30. If you move 3, we will get a profit of 50. So we are representing this profit and weight as a pair, PI and WI. So initially, so everything will represent in terms of set. Set means nothing but a collection of pairs here. Okay. So initially S0, that's a empty sack. Initial sack, it is an empty. Now what happens? We have to select we have to insert 1 into 0th sack. Okay. So we are inserting this one. So obviously insertion means what we are doing? We are moving 5 to the sack with a profit 10. So 0 plus 10, comma 0 plus 5, 5. Okay, we have inserted. Now what is the S1? S1 will be, what is S1? S0 and W1. So S1 means, S0 means 0, 0. W1 means after insertion of one thing. So we are getting 10 and 5. So this is the S1. Remember this one. And this is S0. This is S0. Again, after that, what we have to do? We have to insert one more element, right? Now, S1 and insert one element. So just remember the prefix. Okay, the upper script will be the 1 and lower script will be the insertion of one element. So what we have to do? We have to add one more element. So one more element means 4 with a 40. What happens here? If you add 4, okay, if you add 4 and it is 40, what happens? So complete it is 9 and complete it is 50. Okay, the same thing apply to the S1. So S1, insert to S1. So what happens? 40 and 4. 40, 4. Because we are adding to this particular S1. 0 plus 40 and 0 plus 4. Comma. Then combination. 40 plus 10. 50. Comma. 4 plus 5. 9. So you got it. So empty. Initially we have moved it. And then we are getting the next one. Now, what is a S2? S2 is equal to, so what is a S2 here? So complete S1 and new thing. So S1 is here 0, 0, 10, 5, 40, 4, 50, 9. Right? Yes. Okay. Now you observe what it means. 0 weight, 0 profit. Okay, 0 profit with 0 weight. And if the weight 5, here we are having weight 5. How much profit we are getting? 10. Good. Second case. Adding weight 4. And profit is 40. So you are getting less profit with 1 weight, because you can see with the weight 5 we are getting only 10 profit. With weight 4 we are getting more profit. So imagine it as a cages. For 5 cages the profit is 10. For 4 cages itself the profit is 40. So which one is better? Obviously this one is better. So we can avoid this particular case. Okay, this rule we call it as a dominance rule. Okay, dominance rule. dominance rule. That means if Pi is greater than Pj and Wi is less than Wj, less than or equal to, okay, or simply you can write it less than, okay, then we need to remove the pair with less profit. So this process we call it as a dominance rule. Here the same thing happens. Consider Pi and Wi, Pj and Wj. See, Pi, Wi, Pj, Wj. What happens? Pi is greater than, sorry, I have written small, right, Pj and I, and here also J and I, right. So increasing of weight should increase the profit. So Pj is greater than Pi, Pj is greater than Pi, perfect, and Wj is less than Wi, Wj is less than Wi. So we need to remove the pair with less profit. Which is having the less profit? 10 is the less profit, because the pair is profit and weight, not weight and profit. Don't get confused. Okay, profit and weight. The first term will be the profit, the second term is the weight. So if we need to remove the pair with the less profit, that is a 10. So this is also called as a purging rule. Purging means removing, also known as a purging. Okay, so what we have to do in this case? We have to avoid this one. Okay, so now we can write the final S2 0, 0, 40, 4, 50, 9. Okay, only 3 terms we are getting. So 0, 0, 10, 5, 44, 59. So 10, 5 we are removing. So only 3 terms are there for S2. Now find out the next term, that is S3. So in order to find out S3, we need to add 1 to S2. 1 to S2. So the next term is 30, 60. So 30, 6 and add 30, 6 here. How much? 70, 10, and here 80, 15. Okay, now you observe the profit is 80 if the weight is 15. That's good, but the maximum weight here is only 10. So in the 10 capacity bag we can't insert the 15 weight. So this is also invalid. So we need to remove that one. Now S3 will be the combination of S2 and the insertion. So consider 0, 0, 40, 4. So before 44 we can get a 30, 6, 40, 4, 50, 9, and 70, 10. So these are the elements. And now again you can see the same thing. So here 6 and here 4. So we are getting a profit for 6 weight 30, and we are getting a more profit for weight 4. So we can remove the less profit. And see 0, 4, 4 to 9 and 9 to 10. 0 to 40, 40 to 50, 50 to 70. Everything is okay. Now S3, the final S3, 0, 0, 40, 4, 50, 9, 70, 10. This is the S3. This is the S3. Now insert the last one. already we have inserted the 3 things, we need to go with the 4th one. So S1 into 3, so we have to add the 4th one. So 50 comma 3, so 50 comma 3, 53, so 90 comma 7, 53, 53, 100 comma 12, 50, 120 comma 13, right? Okay, now you can observe this is a beyond the weight 12, so we can't process this one, and this is also beyond weight because 13 and the maximum capacity will also only 10, so you can avoid this one. Okay, now write on the S4. What is the S4? Combine both the things, S3. So 0 comma 0, 40 comma 4, and you can go with the 50 comma 3, 50 comma 9, 70 comma 10, 90 comma 7. See, these are the S4, and again you can observe, yes, so we are getting 3 with the 50 and 9 with the 50. Weight 3 with the profit 50, weight 9 with the profit 50. So you can avoid this one. Okay, with only weight 3 we can get a 50, right? So we can avoid this one. So finally write the S4, 0, 0, 44, 50 and 3, 70 and 10, 90 and 7. And again observe, so with 4 we are getting 40 and with 3 we are getting 50. Okay, again there is a violation, the same dominance rule, right? So avoid the less profit, so you can avoid this one. Again write on the final thing. So hope you are understanding. 50 comma 3, 70 comma 10, 90 comma 7. And again you can see, so with 10 weight we are getting 70, with 7 weight we are getting 90. So again there is a problem. So you can avoid this one also. So S4, 0, 0, 53, 97. So this is finally the S4. Okay, so now we found that S1, S2, S3 and S4. So we have inserted all the 4 elements, right? Now we'll see which one is the best. Which one is the best among all these 3? So here the highest is this one. So just consider the same thing. So 90 comma 7. Check the conditions, belongs to S4, and 90 comma 7 belongs to S3. Check both the condition. Okay, which one is true? So 90 comma 7, it is available in S4. Right. 90 comma 7 is available in S3. It doesn't belong in S3. Okay. So here you can see it is in S4, not in S3. That means you can simply say that X4 is equal to 1. That means we can move the element into bag, into the sack. Okay, if both are equal, we need not move it. Okay, both are equal. That means if 90 comma 7 belongs to S4 and 90 comma 7 belongs to S3, then we need not move the weight to the sack. So here one condition is true, another condition is false. So move the 4th element, last element or last weight into the sack. Now remove the 4th element from this particular weight. So 90 minus 50 comma 7 minus 3. So this is the fourth one, 50 comma 3. So remove the things from the pair. So obviously it will be 40 and 4. Check out. So 40 and 4. Check the same conditions. Now already S4 completed belongs to S3 and 40 comma 4 belongs to S2. Check out whether 40 comma 4 belongs to S3. 40 comma 4 it is available, right? 40 comma 4 in S2. Where is S2? 40 comma 4 in S2. Yes. So obviously we can say the third object need not be moved because both the conditions are true. So in both the cases, in both the sets, 40 comma 4 is available, so need not change. So in our first discussions, we say that 1 represents moving the sack into the, moving the weight into the sack. And coming to the 0 representation, we should not move the weight into the sack. Then, so we need not remove the third element from the here. Okay, so simply continue with the same thing. So 4 comma 4 belongs to S2, 40 comma 4 belongs to S1. Check out, in S2, 40 comma 4, it is available. 40 comma 4 in S1, no, not available. So that implies X2 should be moved. X2 should be moved into the sack. Hope you understood. If both the conditions are true, that means if the pair is available in S of I and S of I plus 1, or sorry, S of I minus 1, then no need to move the weight into the sack. So we need to compare each and every set. Okay, so here 40 comma 4 is available in S2 and 40 comma 4 is not available in S1. So that's why we have to move the second weight because we are checking with the second one, right? Now what happens? So here we need to remove the second element from this pair. So what is the second element? 40 comma 4. So 40 comma 40 and comma 4 comma 4. So what happens? 0 0. So it is 0 comma 0. So we have to check again with 1 and 0 comma 0 with S0. So 1 0 comma 0, yes, and S0 0 comma 0, yes. So obviously X1 will be 0 because the pair is available in both the set S1 and S0. So the solution is 0 comma 1 comma 0 comma 1. So the solution will be either 0 or 1, right? So 0 means we should not move the first weight. 1 means we have to move the second weight. 0 means we should not move the third weight. Okay, and 1 means again we have to move the fourth weight. Just observe, moving off, see this is a weight, this is a weight. Moving off second one, second weight is 4 with a profit of 40. Next, third, fourth means this one. Third weight, okay, with a profit of 50. How much total profit we got? 90 profit. So by moving a 3 and 4, okay, by moving a weights 3 and 4, we got a 90 profit. That is the maximum profit. You can check. So 5 4 it's 50, 4 6 it's 70, 6 3 it's 80, 3 4 it's 90. Just now we got it. 5 3 60. In every combination you can check. So only we will get a maximum profit if you move the third weight and the fourth weight. Sorry, the weight 4 and weight 3. That means the second and fourth one. So X2 and X4. If you move the X2 and X4 weights into the sack, then only we'll get the maximum profit. Okay, so this is how we can solve the knapsack problem. So first we have discussed about what is a knapsack, right? And then we have discussed how to solve it. This is by using the set method. By using the sets, we are using all the combinations, and then we are getting the result with the zeros or ones, which are to be moved and which are not to be moved. So once again, I am repeating. So initially insert one element, and then initially the sack will be 0, and insert one element and combine both the things, and insert the second element and combine both the things, and just remember, so make it a mark of S0, S1, S2, S3 and S4. And one thing we have to remember, the dominance rule: if the Pj greater than Pi and Wj less than Wi, then immediately remove the pair with a less profit. Simple example, we are inserting weight 5 and we are getting a profit of 10, and we are inserting weight 4 and we are getting a profit of 40. So here the remaining weight we can insert into a bag is only 5, and in this case we can insert the weight of 6 into the bag, right? So that means with the highest weight we are getting a lowest profit. So such cases we can remove the pair with low profit, and that we call it as a dominance rule, or the technique called a purging mechanism. And one more thing, so if the weight exceeds the maximum size, then also we can remove the pair. Here you can see 80, 15. So 15 is the weight which is beyond the maximum. So we have avoided it, we have ignored. So here in this case, at 12 and 13 we have ignored, right? And all these are the purging. Okay, so dominance rule, applying the dominance rule. Afterwards, we need to check the highest weight or highest profit pair with the S4 and S3, so that if it belongs to in both the cases, simply we can say we should not move it, because already in either cases, in some other case it may be available. So automatically we should not accept it if the pair is available in Si and Si minus 1. And if not, then immediately we can move that particular weight, and we have to remove the fourth, that particular weight and profit from this particular weight, profit and weight pair. Right? So like that, finally we will get the solution in either only zeros or ones. So this represents we are moving. So by moving the second object and a fourth object, we will get the highest profit. By moving the second object 4 and fourth object 3, we are getting the maximum profit of 90 rupees. So 90, profit as 90. Okay, so this is how we can solve the 0-1 knapsack problem. So today we will see one more example for knapsack problem. So in our previous session we have seen what is a knapsack problem, and then we have solved one problem, right? Now we will see one more problem. So we need to take a number of objects and corresponding weights and corresponding profits, and also the weight, the maximum weight of a sack, right? So let us take 3 objects. So x1, x2, x3, and the profits, so some 35, 40 and 30, and the corresponding weights, let it be 10, 25 and 20, and the maximum sack weight is 40. Maximum sack weight is 40. Now we need to find which objects should be inserted into a sack so that we will get the maximum profit. Okay, now let us assume the sack is empty. So S of 0, it will be 0, 0. And after considering the empty sack, just insert the first object. So I am inserting one object to the empty sack. So we need to add the first profit and weight to this one, right? So these are nothing but profit and weight pairs. The pair is profit and weight. So why I am writing like this means the first element is a profit and the second element is a corresponding weight. So 35 plus 0, it's a 35, and 10 plus 0, it's 10. Now, with one element, that means with one object, the sack with one object is the empty sack and after insertion of one object. So this is a S1. So we need to note down these things. This is S1 and this is S0, which is an empty sack. Now I am inserting one more object to sack with one object, right? So add the second one, 40 and 25 to 0, 0. It is 40, 25. And 40, 25 to this one, right? 40 means 75. Next, 25 plus 10, it is a 35. So you can see it is in an increasing order, right? There is no dominance. There is no dominance. So with a weight of 25, we are getting 45, and with a weight of 35, we are getting some 75. So there is an increase. There is no problem. And S2 is, so combine both these things, 0, 0. So 35, 10, and after insertion, so 45, 25, and 75, 35. Right? Now, this is the S2. So we have taken three elements or three objects. So we need to calculate the S0, S1, S2 and S3. Because already two elements or two objects have been inserted into a sack. Now the third one. So after insertion of 1 in sack 2. So what is the third one? 30, 20. So 30 plus 0, 20 plus 0. So 30, 20. 30, 20. So 65, 20 means 30. 30, 20. So 75, 20 means 45. 30. So 105 profit, 20. It's a 55. It's a 55. Right. Now you can eliminate these two things because the maximum weight is a 40. The sack can accept up to 40, right? But here we are having some 45 and 55, which is beyond the maximum weight, so we can avoid these things. And now we can consider only these terms, that is S3. So 0, 0 and 30, 20. 30, 20. Next, 35 and 10. 45, 25. 65, 30. 75, 35. And here you can see with the 20 weight we are getting some 30 profit, and here with 10 weight we are getting 35 profit. So which is a dominance, right? Which is a dominance. So with a less weight we are getting more profit. So what we have to do? So we can simply avoid the pair with less profit. So among these two, the less profit is 30. So we can simply avoid this set or this element, right? Now we'll write the pair. S3 is equal to, what are the pair? So 0, 0, 35. See, you can observe 35, any other deviations, dominance here. So 35, 10, 45, 20. So both are maximum, and here also maximum. 45, 65, 25, 30 maximum. 65, 75, 30, 35 maximum. So there is no dominance, right? So 0, 0, 35, 10, 45, 25, 65, 30, 75, 35. So among these one, so we can see this is the maximum profit. We can get a maximum profit. Now we'll go with this one. So checking out 75, 35, which belongs to S3, and 75, 35 belongs to S2. So let us check. S3, 75, 35 belongs to S3, true, and 75, 35 belongs to S2. So whether there is a 75, 35 and S2, yes, it is there, right? So there is no change, we need not change. And the third element cannot be inserted into a sack. Third element cannot be inserted into sack. After that, we have to remove, so we need not remove it, okay, because in both the things we are having the same thing. So 35 belongs to S2 and 75, 35 belongs to S1. Let us check. S2, yes, it is available. S1, there is no. So there is no. So there is a deviation. Obviously we can say X2 should be inserted. X2 must be inserted because in S2 it is there, in S1 it is not there. Now what happens? We have to remove the second object, second object profit and weight with this one. So 40, that means a 35, 10. Check it out, S1 and 35, 10 belongs to S0. So we need to check only in two sets. One is S power I and the next one is S power I minus 1. Okay. So 35, 10 it's available in S1, right? Yeah, 35, 10 is not available in S0. So obviously we can move the first object into sack. First object into sack. So you can say the solution S is equal to 1, 1, 0. That means inside the sack we are supposed to move the first object and second object so that we'll get the highest profit. So what is the first object and second object? 10 weight and 25 weight. 10 plus 25. So what is the profit here? We are getting 35 plus 40, which is 75. Okay, so let us check more. Okay, so if you move 25 and 20, that means second object and third object, we can't move because the weight goes beyond the maximum size, right? So we can go with x1 plus x3. So 10 plus 20, the profit will be 65. Okay, so there is no chance. So obviously with this move we can get a more profit. That means moving the objects x1 and x2 into the sack will get a maximum profit. Well, so today we'll see one more concept in a dynamic programming in algorithms, that is a traveling salesman problem. So this problem will solve by using the dynamic programming method. So in our previous session we have already seen what is a dynamic programming, right? So a complex problem will be divided into subproblems and each subproblem will be solved and the solution of each subproblem will be saved in the memory so that in future, in order to avoid the recalculation, so we'll make use of the existing solutions. And this is also mainly used to solve the optimization problems where there will be a lot of solutions. Among them, we have to select the optimal solution based upon the given constraint. So this is about the dynamic programming. So about all these dynamic programming we have seen in our previous sessions. So I'll post the link in the description. So just go through. And now we'll see what is a traveling salesman problem. So here, first let us see what is this problem. So there will be a graph. So here we are supposed to take a graph. Okay, so consider different vertices and edges. We know that a graph will be having vertices and edges. So how this graph is related to our salesman problem? So consider the edges as a distance and vertices as a places in the city. So how the salesperson travels from one place to another place, covering all the places in the city with a minimum distance. Okay, so assume each vertex as a place in the city, so that from the source the salesperson should start traveling and have to visit all the places only once. Okay, all the places only once, and have to come back to the source. So this is the salesman problem. That's also with a low cost. That means distance, least distance. So for that relation, we are taking the complete places as a vertices and the distance as a edges, so that we can have a graph and we can solve it. So one thing, we have to select a source. So selection of source, that's the first important point. And the second one, so starting from source, traverse through all vertices in a graph exactly by one time, and come back to source with minimum distance or cost. Minimum distance or cost. So we have to select the source node, and from that source node we have to traverse all the vertices exactly one time and come back to the source with a minimum distance or cost. So for this we have to consider a weighted graph. So every edge should have a weight which represents the distance or a cost, whatever it may be. Okay, so we have to consider weighted graph. And one more important, so we can have the directed graph or undirected graph. So graph can be directed or undirected. So I think you know the difference between this directed and undirected. Okay, for example, if A, B, C, and this is a graph. Okay, this is a graph. So there is no directions on the edges. So this comes under undirected. For example, A, B, C. Okay, so there is a directions. So there is a direction. That means this edge is between A and B. This edge is between B and C. This edge is between C and A, right? So there is a directions. So this is a directed graph. So we can work this problem, traveling salesman problem, either on both directed or undirected, but it should be a weighted graph. So for every edge there should be a weight, okay, which represents the distance or a cost. And one more important point is the graph, either directed or undirected, the graph should be complete graph. So what do you mean by complete graph? So every vertex should have the edge to all other vertices. Okay, for example, consider A, B and C. So this is an undirected graph. So we can say this is an edge between A and B and also B and A. For example, let us take the distance. So this implies the distance between A and B is 10. Similarly, the distance between B and A is also 10. Distance between A and C is 20. Similarly, C and A also 20 because undirected. So if it is like this, A to B, B to C, C to A. So this is also an directed graph but not a complete graph because A is having an edge from A to B. There is no edge for A to C. And B is having an edge for B to C. There is no edge for A. C is having an edge for A. There is no edge for B. So the complete graph means every vertex should have the edges towards all other vertices. For example, so A is here. I will write one more edge here. So A is having edges to B and C. Now B is having only for C. I will write here. So B is also having an edge from A and C towards A and C. So C is having only for A. So C is also having an edge to A and B. So A is having edge to B and C. B is having an edge to A and C. C is having an edge to B and A. So this is a complete graph. This is the complete graph. Complete directed weighted graph. Okay, so this is a complete weighted, the complete directed weighted graph. Okay, so in such type of graphs, we can apply this traveling salesman problem. Okay, so these points are most important before starting the problem, right? So selection of a source, we can select any vertex as a source, but from that particular vertex, we have to traverse all other vertices exactly once and come back to the same vertex. And consider a weighted graph, so that should be a weighted. Graph can be a directed and undirected. Graph should be a complete graph. So these points are most important. Right. Now, so before going to this one, let us have a formula. So just remember the formula so that while solving the problem, you can understand the formula exactly, right? So here we'll write a formula. The function I comma set. S stands for set, which contains a number of elements, or we can say vertex, right? Is equal to cost of I comma j. So j. So here, okay, I'll write here itself. I'll erase this one. I'll write here. So g of I comma set, which contains all other vertices, is equal to minimum of j belongs to set cost of I j plus again a function j comma set minus j. So this is a formula which we have to remember while solving the problem. And one more formula, g of I comma pi is equal to cost of I comma source. I comma source. Okay, right. And one more thing, remember one more thing, cost of I comma j will becomes 0 if I equal to j, and becomes cost of ij if ij edge belongs to graph. Ij belongs to graph. That means if there is an edge between I and j. Okay. So just remember the cost, if I and j both are equal, then the cost will be 0. Right? Yes. Otherwise we can write down the direct. So remember this formula. Remember this formula. So we need to calculate the shortest path from source, visiting all vertices, and come back to the source. Right. So I is a source. Okay, I is a source, and S is a set of all vertices. Set of all vertices other than I. Okay. From that we have to find out the minimum. Okay. So we'll write down the example. So let us take this example. Okay. So this is a undirected graph. Okay. First let us check. It is an undirected graph. This is a weighted graph because for every edge there is a weight. And let us check whether it is a complete graph or not. So here we are having a 4 nodes, that means a 4 vertices. So every vertex should have the 3 outgoing edges. So A is having an edge from A to B, D and C, right? From B to A, B to D, B to C, okay? C to B, C to D and C to A, okay? D to A, D to B, D to C, yes. So this graph is a complete weighted undirected graph. Now we have to solve the problem. First let us write down the table. Okay, let us write the adjacency matrix. So I am writing here. So A, B, C and D, and here also A, B, C and D. So we'll write the cost. Okay, so this is I and this is J. So there will be no edge from A to A or B to B or C to C or D to D. So that's why I have mentioned. So cost of I comma j will be 0 if I is equal to j. So if I is equal to j, then the cost will be 0. And it will be Cij if the edge ij belongs to graph. Okay, see, A to A. So I is equal to A, j is equal to A. Obviously it will be 0. Next, A to B. Then if there is an edge, A to B, yes, there is an edge. So belongs to graph. Okay, A comma B belongs to graph. So that implies the cost is 10. Next, A to C, 15. A to D, 20. Similarly, B to A, 10. B to C, sorry, B to B there is 0. B to C is 35. B to D it's a 25. Similarly, C to C again it's 0. C to B it's 35. C to C 0. C to D it's a 30. Similarly, D to A it's 20. D to B is 25. D to C it's 30 and it is 0. Okay, sorry, C to A 15, it's not 0. C to A it's 15. Right. So this is an adjacency matrix. Okay, so this represents a cost from one edge to another edges. It's clear. Now, so just start with the set 0. Okay, if the set contains 0, what are the different possibilities? If set contains one element, what are the different possibilities, different edges? Now we'll select the source. So I'll write source as A. A is a source. Okay, A is a source vertex. Now, first, if set is equal to 0, okay, the set contains different elements. Okay, so 0th element, first 1 element, 2 element, 3 elements, because the source is A. So if set is equal to 0, if set is equal to 0. Apply the formula G of I means B. So from B, comma, set is 0. There is no element. So that can be represented as pi. If set is equal to 0, then we can represent it as pi. Now what happens? See, if I 0, then I comma source. So this will be G of, what is I here? B, comma, what is the source? A. So what is the cost here? B to A. B to A, it is a 10. Similarly, there is a possibility of C to pi. C with no element. So G of C comma source, which is nothing but C to A, it's a 15. Similarly, G of D comma pi. G of D comma A, which is DA, it's a 20. So which means if the last vertex is B, if the last vertex is B, obviously our statement says that we have to visit all the vertices and come back to source. So that's what happens. So if the last vertex is B, then what is the edge from B to source? And if the last vertex is C, C to A, that means, for example I am saying A is here, the next edge can be B, C and D. From this, if B, the next edge can be C and D. Next edge can be B, D. Next edge can be B, C. And A, B, C, obviously it will be D. A, B, D, obviously it will be C. If A, C, B, it's D. A, C, D, it's B. A, D, B, it's C. A, D, C, it's B. So only one vertex. So all the vertices have been visited, right? So this is a possibility, maximum possibilities, all possibilities. So after coming to D, what's the next move? So visited all vertices here. So it should go back to A. Similarly, if it is C, it should go back to A. If it is D, again it should go back to A. B, go back to A. C, it should go back to A. B, it should go back to A. So that's what here we have written. If B with a null set, if B with a null set, that means no other vertices are remaining to visit, then obviously the next move will be from B to A. And that means at this position, if there are no unvisited vertices, if set is 0, no unvisited vertices, obviously the edge should be towards the source. So that's why we have written this formula. I comma pi, then I comma source. Right? So hope you understood this one. And the next possibility. So only 3 possibilities, because we are having 4 edges, 4 vertices A, B, C, D, and here we have taken source as A. So we need to check the possibilities of all the remaining 3, B, C, D. Right? Now, if set is equal to 1, that means if there is only one unvisited edge, unvisited vertex. If the set contains unvisited vertex, only one unvisited vertex, then possibilities G of B and the unvisited from B, where it can go, either it can go to D or B, it can go to C. Only 2 possibilities. Okay, only 2 possibilities. So if there are one more vertex, for example, if there is one more vertex, then we can write it here, G, B comma E. That means there can be edge between B and D, B and C, B and E. So anything, right? So the set contains 1 means having one unvisited edge, vertex. So always I am getting edge, right? So that's a vertex. Okay. So write down the formula here, B, D. So what is the minimum of J belongs to S? Here J means D. D belongs to set S. So Cij, that means C, B, D plus G of J comma set minus J. J here D, D minus, D comma set minus D. So here set is nothing but D. See, here set is nothing but D. So D minus D, obviously it will be empty, right? So empty means we can simply write it here, pi. Okay, so there is no other edge, only one edge is here. So only one unvisited vertex. So we are just getting the cost of that particular unvisited vertex. So if there are multiple, obviously we can have to select the minimum edge. So here we are having only one thing, so we can simply remove it and we can write it C edge BD plus G of D comma phi. Okay, so you can see what we have done in the dynamic programming. So we are dividing the complex problem into subproblems and we are calculating each subproblem and we are storing in the memory. So that's what we are doing. So here G of D comma phi we need not recompute it. So already we have recomputed. So D comma phi is this one. So obviously we can get the value from here. So CBD plus G of D comma phi, which means cost of B and D, it's a 25 plus 20 D comma phi. So which is 45. Now again G of another possibility. So there can be an edge from B to C. So this can also be written as BC plus G of, so what is the J here? C comma set minus C. Obviously it will be pi. So the edge between B and C, BC 35 plus G of C pi, it's a 15. So which will be 50. So here we have taken B as a source and we are computing the cost between B and all unvisited edges. See here, next change it, C to B. We can check the possibility. If C is a node and we have to check from C to all possible unvisited vertices. So C to B, and similar here, CB plus G of B comma set B minus B. So obviously it is pi. So which will be CB 35 plus G of B phi 10, which is 45. And similarly from C there might be having an edge to D. Okay, C to B. Okay, now C to D. Cost of CD plus G of D comma pi. So cost of C comma D, C to D is 30 plus D pi 20. So which is 50. Hope you understood. If set is equal to 1, we need to, the set is 1 means one unvisited vertex. There is a one unvisited vertex. Okay, so we need to check all the possibilities towards that unvisited vertex, right? So if you consider B to D and B to C. If you consider C to B and C to D, because we are having only 4 vertices. So if our graph is having the 5th vertex, so here we'll get one more thing, G of B comma E. Okay, that's also one possibility. The same thing, right? Now, consider set is equal to 2. That means 2 unvisited vertices. Unvisited vertices. Here also we have to go with the different possibilities. Check it. G of B, consider B as a source. From source, 2 unvisited vertices will be either C comma D. Okay, C comma D, unvisited vertices. So how we can write it here? Here we can write minimum of, okay, first cost of BC and cost of BD plus G of, what happens here, C comma, okay, set C comma D minus J C plus G of D comma C comma D minus D. So among these two we have to find out the minimum from this formula only, right? J belongs to S, C, I, J. So C, D are the two elements in the set. So BC and BD. So in this case, J value is C. So G of J value C comma set C comma D minus J minus C. And in this case, J value is D. So plus G of D comma C comma D set minus D. So obviously you can see set C comma D minus C means it will be D. Okay, and here C minus D means it will be C. Hope you understood. So among these two, we have to select the minimum. So that's the formula. And in the previous case, we are having a set with only one element. Okay, only one unvisited node. So we are having only an edge between B and D, B and C, C and B and C and D. Now we are having two unvisited vertices. We are having two unvisited vertices. So there can be a chance of having an edge between B to C and B to D. B to C and B to D. So among those we have to select the minimum cost. So that's why minimum BC plus this one. And here, and this will be BC 35 plus G of C comma D. Already this was calculated here. C comma D, which is 50. So which is 50, 85. And coming to this one, C of BD, 25 plus DC. Already we have calculated here. Oh, we have missed it. Yes, we missed it. I'll write here G of D comma C. So we have missed it. We have calculated till CD. So for D also we have to calculate, and DC. So C of DC plus G of C comma 5. So which is DC 30 plus C 15 is equal to 45. There is one more possibility. From D there can be a chance of edge to B. So this is one more chance, right? So C of DB, that means the cost of DB plus G of B comma 5. Similar to this one, right? Similar to this one. So what is the cost here? DB. So D to B 25 plus G of B pi. G of B comma pi. Okay. So G of B pi 10, which is 35. Which is 35. Right? I'm sorry, the board is very small, so I'm forcibly adjusting everything in the single board, right? Okay, just right. Now here you can get cost. G of D comma C D comma C cost is 45. So which is equal to 70. So which one is the minimum? 70 is the minimum. So you have to consider this one. Okay. Now again G of, if C is a source, what are the remaining elements? B and D. So minimum of CB, CD plus G of B comma, okay, from set we have to minus B, so obviously it will be D plus G of D comma B. So which is cost of CB it's a 35 plus G of B comma D, which is 45. It's a 980. Okay, and this one CD, C to D 30 plus DB, here we have written DB 35. So which is equal to 65. So among these two, which is minimum? 65 is the minimum. So this we have to consider. And the next one, G of, what is the next? D. If the possible source is D, from D there can be edge between B and C. So here we can write B and C is equal to minimum of CDB, CDC plus G of B comma, from set we have, if you minus B, the set will be containing only C, plus G of, if C is a source, and remain minus C from the set, so it will be B. So what is the amount here? Cost of DB is a 25 plus BC cost is 50, 75, and here what is the cost here? D to C 30 plus CB, which is a 45, again it is a 75. So both the edges will be having the same cost, so we can select any one edge, no problem. Okay, so only possibilities, 3 possibilities we have chosen, right? If the source is B, there can be edge from B to C or B to D. If the source is C, there can be edge between C to B or C to D. If the source is D, from D there can be a source to B or C. Now, if set contains 3 elements, that means 3 unvisited nodes. So G of, here 3 unvisited means the source A, B, C and D, because here we are having only 4, right? Among 4, the 3 are unvisited, and obviously the next one will be the source. So I'll write here, so which will be a minimum of C of AB, C of AC, C of AD plus G of B comma, if you subtract B from set, it will be C comma D plus G of C comma BD plus G of D comma BC. Okay, hope you understood this formula. So J comma, from set we have to subtract the J value. Okay, so here J value is B, we are taking B from set, so CD. Here J value is C, we are taking C from set, so it will be BD. Here D is a J value, so we are taking D from set, so it will be BC. Okay, so calculate the cost. CAB, so AB cost is 10 plus B of C, D. So here we have calculated, and here we are having a two values. Among these we have to select the minimum, so 70, so which is 80, and the next one AC, A to C, it's a 15, plus CBD. Here also we have calculated two values, 80 and 65. So among these we have to select the minimum 65. So it is also 65 and the result is 80. And the third one, AD, cost of AD is 20. D of BC, which is both are same value, so we can select any value. So it is 75, which is a 95. So among these three, we have to select the minimum, and see, we have to stop the process because we are having a maximum of 4 nodes or 4 vertices, and among these the 3 are unvisited. So already we have fixed that one as a source, and only the possible are 3 more vertices, and we have repeated from 0 unvisited to 3 unvisited. So we have to stop here, right? Now among these we can select the minimum, but here you can see we are having a 2 possibilities because 2 values are same, 80, 80, and we can't select this one because it is the highest. So we have to select either this node and this node. So the path, the possible solutions are A to B or A to C. So A to B or A to C. Okay, then first if it is A to B, the next one is B, C, D. Go to here, B, C, D here. So among these we have selected this one, right? So this one we have selected, B to D. Now B to D. And coming to this one, A to C. If A to C is 1 edge, then next to CBD, CBD. Among these we have selected the minimum, that is CD. So the next vertex visit is D. Now if D, okay, this one we have selected. Next D comma C. Go to that thing, D comma C, this one, D comma C. So the cost is DC. The next one will be C. And similarly here also go to CD, DB. So DB means here. So after that the next node will be B. And after that, in both the cases, the next vertex will be A. So that implies there are 2 possible paths where starting from A, visiting first vertex as B, next D, followed by C, and come back to A. This is one possible path with a distance of 80. So you can calculate A to B, which is 10, B to D, which is 25, D to C, which is 30, and again C to A, which is 15. Total we will get 80. And similarly here, starting from source A, visiting first vertex as C, next vertex as D, followed by B, and come back to A. So in both the cases the distance is 80. So there are 2 possible paths. So if we are having only one among these 3 are minimum, so that will be the single path where the person can travel from source to visiting all vertices and come back to the source. So here we are just calculating and we are saving the result, and we are making using this result in further procedure. Right? So today we will see one more problem in traveling salesman problem. So in our previous session we have seen what is a traveling salesman problem, and we have solved one example which is an undirected complete weighted graph. Now in this session we will see one more example which is weighted directed complete graph. So we have seen the difference between a complete graph and a normal graph, and also weighted graph and unweighted graph, directed and undirected, right? So now we will solve this example, right, by using the dynamic programming. First let us write the adjacency matrix, and we'll erase this one because the board is very short. So I'll write the adjacency matrix and I'll erase the complete thing, right? I'll write the adjacency matrix here. So A, B, C and D. So 4 vertices So we'll write the cost from one vertices with another one. So A to A, so which is always 0, and A to B, so A to B it is 10, A to C it is 15, A to D it's 8, B to A 5, B to B 0, B to C 13, B to D it's 10, C to A it's 6, C to B it's 9, C to C 0, C to D it's again 9, and D to A it's 20, D to B it's 8, D to C 12, and D to D is 0. So this is the adjacency matrix, right? So I'll erase this one. So which is an weighted, directed, complete graph. Now first we'll write the formula. So we need to remember two formula before starting the solution, right? So G of I comma set of S is equal to minimum of J belongs to set cost of Ij plus G of J comma set minus J. This is one formula. And another formula, so cost of or G of I comma phi is equal to G of I comma cost of I comma source. So we need to remember these two formula, so before starting the solution. Now we need to find the minimum distance from source vertex visiting all other vertices at least once, exactly once, and come back to the source vertex. So we'll see the source vertex as A. So we can consider any vertex as source vertex. So the first step we have seen in our previous session, that is we need to select the source vertex. So here I will select the source vertex as A. Now we need to start from A, visiting all nodes and come back to A with a minimum distance. So we'll write the next possible source, unvisited. So first one, let us take if set is equal to 0, that means no unvisited vertices. If there are no unvisited vertices, then the recent vertex will be the last vertex. So the possibility is G of B comma phi, because itself is the last vertex. So what is the formula of this one? G of I comma phi is a cost of B comma source. Here the source is A, cost of A. B of A, cost of B comma A. So we can write simply it as G of B comma A, which is B to A, it's a phi. Similarly, if the last vertex is C, then obviously if the last vertex is C and there are no unvisited vertices, then immediately we need to reach the source. So that's what the problem. So we need to start from source, visiting all the vertices exactly once and come back to the source. So if the last vertex is C and there are no unvisited vertex, so obviously we need to go to the source. So G of C comma source. So CA, which is a 6. And the next possibility D comma pi is equal to G of D comma source. So it is 20. Okay. So the only possibilities are this one. The only possibilities are this one. Now let us assume if set contains 1. 1 means unvisited vertex 1. So I'll write here 1 unvisited vertices. 1 unvisited vertex. Okay. So, for example, if we are at B and there is only one vertex, so what are the remaining vertex? For example, if we are at B, what is the remaining vertex, unvisited vertex? It may be C or it may be D. For example, if our graph is having one more vertex like this one, B, C, D, E, right? So if our graph is having one more E, then there is a one more possibility E. So we need to check the cost for each and every edge. If B, B to C, B to D, B to E. That means the set contains only one unvisited. Only one unvisited. So if we are at B, the unvisited can be C. And similarly, if we are at B, the unvisited is D. So two possibilities. So we are at B, so unvisited vertex, it may be C or D. So we need to find out this one. So what is the formula? Minimum. So here we are set is having only one element. So we need not write this minimum because we will get only one formula. So C of BC plus function of, what is this one? Consider it as a J. So J, that means C, comma, G of J, comma, C, comma, set of C minus C. Set of C minus C. So this can be written as a pi. So obviously, so we can replace this one. So we are having the set as C. We have to subtract the C itself from the set. So the remaining is pi. Okay. So what is the amount here? What is the cost here? CBC. What is the BC cost? B to C 13 plus G of C, comma, sorry, yes, this is the thing I have written wrong. So G of C, comma, pi. Okay, C, comma, pi. So what is the value of this GC pi? Already we have calculated here. So that's what we are saying in the dynamic programming. So the complex problem will be divided into subproblems and we are solving the subproblem and we are storing the result so that in future if it is required, so we can make use of the value from the memory. So here already we have calculated, so we need not calculate once again. So we can simply use this value 6. So here 13 plus 6, which is 19. 13 plus 6 is 19. And now let us calculate the second thing. So the next possibility, B, comma, D. If the unvisited vertex only one is D, then C, B, D plus G of D, comma, pi. Because the set is having only D and we need to subtract the same vertex from the set. So which is nothing but pi. And here what's the value? BD, HBD, B and D. It's a 10 plus G of D pi, which is 20. So what is the value here? 30. So we need not select the minimum because only one calculation. This is one edge and this is one edge. Okay. So this is 19 and this is 30. So now change the vertex. If we are at C, the possibilities are B. Okay. So cost of CB plus G of B, comma, pi. So which is a cost CB it's 9 plus GB pi, it's a 5, which is 14, which is nothing but 14. And the next possibility, G of C, comma, D, if the unvisited vertex is D. So cost of CD plus G of D, comma, pi. So cost of CD, edge C, D is 9 plus G of D pi, 20, 29. Okay, so we have completed the two vertices. Now, if the vertex, we are at D, if we are at D, So G of D comma, the possibilities are C, so which is cost of DC plus G of only one element, so C comma pi. So DC it's a 12 plus C pi, which is 6, is equal to 18. And there is a one more possibility. If we are at D, the next unvisited can be B. So C dB plus G of B comma pi. B comma pi. Then see dB. So dB means 8 plus G of B pi, which is a 5. So which is 13. So we have completed all the possibilities if unvisited is one vertex. If unvisited, so just listen carefully. So if the set is having only one unvisited and we are at B, then the possible unvisited vertex will be C and D. And the next possibility, if we are at C, the next unvisited will be either B or D. And if we are at D, the next unvisited will be either C or B. So we are calculating for all the possibilities. Now, so we have calculated all the possibilities if set is equal to 1. Now calculate with set is equal to 2. That means if set is having 2 unvisited vertex. 2 unvisited vertices, right? Now calculate G of B, okay, comma, if the set is, if we are at B, the next 2 unvisited can be C comma D, okay, C comma D. So how we can write this one? So G of, we have to write down this formula. So we are having a 2 possibilities, 2 edges, one is BC, another one is BD. So among that we have to select the minimum. Okay, so previously in the set we are having only one unvisited vertex. So we need not calculate the minimum because we are having only one edge. There is the possibility of having one edge. But here we are having in the set 2 unvisited vertices. So that means there will be a 2 possible edges. So among those 2 possible edges, we need to select the minimum one. So how we can write? So G of, I'll write here, okay. So minimum of cost of BC, cost of BD. So these two are the possibilities. Plus G of, okay, what's the formula? G of J. Here J is C comma set minus J. So set minus, here the set is having 2 elements. So set minus C, obviously it will be D. And here also G of, here J is D. So D comma set minus D, it will be C. So we need to select the minimum cost among these two. So what is the cost of this one? So BC, okay, BC, B to C, it's 13 plus G of C comma D. Already we have computed this one. G of C comma D. So G of C comma D, which is 29. So this will be 29. So 13 plus 29, right? So that will be 42. Okay. And what about this cost? C of BD. BD. It's a 10 plus G of DC, already calculated. DC, which is 18. So the cost will be 28. So among these two, which one is the minimum? So this is the minimum value. Okay, we need to select that one. And next, so this is the possibility. If we are at B, the next possible edges will be either C and D. Now, G of, if we are at C, the next possible unvisited are B and D. What we have to do? So minimum of cost of CB and cost of CD. And here the j value is b, so b comma, from the set we are removing the b, so the remaining is d, and here it is d, and in the set, from the set we are removing the d, so it will be b. So what is the cost? Cost of CB, what is the CBH? 9, so this is a 9 plus G of B comma D, already we have computed, so BD, so this one 30, which is 39. And what about this one? CD, C to D, it is 9 plus DB, here DB, which is 13, which is 22. Right? So among these two, which is the minimum? This one is the minimum. This one is the minimum. Okay. So among these two, this is the minimum. Among these two, this is the minimum. So if we want to consider the edge, we have to consider this edge. That means C to D. And if you want to consider here the edge is B to D. Okay. Now, so what happens here? Again, check one more possibility. So there is one more possibility. G of, if we are at D, the next possible edges will be B comma C. So how we can write it? So minimum of cost of DB and cost of DC plus G of, here B is a J, and from Z remove B, so C, and here also G, the J is C, from set remove the C, so it will be B. Now calculate the cost. DB, so DB, which is 8 plus G of B comma C, G of B comma C, which is 19, which is 27. And what about this cost? DC, D to C, 12 plus G of C comma B, G of C comma B, which is 14, so which is 26. So among this one, this is the minimum. Sorry, this is the minimum. Okay, this is the minimum. So if you want to consider the edge, we need to consider D to C. Okay, so here we have completed the set 2. That means set of 2 unvisited vertices. Now we will see set of 3 unvisited vertices. So if S is equal to 3, so 3 unvisited. So what is the possibilities? So G of, so 3 unvisited vertices means B, C, D, because in our graph we are having 4 vertices. Among these 4 vertices, 1 vertex we are considering it as a source, and remaining 3 are the unvisited vertices. So simply here we can write it as source, and in the set B, C, D, all the 3 are unvisited. All the 3 are unvisited. Now what we can do here? So we can write it as minimum of cost of AB, cost of AC, cost of AD plus G of, here J is B, so G of B minus set minus J, set minus B. Here the set is having BCD, and among that we have to remove the B, so it will be set of C comma D, and here also G of C comma, and here the J value is C, from set we have to remove C, so it will be B comma D, and here also G of J value is D, and we have to remove D from set, so it will be B comma C. Now calculate here, right? So we need to consider the minimum among these 3. So CAB, that means edge AB, A to B, it's 10 plus G of B comma CD. Already we have computed this one. G of B comma CD. Okay, what is the value? So we are having two values and we have to consider the minimum. So among these two, 28 is the minimum. So we have to consider 28. So the result is 38. And coming to this one, A to C. So A to C, it is a 15. 15 plus C comma BD, already computed, C comma BD. Here also we got two values. Among these two we have to consider the minimum. What is the minimum value? 22. So here we need to give 22, which gives 37. And coming to this one, A to D, which is 8 plus G of D comma BC. D comma BC, among these two the minimum cost is 26. Consider 26, which is 34. Okay, so among these three values, which one is the least? 34 is the least, right? So we have completed this one. There are no other possibilities because the from source, let us consider all the remaining three vertices are unvisited. So that also we have computed. So we need to stop here, right? Now we need to find out the path with the minimum distance. So what is the minimum distance among these three? So only 34. We are getting 34, right? So all the remaining values, that means remaining 37 and 38 both are greater than 34. So here we are having only one path with a minimum cost, that is 34. Now we have to write down the path. So what is the edge of this 34? A comma D. So from source, the next visited vertex is D. Okay, next visited vertex is D. And then we need to find out the next edge from this function, GDBC. Go to here, GDBC. Which one we have considered? This one. So from D, next vertex is C. So we have to consider this DC. The next vertex is C. Right? And again, go to this function for finding the next edge. So from C, next edge, C to B. So go to here, C to B. So edge is C to B. That means B. Okay, B. Because here we are having only one value, right? So go to the B to 5. B to 5. The next edge is A. So obviously it will return back to A. So here the cost is 34. So this is the shortest path. Okay, the shortest path means, so minimum distance visiting all the vertex exactly once from the source and coming back to the source. Now we'll see A to D, it is 8. D to C, it is 12. C to B, it's 9. And B to A, it is 5. So you can consider 8 plus 5, 8 plus 12, 20, 29, 29 plus 5, 34. So which is this one. So we need to consider this edge. And from this, we have to consider this one. From this, we have to consider, so C comma B, this one. And from this, we have to consider this one. So these are the edges. So this is the order we have to, the salesperson or the salesman traverse the vertex with a minimum distance, right? So if you are having 5 vertices, the one more calculation will be there. So this is a one more calculation, and after that we'll get the final calculation. So once practice with on any random graph considering more number of vertices, so that you will be getting understandable. So you will be understanding very easily. So today we will see one more problem in dynamic programming in algorithms concept, that is longest common subsequence among two strings. Longest common subsequence. Right? So we'll see what is exactly about this longest common subsequence, and then we'll solve a problem. Okay, so the first and important point we have to know is there is a difference between a substring and a subsequence. Okay, so subsequence is different from substring. Okay, so most of the people will confuse about this substring and subsequence. For example, let us take AB, CB as string 1 and some random numbers, string 2. So let us take these two strings. Okay, two strings. So here, first, what is a subsequence and what is a substring? You can see, let us take some AB, right? So we are having in both the strings we are having the A and B, right? So AB we can call it as a substring, okay? AB we can call it as a substring, common substring in both the strings. And if you observe here, then how it differs from subsequence? So sequence means order in which we are arranging the alphabets or characters or numbers or anything, right? Elements. In general, we can call it as elements. So arranging the elements in an order, right? So sequence. So we need to find whether there is a sequence or not. Okay. First, let us take A. Okay. So A, B. In this, we can see the particular sequence. That means A should appear first and next B should appear. Okay. So in between there can be any number of elements, no problem. Okay. That means there should not be a consecutive. There may not be a consecutive. Okay. So in between the alphabets or in between the elements there can be anything. But only one thing we have to check, the first A should appear and then B should appear. That means before B, A should appear. So here A we are having and then B, AB, okay. AB is one subsequence. And what about C? ABC, ABC, and here we are having A, B, and after that we are not having C. In the second string we are having a C and after that we are getting A and B. So we can't tell that A, B, C as a subsequence. Okay, and see, let us start with the B. Let us start with the B. So B afterwards C. You can observe here B afterwards C. Yes. So that will be a subsequence. And B, C, and again we are having a B. So here also we can observe B, C. Again we are having B. Okay. B, C. Again we are having B. So there is a sequence. So even though in between B, C, B we are having some more elements, right? That doesn't bother about that, right? Subsequence means you have to follow the sequence whether the elements are following the sequence in the second string or not. So B, C, B, yes. And if you start with the C, so C followed by B, you can observe C is here and followed by B. Okay, B appears after C. Yes, correct. So CB, CB is one more sequence. Next, CB, and there are no other elements, right? Next, last one is a B. So here the last one is a B. You need not write that. So these are the common subsequences. Common subsequences. You can see. So first one A, B. So B should appear after A. So here also B is appearing after A. Here also B is appearing after A. B, C. C before B, right? C before B, right? B, C, B. B, C, B. Yes. Next, C, B. If you take a randomly, take this one, A, B, C, B. So A should appear. Yes, we got it. Next, B should appear. Yes, we got it. Next, C. So there is no string, right? So in the second string, C is appearing before A and B. So A, B, C, B is not a subsequence, only this one. And among this one, the longest common subsequence. So this is the longest common subsequence because it is having some 3 elements. So I am generally writing it as elements. You can consider it as a characters or numbers. Okay, right. So how to find all these things? How to find all these things? So just we have to remember 2 formulas, and first of all we need to draw a matrix. Matrix means rows and columns. So towards the rows we have to write down one string, towards the columns we have to write down another string, so that we'll get some matrix, 2 by 2 matrix. Okay, see, first, what is the length of this string? You can consider the same string. So length is 4, and here the length of this one will be 1, 2, 3, 4, 5. Now the matrix, we have to draw the matrix with 4 by 5. So you can draw either 4 by 5 or 5 by 4. So you can go with a 4 by 5 or a 5 by 4. So if you go with a 4 by 5, so number of rows will be string 1, number of columns will be string 2, and here also number of rows will be string 2, number of columns will be string 1. Okay, so like this we have to first draw the matrix. Okay, right. First we will draw the matrix. Right. See, I'll write here. So A, B, C and B. And here I'll write B, D, C, A and B. So first design a matrix, a table, and then we'll start the procedure. We'll see your formulas, and then we'll start the procedure how we can find out the longest common subsequence. Right. So you can observe here. So extra we have written 1 column and 1 row. You can observe here, right? So this is again separate column and separate row. Right? So initially fill all these first row and first columns with zeros. First rows and first column with zeros. And towards this one it is string 1, and towards this one it is string 2. Right? Now let us see, the index is I and here the index is J. Okay, how can we represent this particular box? So corresponding rows and corresponding columns. Okay, so this particular portion we can represent with corresponding rows and corresponding columns. So for everything we will get some I value and J value. Consider it as an index. Okay, simply you can consider it as an index. So I, J can represent the corresponding column. Now what are the 2 formulas we have to remember? So I'll write the formulas here. If, okay, so consider S as a string. Okay, so S of I is equal to S of J. Consider any string. So this is a string or a character, whatever it may be. So S means this one, A. Here S means this one. So S of I is equal to S of J. Then what we have to do? So we have to add with LCS. So this is usually called it as a LCS. So longest common subsequence, LCS. LCS of string of I minus 1, j minus 1. So we need to find out, or we need to add one number to this particular box. So this particular column, okay, this particular cell. So 1 plus LCS of S of I minus 1, j minus 1. Similarly, the next part, if S of I not equal to S of j, what we have to do? So we have to select a maximum value among LCS of S of I minus 1 j or S of I j minus 1. Okay, I j minus 1. For example, let us consider 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. And here 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. 2, 0, 2, 1, 2, 2, 2, 3, 2, 4. For example, consider. So if you want to fill this particular position, so here just remember two things. Means 0, 0 means ith row, jth column. 1, 0, first row, 0th column. Okay, and this one 2, 2, second row, second column. Okay, second row, second column. So we are starting from 0, and initial first row and first column, just avoid it. Okay, starting from this one. So 0, 1, 2, so second row, 0, 1, 2, so second column, right? So let us assume that, and we will see this formula. 1 plus LCS of S of, for example, if you consider 11, here S of I is equal to S of j. Okay, so S of I is equal to S of j. S of 1 is equal to S of 1. What we have to do? If both are equal, we need to add 1 plus LCS of S of I minus 1. I minus 1 means S of 0, j minus 1, 0. So if you want to, if the elements are equal, S of I and j, both the elements are equal, that means these characters, okay, these characters are equal, then we have to add 1 to this particular element. So S of 0, 0, 0, 0 means this one. So diagonal. Okay, we have to add to the diagonal. For example, if it is not equal, then what we have to do? So we have to go with this one. So LCS of, maximum of, if both are not equal, for example, let us take S of 2 and S of 2. Consider this one. Okay, now what happens? We need to take maximum of LCS of I minus 1, 2 minus 1, 1, j, 2, or LCS of I, 2, j minus 1, 1. So we need to consider 1, 2 and 2, 1. So 1, 2 and 2, 1. So we are checking about this particular cell, and if both the elements are not equal, okay, if both the elements are not equal, so for example, consider this one, S1 is equal to S2, okay. So if both the elements are not equal, then we have to check the maximum of either previous row or previous column. So the same thing, see, 1, 2, 2, 1. So 1, 2 means this one, 2, 1 means this one. So we need to remember these two formula, and we have to fill out all the table. So just for reference, I have written the indexes. Okay, so usually we should not write the indexes. We have to fix the values. So all positions initially 0. So that's why we have added a first row and first column with zeros. Okay, now we have to traverse. So how? See, A and B. Okay, A and B. Here I'll write the strings one. so that we can erase the portion. So string 2 is B, D, C, A and B. So I'll erase this one so that there will be no confusion, and we can simply use the word, right? So string 2, see, this one is string 2 and we are representing it as J. Okay, so now we can observe A and B. Okay, we are comparing the elements A and B. So that is nothing but S of I comma is equal to S of J. So A, B, both are equal or unequal? Obviously these two are unequal. So if these two are unequal, what we have to do? So we have to add one, sorry, if both are not equal, then we have to do maximum of LCS of I minus 1 J, I and J minus 1. So obviously we have to select either portions. Okay, either portions. So either portions means we have to select the maximum of either this portion or this portion. So diagonal. So both are equal. Okay, both are equal. What we have to do? So we can take any of these things. So let us take this one and let us assume we have taken from this particular cell. Okay, we have taken this particular cell. So give an arrow mark through which direction, through which cell we have taken. And next, A and D. A and D, compare A and D. Here also not equal. Then we have to apply the second formula so that these two positions will get. So among these two, which is the maximum? Both are equal. So you can select either. So I will select from this cell itself. Again, I am selecting only this one. So I am writing this arrow mark. Else, if you consider here, from here, you have to write the arrow mark in this way, because we are considering this 0 from this particular cell. Okay. So anything we can do, no problem. So I will select from here. And A and C, again both are not equal. So then again compare and select the either. So again I will take 0 and both are equal from this cell. Now A and A both are equal. So if both are equal, we have to add to S of I minus 1 J minus 1. So what we have to add from here, diagonally we have add. So here 0, it becomes 1 and the arrow mark should be in a diagonal position. Okay. So 1, and in this way we have taken 1. Now A and B both are not equal. So we have to compare and we have to take the maximum of diagonal. So here we are having 1, here we are having 0. So a maximum of 1 comma 0. So obviously we have to consider 1. So I consider 1 and that is from this cell. Okay. So hope you understood. Very simple. So just applying these two formulas. Now coming to this one, B and B both are equal. So in the diagonal, so we have to add 1 to I minus 1 J minus 1. So this one. So this becomes 1 and we have taken this from diagonally. And next, B and D both are unequal. So if it is unequal, we have to consider a maximum among these two cells, I minus 1 J, I J minus 1. So these two cells. So it is 1 and I have taken from this cell. Okay. Coming to B and C, both are unequal. Again, in the diagonal 0 and 1, we have to consider 1 and I have taken from this cell. And again B and J, both are unequal. So diagonally here we are having 1 and here we are having a 1. So both are equal, we can consider anything, right? So I will consider here 1 and I will consider from this cell itself. You can also consider, you just try at home by considering this one. Okay, no problem. Now B and B, so both are equal. Then we have to add 1 to the I minus 1 and J minus 1. So here 1 it is there, now it becomes 2 and I have taken from this particular diagonal position. Next, C, B both are not equal, so I have to consider either from 0 or 1. So diagonal, we have to consider the maximum, and 1 is the maximum. I'll take 1, and from this cell, so arrow mark will be towards upward. So C and D both are unequal, both are 1s, so same thing, and we can consider any value, right? Any cell. Next, C and C both are equal. Now we have to update, that means we have to increment by 1 of this particular diagonal element. So it becomes 2, and here we have considered like this. Okay, next, C and A both are unequal. So 1 and 2 are there diagonally. So we can consider the maximum. So I'll consider 2, and this is from this cell. And C and B both are unequal. So here in the diagonal both are having the same value. So you can consider anything and use an arrow mark. Now B and B both are equal. So increment the diagonal element 0. So 0 will become 1, and arrow mark will be like this. And B and D both are unequal, right? B and D both are unequal. So among these diagonal we have to consider 1, and I am considering from this cell. And B and C both are unequal. So 1 and 2 are the diagonal elements. So 2 will be the maximum. I am considering this way. And B and A both are unequal. So both are unequal means again we have to consider the maximum among the diagonal 2 and 2. So both are equal. So I will consider the same thing. So I will consider from this one. Okay. So B and B both are equal. So increment the diagonal element. So 2, and it will be 3, and in the diagonal. So now we have filled the complete table based upon, with the help of these two formulae. Okay, if both the elements are equal, then increment the diagonal element with 1. And if both the elements are not equal, so select the maximum value among the just previous row or a previous column. So now what is the maximum value? 3. And starting from 3, follow the arrow marks. If there is a diagonal, write down the element there. If it is a diagonal, write down the element. So important, right? Point. If there is only a diagonal, then only we have to write down the element. And that element should be written from right to left. So here we are having a diagonal, right? So this 3 we got from this particular cell. Okay, this 3 we got from this particular cell. So what we have to do? We have to select the element B. Okay, now we are at 2. There is no diagonal, so we should not consider it. So from 2, the arrow mark is this one. That means we got 2 from this particular cell. So consider now this cell. Okay, this cell. So here we are having a diagonal. So we got this 2 from this particular diagonal element. So what is the value? C. So write down here C. Now we are at this position. Here the arrow mark is not diagonal. So we got this value from this particular cell. So moving towards this one. Right? So here again we are having some diagonal. That means we got this with this one. Okay, B. So write down here B. Now we are at this position, and here the weight is 0. So the longest common sequence is BCB. Just now we have seen the longest common subsequence. So just following the same way. Okay, right? So in this way we can solve the longest common subsequence. So just we have to iterate both the I value and J value. Right? So this is also a recursive function. From the previous cell we are using the value. So we are updating 2 from this particular cell. That means the result of this cell is already been saved. And from here we are updating here. And from this cell we are updating into 3. Alright? So hope you understood this one. So the longest common subsequence among these two strings. Longest common subsequence is CBCB among these two substrings. among these two substrings, it is BCB. Okay, so you can consider any two substrings and try out this particular method, so that definitely you will get the longest common subsequence, and we can get a multiple long common subsequences also. Okay, if it is having a multiple paths, automatically we can get a multiple common subsequences. So today we will see one more example on longest common subsequence problem using dynamic programming. So we usually call it as LCS problem. So which is the longest common subsequence, right? So first we need to take two different strings and we need to find what are the common subsequences. Okay, so in our previous session we have discussed about this one. So the difference between subsequence and the substring. So coming to the subsequence, the order of elements can be any, we have to follow the order of the elements, not the consecutive elements. Okay, so that we have seen in our previous session. I'll post the link in the description box. Please follow that and then you can listen. So we have taken two different formulas in order to fill the 2 by 2 matrix. Okay, see, let us take the strings. Consider str1, a string as AB, C, B, D and AB. And coming to the string 2, BD, CA, BA. Okay, so these are the two different strings. Now we have to find out the longest subsequence among these two strings. First we have to draw the horizontal and the vertical lines. I'll write here A, B, C, B, D, A and B, and here I'll write so initially take it as zeros, consider initial values as zeros. Right? So in the vertical we can write it as B, D, C, A, B and A. Consider the boxes. We need to fill all these columns, and these columns should be filled with the help of two formula. So here also initially we are taking it as zeros, initial. Okay. So we have taken the complete cells, and now we need to fill all the cells by using two formula. The first one, if xi is equal to xj, if both are equal, then the cell value will be, okay, we can write it as cell of I j will be 1 plus cell of I minus 1 and j minus 1. So we need to add one element, 1 to the cost of I minus 1 and j minus 1. And the second one, if I not equal to j and both the elements are not equal, then the cell cost of ij will be a maximum of cost of I minus 1 j or C of I and j minus 1. Among these two we have to select the maximum. Okay, select this one. B and A, right? So let us consider this as x and this one as y. So xi, xj, sorry, I think is y, and here also y. Right, A and B both are compared, and we know that both are not equal. So we need to consider a maximum of I minus 1j and j minus 1. So we have to consider I minus 1j. So let it be I and let it be j. I minus 1 means this one. J minus j means this one. And I minus 1j or I j minus 1. So both the cells are this one, diagonal cells. So here we are having the same number. So what we have to do? We can take any value. So I will consider this one and just place the array from which cell we are taking this. I am taking this from this array, from this cell. Now B is compared with B. Both are equal. Then we have to add 1 to the cost of I minus 1, j minus 1. I minus 1, j minus 1 means this one. Okay, this diagonal. So we need to add 1 to this particular diagonal. So 0. So now it will be 1 and we have taken it from diagonal position. Okay. Now B and C both are not equal. Among these two, which one is the max? 1. So I will take 1 and we have taken this from this particular cell. And again B and B both are equal. So we need to add this one. 1 and we got this from the diagonal. And B and D both are unequal. So we need to consider a maximum from either this cell or this cell. So 1 is a maximum and we have taken this from this cell. And B and A both are not equal. So we have to select maximum among these two cells. I will consider this one because 1 is a maximum among 0 and 1 and we have taken from this cell. Now again B and B. So we have to add 1 to I minus 1, j minus 1. So this one is I minus 1, j minus 1. So obviously it will be 1 and we have taken from diagonal position. Now coming to the second one, DA both are not equal. So what we have to do? So we have to consider the maximum among this one and this one. So both are equal. I am taking here and I am taking from this cell. D and B both are unequal. So from these two diagonal positions we have to consider a maximum. 1 is a maximum. I am taking 1 and we have taken it from top cell. Okay, so put the arrow mark towards the upward. Next, D and C both are unequal. We need to consider a maximum among these two diagonals. So both are 1s. So obviously the result will be 1 and we can consider it from any cell. You can write the leftward arrow or upward arrow. Next, D and B both are unequal. Again we got 1. So I will take 1 from this particular cell. D and D equal. So we have to add 1 to C I minus 1, j minus 1, which is this one. So 1 plus 1 it becomes 2 and we got 2 from this here. So D and A both are unequal. Among these 1 and 2 we have to consider a maximum. I will consider a maximum as 2. We got this from this cell. D and B both are unequal. Again 1 and 2 are there. Diagonally we need to take maximum. I will take a maximum and I am taking from this particular cell. Now C and A both are unequal. So if both are unequal, we have to consider a maximum among diagonal. Both are zeros. Again I will consider 0. I consider from this cell. Or okay, you can also consider from this particular cell. No problem. C and B both are unequal. 0 and 1 diagonally we are having two values. Among these two we have to select the maximum. So I am considering 1 and we have considered from this particular cell. C and C both are equal. So we need to add 1 to I minus 1, j minus 1, which is this cell. So 1 plus 1 it becomes 2. We got 2 from this particular cell. And C and B both are unequal. And 1 and 2 we need to choose a maximum among this 1 and 2. So 2 is a maximum and we got this from this particular cell. And C and D both are unequal. among the diagonal we have to select the maximum. So both are equal. So we can select 2 either from this side or this side. I'll consider this side. No problem. Anything. And C and A. So C and A both are unequal. We are having a diagonally 2 and 2. So we can consider 2 and we can select either. C and B both are unequal, 2 and 2. I'll consider 2 and let us consider upwards. No problem. And A and A both are equal. So we need to add 1 to Ci minus 1, J minus 1, which is this cell. So here it is 0. Now it becomes 1 and we got 1 from this cell. And A and B both are unequal. So we need to select a maximum among diagonal 1 and 1. So both are equal. So we can consider any cell. So A and C both are unequal. 1 and 2 are diagonals. We need to select a maximum among these 1 and 2. So I will select 2 and this comes from upward cell. And next A and B both are unequal. Again we are having a 2 and 2. We can select any, both are equal. We can select any number. Okay, I mean the number from any cell. So I will consider from this one. Next A and D both are unequal. Again diagonally we are having 2 and 2. So from this we got a 2 and I will consider from this cell. A and A both are equal. So we need to add 1 to the I minus 1, J minus 1, that is a diagonal here. So 2. So 2 becomes here 3. We got 3 from this particular cell. And next A and B both are unequal. Among these diagonal 2 and 3 we have to consider a maximum. So I am considering 3 and that we got from left side cell. And B and A both are unequal. So 0 and 1 we have to consider maximum. I consider maximum and we got this one from upward cell. B and B both are equal. We need to add 1 to diagonal. So here it is 1. So after adding 1 it becomes 2. So we got 2 from this particular cell. And B and C both are unequal and diagonally we are having a 2 and 2. So both are same. We can consider it as a 2 and we can consider any cell. And B and B both are equal. So obviously this diagonal position we need to add 1. So 2 becomes 3 and here from this cell we have considered the 2. Next B and D both are unequal. So here diagonally 2 and 3 are there. Among 2 and 3 we got only 3. So we have to consider a 3 which is selected from left cell. B and D both are unequal. B and A both are unequal. Here diagonally we are having the same number 3 and 3. So we can select any number from any cell. I consider this one. And B and B both are equal. Diagonally it was 4. So we have to write it as a 4 and we got it from diagonal. Next A and A both are equal. Diagonally 0. It becomes 1. So from here we got it 1. Next A and B both are unequal. So among 1 and 2 we need to take the maximum. So 2 is a maximum. I am considering 2 with this particular element. So A and C both are unequal. Diagonally we are having the same element. So we can take the same element from either cell, either left cell or up cell. And A to B both are unequal. Again we are having 2 and 3. Among 2 and 3, 3 is a maximum selected from up cell. A and D both are unequal. We are having a diagonally both are equal 3 and 3. So obviously we can consider 3 and we can select any cell. A and A both are equal. So if both are equal, what happens? Diagonally 1 should be added to I minus 1, J minus 1. This is I minus 1, J minus 1. 1 should be added to 3. So it becomes 4, which is a diagonal position. And again A and B both are unequal. So we need to select a maximum among these two diagonals. So same value which we are taking from 4. Wait. See, here we need to select the last one. A and B both are not equal. Okay, A and B both are not equal. So we need to select either this cell or this cell, because here we are having a both 4, right? So we need to select the maximum, and here we are having the same number. So we can select the 4 and either from left cell or up cell, you can select anything. So if you consider the left cell, so in such a situation, you can get a more than one longest common subsequence. Okay, we are having two paths. Either we can go with the left cell or you can go with the up cell. So first case, if you are selecting this particular cell, that means the left cell, what is the longest subsequence you can see? So left cell, if you consider a left cell, okay, so what happens? So from here we need to start traveling. So this one and this 4 comes from this cell. So here we got a change, so which is A. Okay, now we are at 3. This cell comes from here 3 and again diagonal. So this cell comes from C. So here there is a change. So B, and writing everything from right to left. Okay. So we are at 2. Now we have considered it as 2. Okay. And here this cell we got from this particular cell. So there is a change. So that is C. 1. So this we have considered 1. So here this cell we had got from A. It was updated. That means a change. So we have to consider this as B. Okay, the left cell. This is the longest common subsequence among these two strings. You can see B, C, B, A. So the same order it was following from string 1 and string 2. In both the strings, the same order. So B followed by C, followed by B, followed by A. Here also B followed by C, followed by B, followed by A. So we are not considering the substring, we are considering the subsequence. So whether it is following the same sequence or not. Right? Next, so if you consider it as an upcell, so if you consider it as an upward cell, if the last cell was taken from upward, so if the arrow mark is from this side, we can check. So this cell we got from this one and here it is changed from the A. So what is this one? B. Now we are at A. So the direction, just follow the direction. And we got a 3 updated from D. So here we have to select A. Okay. Next, this one we got from this cell. So which was not updated. Again, this was appeared from this particular cell which was updated, right? So now it is C. Now we move to 1 and this cell we got from above cell, right? Here we got. Here there is a change. It was updated from A to B, right? So we need to consider B. Now we are at A, which is 0. So this is also the longest common subsequence. How we can check? We can check. So check the same thing in the strings. First B, yes, followed by C, yes, followed by A, yes, followed by B, yes. So the order is same here also. Here also the order is same. So B followed by C, C followed by A followed by B. So both are the longest common subsequences. So this is an example where we can get multiple subsequences. Okay, it's not limited to only one subsequence. So we can get maximum subsequences with a number of elements. So if it is a longest subsequence, 4 elements subsequence, we are getting a 2 answers, so 2 solutions. Okay, so hope you understood. So first we need to draw the table and initialize it with the zeros for first row and first column, and then use these 2 formulae to fill each and every cell and use the arrow marks in order to travel from bottom to top. Here also we need to write the solution from right to left. Write down the elements from right to left. So BCBA is one solution, BCAB is another solution for these two strings. So there will be a more number of subsequences, but this is the longest common subsequence. Longest common subsequence. We'll see one more problem in algorithms concept, that is multi-stage graphs problem. Multi-stage graphs. So here the name itself indicates the multi-stage graph, means here this is a graph problem. It is a graph problem. And what is this problem? And here we need to find the shortest path from source to destination. So already we have solved the similar problem by using a different methodology, by using the greedy methods. But here we are supposed to solve this one by using the dynamic programming, right? So finding shortest path from source to destination. Source to destination. So here we are having a few constraints. In order to find the shortest path, we are supposed to have some constraints. So that is, we need to use the weighted and directed graph. So only we have to take the weighted and directed graph. And here the vertices will be divided into different stages. Okay, so some sort of partitions, right? So vertices were divided into partitions called stages. So each stage will be having a subset of vertices, and so the direction should be only one word, right? So if the direction is from current vertex to the next vertex, so there should not be an edge between next vertex to the current vertex. So I'll show you the example so that you can understand. So if the graph is like this, so if A, B, and let us take this C, D, okay. So these are our different vertices, okay. If there is an edges like this, okay, so this is one partition, this is another partition. So here we can say K1 is a stage, K2 is another stage, and K3 is another stage. So in this stage K1 we are having one vertex, in K2 we are having two vertices, in K3 we are having one vertex, and there should not be direction in this way. So in this example you can see the direction is towards the destination, right? A to B or A to C, and B to D or C to D, and the direction should not be like this. So one is towards destination and another one is towards the source. So this type of graph is not applicable, right? So the direction should be towards the destination only. For example, let us take this as a source, right? And this as a destination. Then the direction should be towards the only destination, not towards the source. And also every edge should have a weight. For example, the weight is 5, 2, 3 and 6. So you can call them as a weight or a cost or a distance, anything, right? Weight, cost or a distance. So there should be this one. So such type of graph we can call it as a weighted directed graph. So here we are having the directions and also weight for each and every edge. So this will be the weighted and directed graph. So in order to solve this graph problem, multi-stage graph problem, so the graph should be weighted and directed, and the partitions, the complete vertex should be in partitions called as stages, and the direction should always to be towards the destination, right? Then we can solve this by using the dynamic programming, and such type of problems can be solved by using two approaches. One is forward approach, another one is backward approach. backward approach. So if you are using this forward approach, we are supposed to select the destination first and we need to solve the problem. So that we call it as a forward approach. Don't get confused. In the forward approach, we are supposed to start our process from the destination itself. And if it is a backward, we have to start from the source itself. Okay. Now in this session, we will see the forward approach of solving this multi-stage graph problem. So let us take an example and we'll solve this multi-stage graph problem using dynamic programming using this forward approach. So come up with an example. See, let us solve this example. So this is a weighted and directed graph. You can see the directions, and also for every edge we are having some weight or cost or distance, right? And also all the directions are towards the destination. For example, consider this as a source and this one as a destination. This one as a destination. Alright. Now we need to find the shortest path from source to destination. Right. So based upon the edges. So we can start from source and we can reach the destination in different paths. We can go with A to B, B to F, F to H, or A to B, B to E, E to H. See, A to B, B to E, and E to H. A to C, C to F, F to H. A to D, D to G, G to H. Similarly, A to C, C to E, E to H. So like this, we will be having a lot of solutions, lot of possible paths, right? But we are supposed to select the path with an optimized route. That means the weight, the cost should be a minimum. That means that's we call it as a shortest path. So such type of problems we can say them as a optimization problems. So where the problem is having a lot of solutions and we have to select a solution based upon the constraint. So here also the constraint is shortest distance, shortest path, right? Now let us check here how many stages we are having. Let us assume this is a stage 1 and this is stage 2, this is a stage 3 and this one is a stage 4, right? Let us assume K as a stages. So there are 4 stages. So K1 is having only one vertex, K2 is having 3 vertices, K3 is having 3 vertices, and K4 is having only one vertex. So we need to start from the destination if you are going with the forward approach. So let us go with the K4, right? So we can call it as a cost of K4 comma, what is a vertex H. We need to find out the cost for K4 to H. So where the formula will be the distance of H to H. So which we can call it as a cost. Okay, cost of H and H. So the destination and source are both are equal, then obviously the weight is 0, right? If the source and destination both are equal, then we can say the weight is 0. So it will be 0. Now, any other vertex available in K4? No. Now we can move with the K3. So K3, the cost of K3 comma, let us find out for E. Okay, then what is this one? So cost of E to destination, right? So E to destination, what is the cost of E to destination here? The distance from E comma H plus cost of H comma H. So here we are having the destination, so E to H and H to H. For example, if it is B, we need to find out the B to E plus the cost of E and H. Okay, hope you understood. So we need to find out the distance from B to H, then obviously we can say the distance of B to E and from E to H. So similarly, if we are finding out the cost E comma H, then the distance of E to H and the cost of H and H. If we are having a multiple paths, we need to find out the minimum. So what is the value here? So DE comma H 18 plus, we need not find out the value once again because already we have calculated here. So that is an advantage of dynamic programming. So we are supposed to solve the problems and save the solution in order to avoid the calculation. Once again calculating the same problem. So here cost of H is 0, which is 18. So is there any vertex in K3? Yes, F is there. So once again cost of K3 comma F. So which means cost of F to destination is equal to the distance from F to H plus a cost of H to H. So what is the distance of F to H? 13 plus cost of H to H. It's 0, which is 13. Next, again we need to find out the cost of K3 comma, there is one more vertex G. So cost of G to H, which we can say the distance of G comma H plus cost of H to H. So what is the value of this one? D distance of G to H. G to H, it is 2 plus 0, which is equal to 2. So we have completed the K3. Now we need to move with K2. So K2 edges are DCB. Now let us find out the cost of K2 comma B. Right? Now we need to find out the cost of B to H. So we need to find out the B to H, the cost of B to H. Now you can see, now you can understand why we are writing here this one. So B to H means, so there are different possibilities. So B to E, E to H, B to F, F to H, right? B to E, E to H, B to F, F to H. So there are multiple possibilities. Here we need to find out the minimum. So minimum of distance of BE, distance of B comma E plus, now we are at E, so we need to find out the cost of E comma H. So cost of E comma H, which was already found here, see, right? Similarly, I'll write here D of C comma E, sorry, B comma F, because from B we can reach H through E or through F, okay, two paths. So we need to find out the minimum plus the cost of F comma H. That is also we have found F comma H, right? Now calculate DBE. DBE means 4 plus cost of EH, we have find out 18. So which gives it 22. And next possibility BF, B to F, it is 11 plus cost of F comma H, which is at 13. So which is 24. So we need to consider the lowest, so the minimum. Next, there is one more edge, one more vertex in K2. Now we need to find the cost of K2 comma C. That means cost of C to H. What is the cost from edge vertex C to vertex H? So that we can also have a minimum because we are having multiple paths, C to E, C to F, C to G. 3 possible paths are there, right? So minimum of D of C to E plus cost of E to H. Similarly, D of C to F plus cost of F2H. Similarly, D of C2G plus cost of G2H. See, there are three outgoing edges. So we can reach H from C via E or F or G. So three possibilities. So we need to find out the distance of C to E and cost of E and H. Distance of D to C and F and cost of F and H. Distance of C and G and cost of G and H. So what's the value here? What's the value? D of CE. CE is 9 plus E and H. So what's the E and H? Cost of E and H already we have find out, right? So here 18. We have calculated, so 18, which is 27. And here C and F, it's a 5 plus cost of FH, already calculated, cost of FH, which is 13. Next, D of CG, it's 16 plus cost of GH, it's 2. So how much? This is 27, 9 plus 18, which is 27, 5 plus 13, which is 18, 16 plus 2, which is again 18. So we can consider two possibilities. One is reaching H through F or reaching H through G. Both are equal cost. Right. Leave it. Now, is there any vertex in K2, stage 2? Yes, there is a edge, there is a vertex of D. So again, find out the cost of K2 comma D, which is nothing but cost of D to H. So here, whether it is required to find the minimum value. Whether it is required to find the minimum value? No, because only one path is there from D to H. There is no outgoing edge, only one edge is there. So we can write it as D of D to G plus cost of G to H, which gives D to G, it is 2 plus cost of G to H, again it's 2. So 2 plus 2, which is a 4, right? So is there any vertex in stage 2? B, C, D. We have calculated B, C, D. All possibilities. So there is no vertex in stage 2. Now go with the stage 1, which is a source. Then K1, the cost of K1 comma A, which is cost of A to H. A to H. How many edges are there? 3 edges are there. So we have to find out the minimum among these 3. So minimum of distance of A to B plus cost of B to H. So we need not find again B to E and E to H. Already we have calculated everything. So A to B and cost of B to H. And see again D of A to C plus cost of C to H. Again D of A to D plus cost of D to H. So among these things we have to find out the minimum. Now find out D of A comma B. What is the distance of AB? 1 plus cost of BH. Already we have calculated somewhere. BH, cost of BH. See, cost of BH, this one. So among these two we have considered minimum. So 22, we need to consider the 22, which is the 23 cost. Now D of AC. AC is 2 plus cost of CH. So here we have calculated cost of CH. So 18, we can consider anything, right? Either, because both are equal. So I am considering 18, which is 20. Next, D of A to D, it is 5 plus cost of DH. What's a DH? Once again here, B to H, C to H, and D to H is 4. So it is 4, which is a 9. Right? So among these three, what is the minimum? This is the minimum. This is the minimum. So we can consider 9. And this is the first stage. So that means a source. So in order to find the path from source to destination, the minimum path is a 9. Right? So we have to find out the path. So 9 means A to D. Okay. So first A to D, then cost of DH. Go to the cost of DH. Where is the DH? This one. So here DH, it is G, D to G. So after D we have to visit a G, and then cost of GH. What's the GH here? GH. So from G we can go with the H. From G we can go with the H. So among all the different paths, this one is the shortest path. You can observe A to D, D to G, G to H, which is 5 plus 2, which is 9. So if you go with A to C, C to F, F and F to H, 2 plus 5, 7, 7 plus 13, 20 it will take. And if you go with A to B, B to E, E to H, 1 plus 4, 5 plus 18, 23 it will take, right? So this is the only path which is having the shortest distance. So in order to reach from source to destination, the shortest path is A to D, D to G, and G to H. Right? So here what we have to do is we have to start with the destination, and from the destination try to find out the cost from each and every stage towards the destination. So here the cost of fourth stage, which is a destination to destination, the cost will be 0. So only one node is there, right? So once again, one more constraint is here in this problem, the graph should contain only one source and one destination. And coming to the third stage, from the third stage we are having 3 nodes, and from the 3 nodes we have to find out the cost from each node to the destination, so E to H. If there are multiple paths, we need to find out the minimum. We need to consider the minimum. So how we can use? We have to find out the distance from E to H and a cost from H to H. So here you can find out, here you can understand, if you are finding the distance cost of B to H, what we are doing, we are finding the distance of B to E plus the cost from E to H. So obviously we have calculated the cost of E and H, the same value we are using here. So in the dynamic programming, the complete problem will be solved into, divided into sub-problems. Those are the overlapping sub-problems, and each sub-problem will be solved and the solution will be stored in the memory, so that in further we can make use of that particular solution in order to get the final solution, optimal solution. So the same thing happens here. For every situation we are saving the solution. So the same solution we are using in our next recursions. So today we'll see one more example in multi-stage graph problem. So in our previous session we have seen this multi-stage graph problem. So where we have to consider the weighted directed graph. So all the vertices will be arranged in stages, in terms of stages, and the problem is to find the shortest path from source to destination. So using this dynamic programming. So in our previous session we have seen one example following the forward approach, and here also we will see the same forward approach. And here we are having a different stages. So this is 1, this is 2, this is 3, this one is a 4, and this one is a 5. So total 5 stages. So in our previous session we have seen about the 4 stages. Now we will see the 5 stages. So first we have to start with the destination, right? We have to start with the destination, and we need to find the minimum path in each and every stage. So here you can see every stage is having a different number of vertices. For example, in the first stage we are having only one vertex, that is a source, and in K5, that means the fifth stage, one vertex, it is a destination. And similarly in the stage 2, we are having a two different vertices. Stage 3, three vertices. Stage 4, again we are having two vertices, right? And you can see B, we are having a two possible paths. C, we are having a three possible paths. So among these we have to find out the minimum, right? So first we need to start with last vertex, that means a destination, right? So now I will go with the K is equal to 5. K is equal to 5. How many vertices are there? We are having only one vertex, that is I. Okay, we need to find out the cost of I. So cost of I comma destination I, which is nothing but distance of I and I, so which is equal to 0. So the distance from the same vertex, if the source and destination are the same vertex, obviously it will be 0. Now any other vertex in stage 5? No, right? Now we have to find out the vertices, the cost in the stage 4. So stage 4 we are having two vertices. How many vertices? Two vertices, G and H. So we need to find the cost of G to I. G to I. Okay, cost of G to I, which gives the distance of G comma I plus cost of I and I. Okay, so which is equal to distance of G and I, it is 7 plus 0, which is equal to 7. Similarly, we need to find out the cost. Any other outgoing from G? No, leave it. So cost of H and I, so which gives the distance of H comma I plus cost of I comma I. That means the next vertex to destination. Okay, here the same vertex will be the destination, so we are getting 0. So H and I, which is 3 plus 0, which is equal to 3. So any other vertex in stage 4? No, we have covered both J and H. Now go with the next stage. K is equal to 3, which is having three vertices, D, E, F. So D, E, F. So we need to find the distance from the cost from D to I, E to I, F to I. So first the cost of D to I, which will be from D of distance of D comma the next vertex, that is G, plus cost of G to I. Okay, so this portion we have already calculated in our previous stage, G to I, right? So directly we can use it instead of recalculating, right? That's what the advantage of dynamic programming. So the problem will be divided into sub-problems where each and every sub-problem will be calculated or solved, and the result will be stored in the memory, and it can be retrieved whenever it requires. So the same thing happens here. So here the cost of D to C. First let us check whether there are any other edges from D to G. How many possibilities from D to G? Sorry, D to I, right? So there are two possibilities from D to I, right? D to I. How many possibilities? We can go with D to G, G to I, D to H and H to I. So two possibilities. Among these two, we have to find out the minimum. So the same thing happens. So I am finding the minimum value here. So D of distance of D comma H plus cost of H comma I. So we need to find out the minimum value of these two. So distance from D to G, which is 1, plus cost of Gi already calculated 7, so which will be 8. So here you can see the distance from the cost from D to I, the cost from D to I via G is 1 plus 7, it is 8. And here D to H plus cost of, so D to H is 4 plus cost of HI, already we have computed here, right? So 3, which is 7. Which one we have to consider? Obviously 7, because among these two we are having a minimum. So this path we are getting 8 and this path we are getting 7. So our solution is to find the shortest path from source to destination. So that's why we need to always find the minimum value, right? So next, E, we need to find the E. So cost of E to I, that means E to destination, E to destination. So how many paths are there? Let us check here. E to destination, that means I. So one possibility, E to G, G to I, E to H, H to I. So two possibilities, right? So let us check minimum. We need to find out the minimum. So D of E comma G plus cost of G comma I. Similarly, D of E comma H plus cost of H comma I. So we need to find out the minimum among these two. Distance of E and G, E to G, it is 6 plus cost of GI, already it was pre-computed. So GI, it is 7. So which gives a 13 as a distance. Distance of EH, E to H, it is 2 plus cost of HI, cost of HI, it is 3. So it's equal to 5. So we got the path, this path, through this path we got a distance 13, through this path we got a distance of 5. So which one we have to select it? So 5 should be selected, right, among these two. So still any other vertex in this particular stage? Yes, F. So we need to find the F also. Cost F to I. Let us check how many edges are there from F. So F to I, how many paths? You can check. F to G, G to I. Similarly, F to H, H to I. Two paths are there. You can observe. F to G, F to H. So same D of F to G plus cost of G to destination. Similarly, D of F to H, F to H plus cost of H to destination. So we need to find out the minimum among these two. What is the distance of F and G? F and G, it is 6 plus cost of G and I, which is 7. Again we got 13 as a result. Okay, then D of F to H, it is 2 plus cost of H I. So here we have computed, it is 3. So which gives a 5 as a result. So among these two, here we got a 13 and here we got a 5. Again we have to select this 5, right? Yes. So any other vertex in stage 3? You can observe in the stage 3, D, E, F. Already we have computed D to destination, E to destination, F to destination. Now we need to find out the cost from stage 2 vertices. So K is equal to 2, which is having the vertices B and C. B and C, right? Now, what we have to find? We have to find from B to I, so which is a cost of B to I. So let us check the possibilities from B to I. That means how many outgoing edges. So B to I, how many outgoing edges? So B to D, and similarly B to F. Two edges are there, and D towards I, F towards I. Two possible paths. So here also we have to consider a minimum. So D of B to D plus cost of D to I. Similarly, D of B to F plus cost of F to I. So you can see already, so B to D, what is the distance from B to D? B to D, I think it was 2. Let us assume it as 2. So B to D, let us take it as 2 plus cost of D to I. So what is the cost of D to I? Already we have computed. So here we got 8 and 7, and we need to consider the minimum. So 7 is the final value. So it is 9. D of B to F, B to F it is 3 plus cost of F to I, here F to I. So 13 and 15, among these two we have to select the minimum, so it is a 5, so which is 8. So we need to consider the minimum value 8. And any other vertex in the stage 2? Yes, C. Now find out the cost from C to I. Okay, C to I. So D of, so C to I, any other possibilities you can check. So C to D and D to I, C to E and E to I, C to F and F to I. So there are 3 possibilities here. So we need to check all those things. So C to D plus cost of D to I. Similarly, D of C to E plus cost of E to I. Similarly, D of C to F plus cost of F to I. So among these things we have to consider the minimum. Let us check the distance or the cost. So D of CD, D of CD, C to D it is 6 plus DI. What is a DI? So here 7 which is a 13. D of CE, C to E it is a 5 plus EI which is again 5 which gives a 10, and D of CF, C to F it is 8 plus cost of FI again it is 5, so which is a 13. So among these 3 which one is a minimum? Obviously 10 is a minimum. So we got 13, here it is 10 and here it is 13, so 10 is the minimum. So we are considering the 10 as a value. Now any other vertex in the stage 2, we have computed the distance or the cost from B to destination and C to destination, which are the 2 vertices available in the stage 2. So completed. Now come with the stage 1. So stage 1. So stage 1 we are having only one vertex, that is A, which is a source. We need to find the cost of A to I. So which gives the distance. So here you can see A to I. What are the outgoing edges from A to B and A to C. So we can go with A to B and followed by AI, A to C and followed by I. So 2 possible paths are there. Let us check. So cost of, so here the distance of A to B plus cost of B to I, and similarly D of A to C plus cost of C to I. So among these 2 we have to select the minimum. So I am writing here minimum. So we need to select only the minimum value. So here also it is a minimum value. Now D of AB is 5 plus cost of BI. So here we have computed BI, right? So here 8, we got a minimum value 8, 5 plus 8 which is 13, and D of AC is 2 plus cost of CI. So among these 2 we got 10, so which is 12. Among these 2 which one is the minimum? 12 is the minimum. So here A is a source and I is the destination. So in order to travel from source to destination, the minimum distance or the minimum cost is 12. So now we have to backtrack to find out the path. Okay, find out the path. So this is the last stage. A is a source, last stage. So we need to stop the calculation, and here we are considering that the AC plus cost of CI. So we need to consider the edge from A to C first. A to C, and then cost of CI. Go to the cost of CI. So in that we are having a 3 possible paths. Among these 3 possible paths, which one we are selecting the minimum? That is this one, C to E. So the next vertex is E. And cost of EI. So cost of EI, again go with this one, cost of EI. Here we are having a 2 possible paths. Among these 2 we are selecting this one because of minimum cost. E to H. So E to H. and cost of hi. Cost of hi, go to here. So it is hi, which is the destination, this one. So this gives the optimal result. That means the shortest path from source to destination. Find out the values or weights here. A to C, which is a 2. C to E, which is a 5. E to H, which is again 2. And H to I, which is again 3. Which gives the total cost of 2 plus 5, 7 plus 2, 9 plus 3, 12. This is the minimum cost to find a path from source to destination. So here A is a source, I is the destination. So this is the forward approach where we are considering from the destination itself. So first we need to consider the destination. From that we have to go with the source, towards the source, right? So we need to compute all possible paths in all different stages. So here stage 5, only one vertex, that is the destination. In stage 4 we are having a 2 vertices G and H. In stage 3 we are having a 3 vertices D, E, F. And in the stage 2 we are having 2 vertices B and C. And in the stage 1 only one vertex, which is a source, right? So here we are computing and we are making use of the same result in our next problems. So coming to the stage 3, we are not computing about cost between G and I. So we are considering the value of G and I from the previous result. From here we are considering. So here we are not computing the cost of D and I because we have already computed this cost of D and I in the previous result. So the problem is solved, and divided into sub-problems, and again the sub-problems have been solved and the results have been saved in the memory, and we can retrieve that results whenever it is required in order to avoid the recomputing the values. So this is called the dynamic programming. So this is the multi-stage graph using dynamic programming. So today we will see one more approach to solve the multi-stage graph problem. So the multi-stage graph problem means finding the shortest path from source to destination, right? So in our previous session we have seen one approach, that is a forward approach. Now we will see the backward approach in order to solve this multi-stage graph problem. Multi-stage graph, and this is a backward approach. So in our forward approach we have started from the destination and we have traveled through the source, and now quite opposite, we have to start from the source and we need to travel through the destination, right? So here there are a lot of stages. We can see it is 1, second stage, third stage and fourth stage. So usually we are representing a stage with a K. So K1 is the first stage where we are having only one vertex A, and K2 is a stage which is having 3 vertices B, C and D. K3 is another stage which is having 3 more vertices E, F and G. Now H is a fourth stage, only one vertex, that is a destination. Starting from 1. So in our forward approach we have started from the destination itself. Now we have to start with the source, and the formula is same. We need to find the cost of source to destination. So here K is equal to 1, which is having only one vertex. So we need to find out cost of A to A, source to destination. So here source and destination both are equal. Obviously that will be the distance between A to A, which is equal to 0, because we are at source and we are at destination. So the distance between source and destination is 0 because both are same, right? Now there are only one vertex in stage 1 because it is a source. So completed. Now go with the second stage where we are having 3 vertices B, C and D. So we need to find out cost of source to B, cost of source to C and cost of source to D. So one thing we have to remember, how many incoming edges for B, C and D, because we are traveling from source to B. So if B is having two edges, that means there are two possible paths from source A to B. So then we have to find out the minimum among those two. So here we are having only one incoming edge for B, C and D, you can see. So we need not go with the minimum. So only one calculation will be there. So that will be cost of A comma A plus distance of A comma B. That means edge. And here also cost of A comma A plus distance of A comma C. Here also cost of A comma A plus distance of A comma D. So here we are at source, so that's why you need not write this one directly, we can go with the edges, right? So if you are at E, then how to reach to E? So you can reach A to B, B to E, similarly A to C, C to E. So this we are computing here, right? So this will be the cost of A to B plus distance of B to E. That means whatever the vertex is, so just before E, that is already computed. So in the same way, now we are at A, so the cost of A to A plus A to B, cost of A to A plus A to C, cost of A to A plus A to D. So we can compute here, cost of A to A is 0, which is already computed in our previous stage. So that is a dynamic programming. So complete problem will be divided into different solutions, different sub-problems, and each sub-problem will be solved and the solution will be saved in the memory, so that in order to avoid the recalculation, right? So cost of A comma A is already computed, which is 0, 0 plus distance of A and B, which is 1, so finally 1. And here cost of A to A, it is 0 plus distance of A to C is 2, so totally it is 2. And here again cost of A to A is 0 plus A to D, it is 5, so it will be 5. So in order to reach from A to B, the distance is 1, A to C it is 2, A to D it is 5. Now, so any other vertices in the stage 2? No, B, C, D. So we have found already the distance from source to B, source to C, source to D. Now go with the 3, stage 3. So what are the vertex available in D 3? E, F and G. Now we need to find out cost of A to E. A to E. So how many ways we can go to E, right? So how many incoming edges? So find out the incoming edges of E. So incoming edges of E are 2. One is from B, another one is from C. So we need to find out the cost of A to B, A to C, and then the distance of B to E. So, and we have to use a minimum value, so which is a cost of A to B plus distance of B to E. Similarly, cost of A to C plus distance of B to C. So we need to find out the minimum among these two, because in order to reach E, vertex E, there are two possible paths from the source. One is through B, one is through C. So cost of A comma B already we have computed in our previous stage. Cost of A to B is 1 plus D of B, distance of B and E, it's a 4. So which is totally 5. And coming to the cost of A to C, already computed in our previous stage, it is 2, distance of B and C. Sorry, this is not B and C. C and E, right? C to E, which is, this is 11, right? Okay. B, okay. So C to E it is 9, so it is 9, which is 11. So among these two, which is a minimum? This one. We need to consider this one. Okay. Now, any other edge? A to F. Cost of A to F. So in order to reach F, you can see, in order to reach F, what are the incoming edges to F, two edges. So what are those two edges? One is from C, okay, another one is from B. So we need to reach A to C, A to B, and then only we need to go with the C to F. So we need to find out the minimum of, so cost of A to B plus distance of B to F. Similarly, cost of A to C plus distance from C to F. We need to find out the minimum cost of AB, already computed here, 1 plus distance of B and F. B and F distance is 11. So total it is 12. Then cost of A and C. Cost of A and C already computed, so which gives a 2 result, plus distance of C and F. C and F, it is 5. So it will be 7. So we need to consider 7 itself. Okay. Now cost of, there is a one more vertex G. So source to G. So how many edges, incoming edges for G? You can see two edges. One is from C, another one is from D. So we can travel from A to C and A to D. So which one we have to pass? Okay, which one we have to select? Minimum path. So here also we need to find out the minimum value among the cost of A to C plus distance from C to G. Similarly, cost of A to D plus distance of D to G. So cost of AC already computed, which is 2 plus distance of CG. C and G is 16, total 18. So cost of A and D is 5. Distance of D and G is 2. So which is 7. So we need to select this one. Okay. So any other vertex, we have find out the distance from A to E, A to F and A to G. So both E, F, G all are from stage 3. Okay. So this is stage 2 and this is stage 1. This is stage 1. Right? Now going to the stage 4. So which is a destination. So here we are having only one vertex, that is H. So one constraint in multi-stage graph is there should be only one source and one destination. So if any stage is having only one vertex, that will be the destination. Now we need to find out the cost of source to destination. Source to destination. So in order to go with H, what are the incoming edges? You can see one is from E, another one is from F, another one is from G. So through E, what is the cost between A to E, A to F and A to G? Because source is A itself, right? So already these we have computed in our previous one. These we have computed in our previous stage because E, F, G all are in stage 3. So here we have computed the cost from A to E, A to F and A to G. So we have to use the already computed solution. See, so this can be a minimum of so cost of A to E plus distance of E to H. Similarly, cost of A to F plus distance of F to H. Similarly, cost of A to G plus D of G to H. So find out. We have to find out the minimum. Cost of A to E. So already we have computed cost of A to E, which is 5. We got a 2 paths, 5 and 11. Among that we have to select the minimum path. I am selecting this one. So 5 will be the cost of A to E plus D of EH. EH it is 18. So which is 23. And cost of AF already computed here. AF Again we got two values, two possible paths. One is with the 12, one is with 7. So we need to find out we need to consider the lowest path. So that means 7. So 7 plus distance from F to H. So F to H, the distance is 13. So which is 20. And similarly cost of AG. So again we are having two possible paths. Among that we have to select the least possible path, which is 7. So 7 plus D of GH, which is 2. So it will be 9. So among these two, 23, 29, which one is the lowest? So this one is the lowest. So we need to consider the 9, right? So this is the only one vertex in this stage 4. So that implies this is the destination. Okay. So now what is the solution for this one? What is the path? Now what is the last one? Distance of G to H. So distance of G to H, and which is added with A to G. So go to the cost A to G. So in this A to G we have considered this one, right? So A to G, that means the distance of D and G. So D and G, which is computed with A and D. Cost of A and D, go back. Cost of A and D. So which is distance from A and D. So which is distance from A and D, right? And then cost of A comma A. So source and destination. So this is the shortest path for this particular multi-stage graph. You can see A to D, which is a 5, D to G, which is a 2, G to H, again it is 2. So totally 9 is the distance to travel from A to H. That means source to destination with the shortest path. So you can cross check multiple ways. So A to B, B to E, E to H. So it will be 5 plus 18, 23. A to C, C to F, F to H. 7 plus 13 is 20. So A to C, C to E, E to H. 2 plus 9, 11 plus 18, 29. So all other possible paths will give more than 9 distance. More than 9 distance. So only this particular path, that means A followed to B, sorry D followed to G followed to H, will give the shortest path to travel from source to destination, right? So hope you understood. Here we have taken the 4 stages. So you can remember that the same diagram we have taken for the forward approach also, and we have solved it and we got the same path, okay, for the shortest distance, right? So you can cross check. So the complete subject link will be posted in the description. So you can go through the forward approach, and now you can analyze the backward approach. So already in the forward approach we have taken one more example with 5 stages. So try to solve that 5 stages by using the same problem, same procedure. So you need to get the same path which gives the shortest distance. We will see one more concept in algorithms, that is optimal binary search tree. Optimal binary search tree. So which can also be called as OBST, and this by using the dynamic programming. Okay, so we have to implement this one using dynamic programming. So we know that dynamic programming means the working of dynamic programming will be similar to the divide and conquer method. So where the complete problem will be divided into sub-problems, and that will be solved, and the solutions of each sub-problem will be stored in a memory, right? So that we can implement by using a top-down approach and the bottom-up approach, and the process we call it as a memorization and the tabulation. So the same concept we are going to use in this particular OBST, optimal binary search tree, which is an application of dynamic programming. Now we will recall about the tree. So a tree is nothing but nodes and vertices. Okay, and coming to the binary search tree. So we have seen about the binary search, right? So the constraint of binary search is to maintain the sorted elements. That means we have to first the elements to be get sorted, and then only we have to apply the binary search tree. And here we will be having the root node
in this binary search tree, and on the left hand side of this root node, all the elements should be less than the root element, and on the right hand side of the root should be greater than the root elements. So if the tree satisfies this one, we can say it as a binary search tree. Okay, so for example, let us take some 10, 20 and 30. So you can consider 20 as a root, and left hand side the less than element, and right hand side it is a one more element, that means a greater than root. For example, the same thing, if you consider 30 as a root, left side you can have a 10, and on the right hand side of 10 it will be a 20. And you can see on the right part, right hand side of this root, we are having all the elements of which are less than root. And if you consider 10 as a root element and 20 is on the left hand side, sorry, right hand side, because greater than 20, and 30 is the right hand side of 20. And similarly, you can also go with a 30, with a 20, with a 10. See, all these are the different cases. So we can draw the binary search tree for these three elements in these multiple ways. Right? Now, the question is optimal. How we can say it as an optimal binary search tree? So the mainly binary search tree, the name itself indicates it is used to search the element in a tree. For example, if you want to search for 30, so it will be here, and it will be here, and it will be here, and it will be here. So for searching the element, we will be using this binary search tree. Now what about this optimal binary search tree? Optimal binary search tree. For example, if you want to search 30, how many comparisons you require here? So 1 and 2. So 2 comparisons are required. But here it is only one comparison is required because it's a root element. But here 1, 2, 3. 3 comparisons are required for searching of 30. And here it requires only one comparison, right? So if you want to search the 30, we are having a different possibilities. Among that, these two comes under the optimal. These two comes under the optimal because it requires a minimum number of comparisons. So with one comparisons we can get the success. And here also we can, with one comparison we can get the success. For example, if you want to search for 20. So it is one comparison, it requires the 3 comparisons, it requires the 2 comparisons, it requires the 2 comparisons. So you can check. So these 3 will be the optimal. Okay, any one we can draw. Okay, so like that. So optimal means with a minimum number of comparisons we are supposed to get the success. Okay, so less number of comparisons, the search operation should be done. Alright, so that you can see, in order to search all these elements, see, I will draw here and I will explain you. If you consider the same 3 elements, some 10, 20 and 30, so I will give you a few examples. So 20 and 10, this is the first case. If I go with the 20, I can get a 10 and I will get a 30 here, and if I get a 10 here, I will get a 20 here and I will get a 30 here. So let us take only the 3 possibilities. We will be having a more number of possibilities to draw the tree. So here, how many comparisons we require? For 30 it will be 1, for 20 it will be 2, for 10 it will be 3. And here for 20 it will be 1, for 10 it will be 2, for 30 it will be 2, for 10 it will be 1, 2 and 3. So what is the average cost for search? Average cost, 1 comparison, 2 comparison, 3 comparison by 3. And here 1 plus 2 plus 2 by 3. Here 1 plus 2 plus 3 by 3. So which is nothing but, here it is a 6 by 3, it is a 5 by 3 and it is again 6 by 3. So obviously this is the optimal binary search tree for these elements among these three. Okay, there are many possibilities. We can go with one more possibility. So let us take a 20 here, and here we can give a 30 here, and here it can be 10 here. So this is also one more possibility. And we can compare all the things. But among these three, we can say that it is a 5 by 3. The cost will be 5 by 3. That means it requires a minimum cost to search all the three elements. So this will be called as an optimal binary search tree. So which will have a minimum comparisons. So if there is no comparisons, if there is no search, obviously this will be the binary tree. No doubt at all. All the three comes under the binary trees. Now we will see how can we find out the optimal binary search tree among a different binary search trees, different combinations. Okay, so if we take some 4 elements, there will be a lot of combinations of, we can draw a lot of combinations of binary trees, binary search trees. But among that, we have to find out the optimal binary tree. So that is the problem here. How to find the optimal binary tree? That means with a minimum cost. So for this, first we have to find out the root element. So which root element will give the minimum cost of the complete tree? So here we'll be having two options. One is the keys, which are nothing but elements, and another one is probabilities, or sometimes we can also call it as a frequencies, the frequency for a successful search of an element. Okay, so we'll be having these two things. Okay, and there will be also the third thing, probability of success and probability of unsuccess or not success. So there will be two types. So we can implement this OBST with the two types. One is with the keys and probabilities of success, and another one is the keys and probability of success and probability of unsuccess. Right? So two ways we can find out the optimal binary search tree. So now we'll go with this process. That means with the keys and corresponding frequencies or the probabilities of success. Right? Yes. Now we'll see. We'll take a problem and we'll solve it. So we required keys and the probabilities or frequencies. So here my keys are 10, 20, 30 and 40. I'll take only 4 elements. Okay, 4 elements. So the corresponding keys 4, 1, 3, 2. These are the probabilities. Now we have to find out the optimal binary search tree. That means the binary search tree with a minimum number of comparisons. So we can construct a lot of binary trees. For example, I will take a 10 here, so 20 here, and 30 here, and 40 here. So this is also binary search tree. And if you consider 30 as a root, I can go with a 20 here, and a 40 here, and here again a 10. This is also one binary search tree. And if you go with a 20 as a root, I can get 10 here, 30 here, and 40 here. This is one more binary search tree. If you go with a 40, and you can go with the 30 here, 20 here, 10 here. So this is the one more. So like this, there will be a lot of combinations of binary search trees. Among these, we have to find out the optimal binary search tree. Now, let us consider, see, this will be using some table. We are supposed to fill the table. So first I will draw the table here. So 0, 1, 2, 3, 4. Because we are having a 4 nodes. So similarly on the rows also I will go with a 1, 2, 3, 4. So 4 rows and 4 columns. So I am constructing the table with 4 by 4 size. And now we have to fill out the cost of each and every node to other nodes. So this is the use of this table. So what is the main purpose of dynamic programming is memorization or tabulation. That means storing the results for the future purpose. So now here let us consider this as a I, rows as I and columns as J. So I'll tell you what is that I and J. Now we have to consider what is the root. Okay, which should be used as a root. For example, for the first case, if there are no nodes, so we can have 0 nodes in a binary search tree, 1 node in a binary search tree, 2 nodes in a binary search tree, 3 nodes in a binary search tree, and 4 nodes in a binary search tree. Okay, yeah. So this is nothing but I minus j is equal to 0. This is, sorry, j minus I is equal to 0. Always j should be greater than I. Okay, so j minus I is equal to 1. J minus I is equal to 2. J minus I is equal to 3. J minus I is equal to 4. So that implies a tree with 0 nodes, tree with 1 node, tree with 2 nodes, tree with 3 nodes, and tree with 4 nodes. Now what we have to find? We have to find out the root. So which we have to consider it as a root. So if it is 0, 0 nodes, that means there will be no roots. So there will be no cost. So when happens in this one? So obviously whenever I becomes j, then this becomes 0. That means let it be C as a cost 1 1, cost 2 2, cost 3 3, cost 4 4. Okay, so always this becomes zeros. Okay, so I'll fill this one 0 0, 1 1, 2 2, 3 3, 4 4. All the costs are 0. Now let us consider the second one. That means j minus I is equal to 1. J minus I is equal to 1. That means if it is having only one root node, so that means I and j, you can check 0 1, C of 0 1, C of 1 2, C of 2 3, C of 3 4. So you can check I and j. So let us consider C of I, j. 1 minus 0 is 1, 2 minus 1 it is 1, 3 minus 2 is 1, 4 minus 3 is 1. You can check it. So 0 1, okay, 1 2, this one, 2 3, this one, 3 4, this one. So that means this is a next diagonal position. So that you have to find out. So what we are saying, 0 1, 0 1. So if it is there only one element. So always remember, you don't consider this I value. Start with I plus 1. Okay, don't consider the I value. Start with the I plus 1. Now 0. So we should not consider 0. So I plus 1, 0 plus 1, 1, and the end is j, that means 1. So only one node. What's the first node? 10. So if there is 10, see the formula I am writing here, C of I, j is equal to minimum of C of I, k minus 1 plus C of k, j plus W of I, j. W is nothing but a cost, complete cost. So I'll write somewhere else this one. Okay, no problem. As of now, leave it. So C of 0 1, that means C of 0, and here minimum this is I less than k and less than or equal to j. That means k value will be in between greater than I and equal to j. So that means, so 0 less than k less than or equal to j. So in this case, ij. So what is the value of k here? So greater than 0, so we should not consider 0, right? Greater than 0 and 1. So here it is 1, j value is 1. So obviously the value will be k is equal to only 1. So only 1, if k value is only 1, you can see. So hope you understood this one. Now we will consider one by one. So we are now in this position. I am erasing all the remaining, okay, for calculation purpose. So we need to calculate C of 0, 1. So C of 0, 1 is equal to a minimum of, okay, so that means only one element is there. One element means only 10, the node 10. So what is the frequency for search of 10? It's a 4. So simply you can write it here 4. Okay, so if here it is a 4, 1, 2. So you should not consider 1, only 2. So that means second element 20, frequency is 1. You can represent here 1. And 2, 3. 2, 3. So 2, 3 means don't consider 2, the third one. So third one is the 30. 30 frequency is 3. You can simply use here 3. And the next one is 2. Here it is 2. Okay, don't confuse. I'll explain you this one. So see, if it is 2 nodes, what we have to get? J minus I is equal to 2. For example, consider 10, 20, 30, 40. So what we are doing? First, this one completed. So either 10 or 20 or 30 or 40. These are all individual nodes. So that's this diagonal. Now we have to suppose to find what is the 2 nodes. J minus I is equal to 2. So for that we can write it as C of 0, 2, C of 1, 3, C of 2, 4. So we can't go with the 3. If it is 3, then it will be 5. So there are only 4 nodes are there. So 1, 2, 2, 3 and 3, 4. So that we can go with this one. Okay, see. Now we are replacing this one. So we have to find out C of 0, 2, the cost of 1, 3 and the cost of 2, 4. For example, let us go with the 0 and 2. 0 and 2. 0 to 2. Right? So only 2 elements are there. That is 10 and 20. Only 2 elements are there, 10 and 20. So you can check the possible binary trees on 10 on the right hand side, 20, and if it is 20, left hand side it is 10. Only 2 possibilities. So what's the this one frequency of 10? It is a 4. Frequency of 20, it is 1. Frequency of 20, it is 1. Frequency of 10, it is 4. So how many comparisons required? 1 comparison, and here it is 2 comparisons. Here it is 1 comparison, here it is 2 comparisons. Now find out the cost here. So 1 comparison into 4 plus 2 comparisons into 1. So which is nothing but 4 plus 2 is a 6. And here you can see the cost is equal to 1 into 1 comparison plus 4 into 2 comparisons is equal to 1 plus 8, which is 9. So among that, which will be the optimal? Obviously, if 10 is a root node, then it will be an optimal. If 10 is a root node, it will be an optimal, right? So with this, because we need only 6 comparisons, that means a 6 cost. Cost is 6. Here cost is 9, which is greater than 6. So this will be the optimal. So the same thing we'll be getting by using this formula. I'll write this formula here once again. So C of I, j is equal to minimum of I less than k less than or equal to j, C of I k minus 1 plus C of k, j plus W of I, j, where W of I, j is nothing but a weight or a cost. okay, cost. Now you can consider the same thing here. Okay, we'll do the same thing by using formula. We have to do this thing for each and every possibility, but here it is only two elements, we are having only two combinations. If that is a 3, we'll be having a lot of combinations. If it is a 4 nodes, we'll be having a more combinations. So this is a generalized formula to find out this particular cost. For example, consider the same thing 0, 2. So C of 0, 2 is equal to minimum of 0 less than k less than or equal to 2. Okay, so 0 less than k less than or equal to 2. That means k will be either 1 or 2. So we have to write down 1 or 2 and we have to take out the minimum. So this is the minimum. So I will write here C of I is 0, k minus 1. If k is 1, k minus 1 will be 0 plus C of k is 1, j is 2. So this is a I value, this is a j value. Okay, this is one possibility. Now if k is equal to 2, then it will be 0, k minus 1, 1 plus C of, what is here? K is 2, 2, 2 plus W of 0, 2. So that is the 0 of 2 means only we have to consider other than I plus 1 to j. That means I plus 1 means 1 to 2. So 1 to 2, here it is a 1, 2, 3 and 4. 1 to 2, that means 4 plus 1, it will be 5. The frequency 4 plus 1, it will be 5. So this will become 5. Okay. So what we have to do? Check out. Cost of 0, 2 is equal to minimum of, okay, first C of 0, 0. You can go with the table. 0, 0, cost 0 plus cost of 1, 2. Cost of 1 and 2 is 1. And this one, C of cost of 0 and 1. 0 and 1 is 4. Cost of 2, 2. 2 and 2, it's a 0. Plus, what's about 5. So how much you will be getting? 1 plus 5, either 6, 4 plus 5, either 9. So what we got in this way. So these are the two different ways. Actually, based upon the frequency, if you are able to draw the tree, then it will be simple to find the cost. But if there are more number of nodes, so we have to find out for all the combinations. So that will be somewhat difficult. So that's why we can use this particular formula to find out the cost. Okay. So now, which one we have to consider? 6. 6 we are considering, right? So if you consider 6, what is the root node here? So here you can apply 0 to 2, it is 6. And what is the root here? So whenever the k becomes, so this is the solution, right? Whenever the k becomes 1, we are considering it as the optimal, right? See, the first 10. K is equal to 1. So this is the k value and this is the elements and this is a probability, right? So whenever the k becomes 1, this first case, if you consider first case and second case, first case only we are getting the optimal solution. So first case k is equal to 1, right? So you can represent it here as a 1. 1 as a root node. So similarly here also you can see 4. 4 is a 1. 1 is a 2 as a root node. 3 as a root node. 4 as a root node. Okay. Now consider the same, apply the same formula to find out the cost of 1, 3. So now I am not drawing the trees anymore. I am directly using this formula to find the cost, okay, for remaining process. So I use this place to find out the cost of everything. And see, we are just storing the information in the table so that we can retrieve the data whenever it is required in order to avoid the recalculation. Now, C of 1 comma 3. So is equal to a minimum of 1 less than k less than or equal to 3, and what we have to do, C of I 1 comma k minus 1. So here k will be becomes 2 comma 3 because 1 less than k less than or equal to 3. That means k will be in between greater than 1 and less than or equal to 3. So k of 1 comma 2 minus 1, 1 plus C of k 2 and 3. This is one possibility. And one more possibility, whenever k becomes 3. So 1 comma 3 minus 1, 2 plus C of k. That means a 3 comma 3. Sorry. Plus W of 1 comma 3. So this we have to find out. Now you can find a minimum of C11, 1 cost it is 0, plus 2 3, 2 and 3 cost is 3. So simply remember this 4 1 3 2 are cost, and 1 2 3 4 are the root nodes. So 1 represents this 10, 2 root node means a 20 as a root node, 3 means a 30 as a root node, 2 means a 40 as a root node. So next, if there are 2 items, we have to consider 1 as a root node so that we will be getting the optimal solution. So 0 plus 3 and C1 2, 1 and 2, it's a 1 plus 3 and 3, 3 and 3 it is 0, yes, plus W of 1 3. So we should not consider 1 here, right? So we are considering from only 2 and 3. So 2 and 3, what is the profit of 2 and 3? That is the cost of 2 and 3. 1 plus 3 is a 4. Now, what is the minimum value here? It will be 7 and it will be 5. So, obviously 5 will be minimum. 5 will be minimum. Right? We have to consider 5 else. So, what is the value of k? That means a root node. So, the second case we are considering. In the second case, what is the k value? 3. So, 3. So, in these two things, that means from 20 and 30, in between 20 and 30, 3 should be the root node. That means the 30 should be the root node, then only we will be getting the optimal solution. So, just represent that there. So, the cost is 5 and 3 is a root node. Okay, 3 is a root node. Now, see, here it is a 5. Now again we have to consider C of 2, 4. One more possibility, 2 and 4. So the same thing apply here. So we have to fill all the table, right? So here always the J should be greater than I. So we will be getting only the upper triangle. Okay, we can ignore the lower triangle. So next C of the next one is a 2 comma 4, and you can see a minimum of 2 less than k less than or equal to 4. And see the k values will be 3 and 4, which is minimum value 2, that means a greater than 2 we should consider. So C of what we have to do? I k minus 1. I is 2, k minus 1 3 plus C of 3 and no, k is 3, no, k is 3 means here 2, 3 and 4. And similarly C of I came 4, 4 minus 1, 3 plus C of 4 comma 4. So what we are getting? Plus W of 2 comma 4. So we have to consider the frequencies of 3 and 4, right? So 3 and 4 means these two things, which is a 5. So this will be 5, this will be 5. So we have to consider the values, the minimum of, so C2 comma 2, cost of 2 2. Which is 0, 3 4, cost of 3 and 4, cost of 3 and 4, it is a 2. Next, cost of 2 and 3, 2 and 3, it is a 3. And 4 and 4, 4 and 4, it is a 0. Plus 2 4 means it's a 5. So among these minimum values, this will be 7 and this will be 8. So 7 will be the cost of 2 and 4. So when we are getting the cost 7, what is the root node? So first case we are considering so that we are getting the optimal, right? In the first case, what is the k value? It is a 3. Okay, so 3. Now update here. So the cost of 2, 4, 2, 4 will be 7 and the root should be 3. The root should be 3. That's most important because after that, after completion of this table, so we are supposed to draw the tree, construct the tree. That will be based upon these root nodes because these are the root nodes we are using to get this particular minimum cost. Okay, yes. So there are all possibilities has been completed for 2 nodes. Now gradually increase. That means 3 nodes. So what happened to get the 3 nodes? So you need to find out the root if there are 3 nodes. Okay. So 3 nodes. What is the root if the tree is having 3 nodes? That means j minus I should be 3. J minus I should be 3. So starting from 0, if you can consider 0, 3 and C of 1, 4. So you will be getting only 2 possibilities. If you go with the 2, then it will be automatically 5. So there are no 5 nodes, only 4 nodes. So there are only 2 possibilities here. So first let us consider C of 0, 3. We will find out. So a minimum of 0 less than k less than or equal to 3. What we have to do? C of 0, so here k will be becomes 1, 2, 3. 3 possibilities are there here. 3 possibilities. So among these 3, which one should be the root node to get the optimal solution? So k value 1, 0 plus C of 1, 3. And similarly the second one, if k value is 2, 0, 1 plus C of 2, 3. And if it is k value is 3, 0, 2 plus C of 3, 3. So just go with this formula. What we have to add? W of 0, 3. W of 0, 3. So that will be minimum of, you can calculate 0, 0 plus 1, 3. 1 among 3. So 5. Next 0, 1. 0, 1 it is 4. And 2, 3. Yeah. 2, 3. 2, 3 it is a 3. And then 0, 2. 0 with 2 it is a 6 plus 3, 3 it is a 0 plus, what's the weight here? So we have to consider the weight from I plus 1. That means 1 to 3. So 1, 2, 3. So 4 plus 1, 5, 5 plus 1, 5 plus 3, 8. So it will be 8. So the cost will be a minimum of, so what's the minimum value here? So 5, 7, 6. Okay, 5, 7, 6. So 5 is the minimum value, 5 plus 8, it will be 13. So we have got the cost of 0 to 3 is 13. When we got this 13? By considering the first case. What's the k value in the first case? K value in the first case is 1. So it is 13 with a 1 as a root node. 13 with a k value as 1 as a root node. Okay, now hope you understood, right? So this is the case where we'll be getting the optimal solution. So whenever the k value becomes 1, we are considering the optimal solution. So that means in these 3, 10 will be the root node, then only we'll be getting the optimal solution. Now there is one more possibility. To find the root node. So which is C of 1, 4. So which becomes minimum of 1 less than k less than or equal to 4. And C of, whenever here k becomes 1, 2, 3 and 4. Whenever k becomes 2, 1, 1 plus C of 2, 4. Similarly, C of 1, whenever k becomes 3, 1, 2 plus C of 3 comma 4. So because it is a k, I k minus 1 kj, and see here it is also C of 1 comma 4 is a k, so k minus 1 3 plus C of 4 4, and we have to add the frequencies from 1 to 4, that means 2 to 4. So what is the values? The minimum of, what's the values here? C of 1 1, which is a 0, plus C of 2 4, 2 4, it's a 7, and again 1 2, C of 1 2, it's a 1, plus C of 3 4, 3 and 4, it is a 2, C of 1 3, 1 and 3 is a 5, plus C of 4 4, it's a 0, plus this one. So now we have to consider these three, 2 to 4, 1 3 2, that means total 6. So among these three, which one is the minimum? This one. That means we are considering the second case. So 3 plus 6, it is a 9. Okay, 3 plus 6, it is a 9. So now what is the root node here? So second case. In the second case, what is the k value? 3. So 3 will be the root node. So 9 will be the cost, and here also I will go to with the 9, and the root node is 3. And there is one more possibility. So now we are considering all the 4 nodes, right? We are considering all the 4 nodes because we are having only 4 nodes. If you are having 5 nodes, then there might be 2 more possibilities. Okay. So 4 nodes. We are having only 4 nodes. We are having 4 nodes. So that means j minus I is equal to 4. That is, we'll be having only one case among that. That is 0 comma 4. So C of 0 comma 4 is equal to a minimum of 0 less than k less than or equal to 4, and you can now apply C of, whenever k, here the k becomes values of 1, 2, 3 and 4. K values are 4, right? So whenever k becomes 1, then 0 comma 0 plus C of 1 comma 4. When k becomes 2, 0 comma 1 plus C of 2 comma 4. So here I k minus 1 kj. C of 0 comma, when k is equal to 3, 2 plus C of 3 4. And whenever k becomes 4, 0 comma 3 plus C of 4 4 plus W of 0 comma 4. So here what we have to do, we have to consider from I plus 1. So all these things we should be considered. Now let us calculate a minimum of, so 0 0, its cost is 0 plus 1 4, 1 and 4, it is 9. Next 0 1, 0 1, it is a 4, 2 4, 2 with 4, it is 7. Okay. Next 0 2, 0 to 2, it is a 6 plus 3 4, 3 with a 4, it's a 2. 0 3, 0 with a 3, it's a 13 plus 4 4, 4 4, it's a 0. Plus, wait, 4 plus 1 plus 3 plus 2, that means total 10. Now what will, among these things, what's the minimum value? It's a 9, it's 11, it's 8, it's 13. So this is the minimum. So 8 plus 10, which is 18. 8 plus 10, which is 18. So when we are considering this 18, the third case. In the third case, what is the key value? What is the key value in the third case? 3. So 3. So the cost is 18 and 18 and it is 3. Now you can see the root node is the third element, which is 30. Third element, which is 30. Now we have completed the construction of a table, right? Now we have to construct the tree. We have to construct the tree. How we have to construct the tree? So only one formula is there. So which is R, that is a root node. So of 0 comma 4, of 0 comma 4, or you simply can write it as I comma j, which is a k. So obviously left node will be R of I comma k minus 1, and here it is I R of k comma j. So the same thing we have to apply here. Now what is the node? 0 to 4. So we have to consider all the 4 elements, right? So when we are considering all the 4 elements, what is the root node in which we are getting the optimal solution? So our problem is having 4 elements. Okay, our problem is having 4 elements. So this will be the root node. Which will be the root node? 3. So third element means 30. So here the k value is 3. So I am writing the element, okay, k value. So after that I have to write it as here R of, what is this one? 0 comma k minus 1, 3 minus 1. Okay, 3 is a k. This is a k value. Okay, so 3 minus 1, 2. 0, 2. 0, 2. What is the root node? 1. So first element. Okay, just remember here these are the k values. K value means the order of elements. Okay, not the one. 3 is not an element. 3 means third element. 1 means first element. 2 means second element. Okay, now what is this one? R of k. What is the k value here? 3. See, this is a k value. 3 comma j means 4. What is the 3, 4? 3 and 4. Okay. So what is the k value? 4. So this should be written here. That means the fourth element. Fourth element in this order, right? Now expand this one. We have to expand until we get the 0, 0. Okay, until 0, 0. Now again R of, see, I value is 0 comma k value. So here it is a k. 1 minus 1, 0. So R of 0, 0, 0. So you can remove this one. And what about this one? R of k. See, R of k. K means 1. 1 comma j. J means 2. 1 comma 2. 1 comma 2. It's a second. That means a second element. Second element. Now expand this one. What is this one? R of I means 3 comma k minus 1. Here it is a k. 3. So which is 0. So this is not possible. Okay. And expand this one. R of, what is the k value? K value is 4. When j value is a 4, which is again 0 cross. Now you can construct this tree. So third root, first element, second element, and the fourth element. Now you can consider this one. See, I'll erase this one and I'll draw. What is the third element? 30. First element on the left, 10. Second element on its right, 20. Fourth element on its right, 40. And you can check about this binary search tree. So 30 is the root. So left side we are having the less than 30 and right side we are having the greater than 30. If you consider 10, left side there are no elements, right side we are having the greater element. Right? So this is the optimal binary search tree we can construct from these elements with the probability of success. So this is only having the probability of success in the search. Okay, so there is a one more possibility there. We can have a one more chance. That means the probabilities for unsuccessful search. Okay, that will go with the next session. So hope you understood. Just by observing this formula, we are supposed to use this table. We have to fill this table. So you can observe we have calculated 0, 0, 0, 1, 0, 2, 0, 3, then 1, 1, 1, 2, 1, 3, and 2, 2, 2, 3, 2, 4, and all these things we have calculated to find the root element. That means this is a bottom-up approach. So this process we can call it as a tabulation. Okay, not a memorization. It's a tabulation. It's a bottom-up approach. So we'll call it as OBST, optimal binary search tree. So in our previous session, we have discussed about this complete information about OBST. So what is a tree, what is a binary search tree, and how it differs from the optimal binary search tree. So if you have not seen that video, I'll post the link of that particular video in the description. First, go through that video so that you will be getting a clarity about the differentiation of tree binary search tree and optimal binary search tree. And in our previous class, we have seen one example that takes the frequencies of successful searches. And now today's session we'll see one more example which takes the frequencies of both successful and unsuccessful searches, right? So let us take an example. Let us take some elements. So those are 10, 20, 30 and 40. So I'm taking only 4 elements, right? So in order to reduce the calculations, okay. So we need to construct the optimal binary search tree. That means we have to construct the binary search tree with a minimum number of comparisons for a successful search of each and every element of that particular tree. So obviously here the question is which we have to select it as a root. Then we can get the optimal binary search tree. So with this we can have a multiple binary search trees. We can construct a multiple binary search trees. Among that we have to decide which will be the optimal binary search tree. That means minimum number of comparisons. With the help of minimum number of comparisons, how efficiently we can get the search, right? Now, let us take some P of I. Let us indicate P as a successful search, successful searches, which is from 1 to 4. Let us take the frequencies as 3, 3, 1, 1. That means the frequency of first element, to search for the first element is 3, and the second element is 3, the fourth element is 1, and fifth element is 1. And similarly, let us consider a Q as unsuccessful. So obviously, that will be from 0 to 4 because so if we are having 4 elements, in our tree, so we have to compare all these 4 elements, and in the fifth element we will be getting the fifth comparison, we will be getting the unsuccessful, right? So fifth element we will be getting the fifth comparison, we will be getting the unsuccessful. So the unsuccessful nodes will be 5 and successful nodes will be the number of elements. If n elements are there, the successful frequencies will be n and unsuccessful frequencies will be n plus 1. So let it be some 2, 3, 1, 1 and 1. So that's why we have given it as 0 to 4, P as 1 to 4. Right? Now we have to start executing. So let us write the formula first. So whichever the formula we have done, the same thing we have to apply here. So what's the formula we have done? C of I comma j is equal to minimum of I less than k less than j, and from here we have to apply C of I comma k minus 1 plus C of k comma j plus W of I comma j. So this is a formula where we have to find the cost of the element, to search the element, cost. And the next one, similarly R of I comma j is equal to k. That means for which k value we got the minimum cost. So we need to consider the element as a root. So this is particularly for the root element, to select the root element. So for which k value, this particular expression we are getting a minimum value, that will be the k value and that will be considered as a root. So that will be considered as a root of ij. Now W of I comma j is nothing but W of I comma j minus 1 plus P of j plus Q of j. So this is a formula. This is a formula we have to calculate the W of ij. So this is a somewhat different which we have not calculated in our first example. That means when we have taken only the successful frequencies. But here in this example we are taking the two different frequencies, successful and also unsuccessful. So based upon these two we have to find out the optimal binary search tree. Now the initial conditions. So what is the initial conditions? Whenever it is I comma I, that means whenever j becomes I, whenever the j becomes I, then that will be a Q of I. It will be Q of I. And similarly, cost will be 0 and obviously root will be 0. See, simple. This is nothing but when the tree structure doesn't have any elements. If tree structure doesn't have any elements, obviously in the first thing only we will be getting the unsuccessful. Yes or no? So for example, we are searching for element 10 and initially there is no tree. Then obviously what happens? For the first frequency itself we will be getting the unsuccessful. So obviously, so Q of j will be the weight. And what about the C of ij, cost to search? So if there is no element, there will be no cost. If there is no tree, there will be no root. So that's why these two becomes 0 and this becomes the unsuccessful. So now we have to draw the table for searching of the root element. So which one should be a root, right? So the root should be for elements 0. So this is this thing. And what is the root for element 1? If there is only one element, then what will be the root? Itself will be the root, right? And if there are two elements, for example, we are having here 4 elements. That means 4 nodes. So we can consider 0 nodes. What is the root? So obviously 0. Okay. Then if there is only one node, what is the root? If there are 2 nodes, what is the root? So we have to find out the minimum root, right? So what is 3? If the tree is having some 3 nodes, what is the root? And if it is having some 4 nodes, what is the root? We have to calculate that root value. Okay. And this happens when j minus I is equal to 0. That means j and I is equal to 0. Both are the same, right? If this becomes j minus I is equal to 1. And this becomes j minus I is equal to 2. This becomes j minus I is equal to 3. This becomes j minus I is equal to 4. So we need to calculate the cost, weight and root for all these cases. So whenever j minus I is equal to 0, whenever j minus I is equal to 1, whenever j minus I is equal to 2, whenever j minus I is equal to 3, whenever j minus I is equal to 4. That implies here 0 means 0 nodes in the tree. If it is 1 node. If it is 2, there are 2 nodes in a tree. Among that we have to select the optimal. That means the minimum cost. And here j minus I is equal to 3 means if the tree is having 3 elements, what is the root we need to calculate? So in order to get the optimal binary search tree. And j minus I is equal to 4 means if the tree is having 4 elements, which one should be considered, right? Now, see. Now let us draw the tabular form. So I'll draw the tabular form here. So I'll take 0, 1, 2, 3 and 4. 0, 1, 2, 3 and 4. So we need to fill the table and find out the root and apply the backward process so that we will be getting the complete tree structure, right? So let us check out. So for every case, we are supposed to find the weight, cost, and also root. Weight, cost, and root by using these formulas. Now, so this is a I value and this is a j value. I value and j value. Now, initial conditions, and we have seen, and every time, see, by using this formula, I'll calculate each and everything and here, and we'll update the table here. Now, initial conditions, whenever I minus j, I is equal to I, that means first one, j minus I is equal to 0. J minus I is equal to 0 means, so there are no nodes in a tree. If there are no nodes in a tree, obviously the cost will be 0, the root will be 0. But the weight, that means the frequency, will be 2 or 3 or 1 or 1 or 1. Okay, let us check. So this implies I is equal to, j is equal to I. J is equal to I. So we'll get W11 is equal to, okay, W of 1, 1. W of 1 comma 1. I is equal to j. Okay. So what is the value? Q of I. Q of I. So that means Q of 1. Q of 1. So what is the Q of 1? See, 0 and 1. Q of 1 is 3. So 3 will be the weight. What about the cost here? I'll write the cost here. So C of 1 comma 1 is equal to, so if both are equal, then it will be 0. So 0 and root of 1 comma 1. So what is the root of 1 comma 1? That's also will be 0. Right? So update here. 1, 1. Okay. So if it is 1, 1, it will be 3 and so on. Right? So 1, 1. So W of 1, 1 is equal to 3. C of 1, 1 is equal to 0. R of 1, 1 is equal to 0. Okay. Now, let us also consider W of 0, comma 0. So then it will be Q of 0. Okay. Then Q of 0 means it will be 2. C of 0, comma 0, which is 0. R of 0, comma 0, which is 0. So, yeah. This is 1, 0, no? So we need to update here, not here. So this is the place. W of 1, 1 is equal to 3. Yes. C of 1, 1 is equal to 0. R of 1, 1 is equal to 0. And here, W of 0, 0 is equal to 2. C of 0, 0 is equal to 0. R of 0, 0 is equal to 0. Right? Now, 2 comma 2, then also it will be 0, right? So Q of 2, so what's the value of 2? Q of 2 is this is 0, 1, 2, it's a 1. And C of 2 comma 2, which is 0, and R of 0 comma 0, it is again 0. So 2, 2. So W of 2, 2 is equal to 1, C of 2, 2 is equal to 0, R of 2, 2 is equal to 0. Okay, we'll extend this one. Right. Now, again W of 3 comma 3. So again it will be Q of 3. So Q of 3, which is again 1. C of 3 comma 3 is equal to 0. R of, yeah, here it is 2 comma 2. 3 comma 3 is equal to 0. So this position. So W of 3, 3 is equal to 1. C of 3, 3 is equal to 0. And R of 3, 3 is equal to 0. Okay. So same thing. Now W of 4 comma 4. So we need to consider each and every condition, right? Every case, each and every case we have to calculate. So W of 4 comma 4 is Q of 4. So which is again it is 1. And C of 4 comma 4 it will be 0, and R of 4 comma 4. If there are no elements, then automatically root will be also 0. So W of 4 is equal to 1. C of 4 is equal to 0, R of 4 is equal to 0. Okay, so same thing, we have calculated all the roots, okay, all the roots, a k value or weightage and a cost for 0 elements of a tree, if the tree is having 0 elements. Now if the tree is having only one element, if tree is having only one element, that is j greater than I. Now, what are the weight, cost and root? If tree is having only one element, okay, consider tree is having only one element. So obviously W of 0 comma 1, which is 1 minus 0, it is 1, right? Now, what we have to calculate, W0 of 1 is equal to W of I value 0 comma. Next, what's the formula here? J minus 1, y minus 1, 0, plus P of j, j is 1, plus Q of j, 1. So, which is nothing but W of 0, 0. W of 0, 0 is 2. So, 2 plus P of 1, 3, Q of 1 is this one. So, this starts with 0, right? So this is 0, 1, 2, 3, 4. So that's why I have written a key here 0 to 4. And here 1 to 4, 1, 2, 3, 4. So Q of 1 means this one, 3. So which is nothing but 8. Okay. Now calculate the cost from 0, 1. Which is a minimum of 0 less than k less than or equal to 1. C of, so here k holds only one value. That means the k is in between greater than 0 and less than or equal to 1. Greater than 0 and less than or equal to 1. So that means it will take only one value. So now C of, what's the formula here? I means 0, comma, k minus 1. Here k is 1. 1 minus 1, 0, plus C of k. K means 1, comma, j. J means 1. Plus W of 0 comma 1. So W of 0 comma 1 already we have calculated here based upon the successful and unsuccessful searches. So what is the value here? So then here we are taking only one value, so that will be the minimum value. So if there are multiple k values, so that way there will be getting a multiple value. So from that we have to select the minimum value. So but here we are having only one value. So C of 0, 0, C of 0, 0, it is 0. Plus C of 1, 1, 1, 1, again it is 0, plus W of 0, 1, W of 0, 1, here we have calculated, so 8, so which is nothing but 8, and obviously the root of 0 comma 1 is equal to k, see, k, so here what is the k value? 1, so 1, so what is the values? 8, 8 and 1. So whenever j minus 1, I is equal to 1, W of 0, 1, C of 0, 1 and R of 0, 1. So we need to fill this one. So 0, 1, 0, 1 means this one. So W of 0, 1 is 8. C of 0, 1 is again 8. R of 0, 1 is 1. Okay. Now what we have to do? Again, we need to calculate a few more things. So which is W of 1, 2. So in this case also the j minus I value is 1, right? So is equal to W of 1 comma 1 plus P of j, that means 2, plus Q of j, which is 2, So W of 1, 1. 1, 1 W is 3 plus P of 2. P of 2 is 3. Q of 2, 0, 1, 2, it is 1. So which is 7. And C of 1, 2, which is nothing but a minimum of 1 less than K less than or equal to 2. And C of I K minus 1, that means 1 plus C of J, K is 2. Here K value is only 2. So 2 comma J, that means 2 plus W of Ij, 1 comma 2. So here the K value will be only one value, right? So because K value will be greater than 1 and less than or equal to 2. So K is equal to 2. C of 1, 1. C of 1, 1. It is 0. Now C of 2, 2. C of 2, 2 again it is 0. Plus W of 1, 2, which is 7. So that is 7. So a root of 1 comma 2. So only one value K is there. So that will be a 2. So what we have to do? So we have to fill the three things here. So 1, 2. So this one. So W of 1, 2 is equal to 7. And C of 1, 2 is equal to 7. And R of 1, 2 is equal to 2. Right? Now, one more thing. That is 2, 3. This place. This will also be 3 minus 2, 1. Right? So C of 2 comma 3. So we need to calculate C of 2 comma 3. So C of 2 comma W of, first we need to find out the weight because we have to add this weight in the C cost, right? So W of I comma J minus 1, 2 comma 2 plus P of J, that is 3, plus Q of J, which is again 3. So W of 2, 2, it's 1 plus P of 3. So 1, 2, 3, it's 1. Q of 3, 0, 1, 2, 3, it's again 1, which is 3. And cost of 2 comma 3 is equal to a minimum of 2 less than K less than or equal to 3. And C of, so here the K value will be only one element, that is a 3. One value, it's a 3. So C of I, that means 2. K minus 1, again it is 2. Plus C of K, which is 3 comma J, J is again 3. Plus W of Ij, that means 2 comma 3. So what happens here? C of 2, 2. C of 2, 2 is 0. Plus C of 3, 3. It's again 0. So yeah. So this is 1 comma 2. 1 comma 2. Okay. So W of 2, 3. It's a 3. Okay. And here R of 2 comma 3 will be K. K is here only one value, that is a 3. So 3, 3, 3. So 2 comma 3, this place. 2 comma 3. W of 2, 3 is 3. C of 2, 3 is 3. R of 2, 3, it is, again it is 3. Again it is 3. Now, one more case, that is 3, 4. This also, the difference is 1, right? So W of 3 comma 4. So which is W of I J minus 1 plus P of J plus Q of J. So which is W of 3, 3. It's a 1 plus P of 4. It's 1 plus Q of 4. It's 1, which is 3. And cost of 3 comma 4, it will be a minimum of 3 less than K less than or equal to 4. So the K value holds only 4, right? Now C of I comma K minus 1, it is 3 plus C of K comma J, right? Plus W of Ij, so 3, 4. So which is nothing but a 0 plus 0, 3, 3, 4, 4. C of 3, 3, C 4, 4. Plus W of 3, 4 is 3. So which is nothing but 3. And R of 3 comma 4, which is nothing but a 4. Okay, K value is 4. So fill here W of 3, 4 is 3, C of, after weight, cost. C of 3, 4 is again 3, R of 3, 4 is 4. Okay, now see, this is completed, this diagonal is completed, right? That means if the tree is having only one element, right? Now, let us consider the second one. If tree is having two elements, that is j minus I is equal to 2. So j is greater than I. We need to find out W of 0, 2, W of 1, 3, and W of 3, 4, 2, 4. See, 0, 2, 1, 3, and 2, 4. So this diagonal. Right? Now W of 0, 2, which is nothing but W of I, j minus 1. So 0, 1 plus P of j 2 plus Q of j, again it is 2. So W of 0, 1, what is it? 0, 1, W of 0, 1, it's a 8. 8 plus P of 2, P of j. P of 2 means 1, 2, this is 3. Q of 2, 0, 1, 2, it is a 1. So which is nothing but 12. And the cost of 0, 2, so which will be minimum of 0 less than k less than or equal to 2. So here you will be getting k value as 1, 2. So two values we are getting. So we need to consider only one thing which is having the lowest value. So minimum value, right? So C of whenever k is equal to 1, then it will be 0, 0 plus C of 1, 2. Similarly, C of wherever k is equal to 2, 0, 1 plus C of 2, 2. So we need to consider minimum from these two, and we have to add it to W of 0, 2. So what's the values here? The minimum of, let us take the value C of 0, 0. C of 0, 0 is 0 plus C of 1, 2, 1 and 2. C of 1, 2 is 7. And here C of 0, 1, 0 and 1. C of 0, 1 is 8 plus C of 2, 2. C of 2, 2 is 0. Plus W of 0, 2. 0, 2 is 12. So among these, so what is the minimum value? 7. 7 plus 12, it will be 19. 7 plus 12, it will be 19. Now root of 0, 2 will be k. So in which k value we have got the minimum value? Obviously in the first case. In the first case, what is the k value? 1. So R of 0, 2 will be 1. R of 0, 2 will be 1. So we need to update the same thing here. So 0, 2, 0, 2. So W of 0, 2 is equal to 12. C of 0, 2 is equal to 19. And R of 0, 2 is equal to 1. So here you can see we are having a 2 k values. Among those 2 k values, for which k value we are getting the minimum value, that should be considered as a k. So in these two, the first case we are getting the minimum value as 7. So for the first case, the k value will be 1. So that will be stored in R02. Now 1 happened. Now we have to calculate W of 1, 3. Now we have to calculate W of 1, 3. So W of 1, 3 is equal to W of I means 1, J minus 1, 2 plus P of 3, that means J, plus Q of J, it's again 3. So what is the value of W1, 2? 1 and 2, it is a 7, plus P of 3, 1, 2, 3, it's a 1, plus Q of 3, 0, 1, 2, 3, it's again 1. So which is nothing but a 9, value of 9. So cost of 1, 3, C of 1, 3 is a minimum of 1 less than k less than or equal to 3, which holds the k values as 2, 3. So we need to find out the cost. C of I, 1 and k minus 1. Let us consider k as 2. 2 minus 1, 1 plus cost of k means 2 and j, 3. And the second case, C of I, 1 k minus 1. Now k, let us take k as 3. 3 minus 1, 2 plus c of 3 comma 3 plus a weight of 1 comma 3. Now you can consider here minimum of C11. C11 is 0 plus C23. C23 is 3 and C12 is 7 plus C33 is 0 plus W of 13 which is 9. So that implies among these two cases 3 is minimum. So 3 plus 9 is 12. Now R of 1 comma 3. So we got a 12. Okay, and among these two cases we are taking the first case as a existence because the first case is we are getting the minimum value. In the first case, what is the k value? 2. So now R13 will be 2. So update here. So what is that one? 13, right? This one. So W13 is equal to 9. C13 is equal to C13 is equal to 12. R13 is equal to 2. R13 is equal to 2. So 3 is again 0, right? So we should be very careful about these values, right? Now there is a one more case which is 2, 4. We need to calculate the weight, cost and root for 2, 4. 2, 4. Okay, the nodes of 2 and 4. So W of 2 comma 4. So that means we are calculating for every combination, right? So C of W of 2 comma 4. So 2 comma 4, you can see W of 2 comma 3 j minus 1 plus P of j 4 and Q of j 4. So W of 2 3. 2 and 3 is a 3 plus P of 4 which is 1 and Q of 4 which is again 1 which is nothing but a 5. And C of 2 comma 4 is equal to a minimum of 2 less than k less than or equal to 4. So which k holds the values 3 comma 4. And C of I it's 2 k minus 1. First case k is 3. 3 minus 1 2 plus C of k 3 comma j 4. And the second case again, now k, consider k as a 4. 4 minus 1 it is 3 plus C of k it's a 4 comma j is 4 plus a weight of 2 comma 4. So now consider the minimum among these two. C22. C22 is 0 plus 3 4. 3 and 4 it's a 3. 2 3. 2 3 it is 3. See 2 3 it is 3. Yeah. Plus 4 4 it is 0. So you can consider any value. K can be either 3 or 4. Right? Plus 5. So which is nothing but 8. So R of 2 comma 4 will be either 3 or 4. Anything you can consider, I will consider it as 3. Okay, because both are same. Now update here. W of 2 4 is equal to W of 2 4 is equal to 5 and C of 2 4 is equal to 8 and R of 2 4 is equal to 3 or 4, whatever it may be. You can consider anything, right? So here R is 4, 4 is equal to 0. So now we have calculated the root. We have find out the root if the tree consists of 2 elements. That means the difference between I and j should be 1. 2. Now we have to consider this one. J minus I is equal to 3. Now that means if the tree is having 3 nodes, okay, if tree is having 3 nodes, which one should be considered as a root? So for this we have to calculate the things like W of 0 3 and W of 1 4. So 0 3 and 1 4, right? Now W of 0 comma 3 is equal to W of I j minus 1 2 plus P of j 3 plus Q of j 3. So I am applying only these formulas. So is equal to, I'll write here itself, okay. W of 0 2, W of 0 2, it's a 12, plus P of 3 1 2 3, it's 1, and Q of 3 0 1 2 3, it's 1. So which is nothing but 14. W of 0 3 is 14. And similarly C of 0 comma 3, and here we are getting minimum of 0 less than k less than or equal to 3, where k will be holding the values of 1, 2 and 3. So we are getting 3 values. Now first case, consider k as 1. So C of I, k minus 1 0 plus C of k 1 and j 3. Second case, C of I g 0, k minus 1 2 minus 1 1 plus C of k 2 and j 3. And third case 0, C of I 0, k is 3, k minus 1 it is 2 plus C of k 3 and j 3. And then add the W of 0 comma 3. Now you can consider here a minimum among these three values. C00 it will be 0 plus C13 1 3, C13 it is 12 and C01 01 it is 8 plus C23 2 3 it is 3 and C of 02 02 it is 19 plus C of 33 it will be 0 plus W of 03 which is 14. So among these, which one is the lowest? The second one. 12, 11, 19. So 11. 11 plus 14. So this is the minimum value. 8 plus 3. So 11 plus 14. It is a 25. 25. Now what is the root of 03? Then the k value becomes the minimum. So second case k value is 2. So R of 03 is 2. Now you can see 14, 25 and 2. Update here. So W of 03 is equal to 14, C of 03 is equal to 25 and R of 03 is equal to 2. Okay, and we have to check with them one more case, that is 1 4. 1 4. Calculate the same, apply the same formula for this to calculate the weight, cost and root. So W of 1 comma 4. So which is equal to W of I 1 j minus 1 3 plus P of j 4 and Q of j 4. So W of 1 3 it is 9 plus P of 4 it is 1 plus Q of 4 it is again 1. So which is 11. Now we need to find out the cost. So cost of 1 comma 4 it will be a minimum of 1 less than k less than or equal to 4. So k value will be 2 comma 3 comma 4. So first case C of I 1 k minus 1 here, k first case 2 minus 1 1 plus C of k which is 2 j it's a 4. In the second case k will be 3, so 1 comma 2 k minus 1 2 plus C of k 3 and j 4. In the third case k value will be 4, C of I 1 k minus 1 it is a 3 plus C of k 4 and j 4. So which should be added with a weight of 1 comma 4. So here we have to find out the minimum among all these three. C of 1 1 it will be 0 plus 2 4 2 and 4. C of 2 4 it is 8 and C of 1 2 it is 7 plus C of 3 4 it is 3. And again C of 1 3 it is 12 plus 4 4 it is 0. So among these three the first case is having the minimum value. So W of 1 4 is 11. So which will become 19. So root of 1 comma 4 will be obviously the first case, that means 2. Update this in the table, right? So here we have to update W of 1 4 is equal to 11, C of 1 4 is equal to 19 and R of 1 4 is equal R of 1, 4 is equal to 2. So first case, it's a 2. Okay. So this we have done. Now, in the last case, we need to find out the root whenever the difference is 4. That means element is having some 4 elements. Okay, the tree is having 4 elements. So our element is also 4 elements, right? The number of nodes we have taken is 4. So this will be the last case. So it will be 0, 4, this part. So we need to calculate the same formula. We have to apply the same formula and calculate the weight, cost and root. So weight of 0, 4 is equal to W of I 0, J minus 1, 3 plus P of J 4 plus Q of J 4. So W of 0, 3, W of 0, 3, which is a 14, and plus P of 4, it is 1, Q of 4, it is 1, so which is 16. And similarly C of 0, 4, which is a minimum value of 0 less than k less than or equal to 4, k holds the values 1, 2, 3, 4. So 4 values. So when in the first case k value will be 1, second case k value will be 2, third case k value will be 3, fourth case k value will be 4. So C of I means 0, k is 1, 1 minus 1, 0, plus C of k, 1, J 4. This is the first case. Second case, C of I 0. Now I value, k value is 2, 2 minus 1, 1, plus C of 2, 4. Third case, k value will be 3. So C of 0, 2, 3 minus 1, plus C of 3, 4, k, j. And the fourth case, k value will be 4, C of 0, k minus 1, 3, plus C of k value is 4, j, 4. J value is 4. So plus weight of 1, 0, 4. So we need to calculate the minimum among these 4 cases. So what is the first one? So 0 plus C14. C14, it is a 19. C01, C01 is 8 plus C24, 24, it's again 8. And C02, 02 is 19. C34, it's a 3. C03, 03 is 25. And C of 44, it is 0. So among these, the second case we are getting the minimum 16, right? So plus it is 16. So which will be 16 plus 16, 32. So R of 0, 4, in which k value we got a minimum value? Second case k value is 2. So 16, 32 and 2, update here. So W of 04 is 16. C of 04 is 32. R of 04 is 2. Here 2. Right? So here we have completed the root nodes, finding of root nodes for each and every case. So the same thing we have applied in the first case also. That means first example in our previous session. But there we have considered only the successful frequencies. But here we are also considering the unsuccessful frequencies. So the calculation of this particular W weight will be different. Okay, that's the only difference. The formula of C is same and also root is same. Now we have completed this one and we know the root. What is the root? Okay, if the tree is having 2 elements, 3 elements, 4 elements, 1 element and 0 element. Now we need to construct the tree. Yes. Let us consider this one. Let us consider and let us draw the tree. So only thing is we have to consider it from R of 0, 4. Okay. So R of I, j. Sorry. This is j, which is a k value. So the left tree will be R of I, k minus 1. And right side element will be R of k, j. Okay, again it will be the k values. Whatever the result we are getting, that will be the k values. Consider this one. So R is having some 4 elements. That means the tree is having some 4 elements. We need to start from R of 0, comma 4. What's the R of 0, comma 4? 0, comma 4. It is 2. 2. So here 2 means the second element. So elements, these are the elements, right? So 1, 2, 3 and 4. Second element. Now the left is R of I comma k minus 1. 0 comma k minus 1. It's a 1. R of 0, 1. What is the R of 0, 1? R of 0, 1 is 1. So here it is 1. And now here it will be R of, so this is a k value, right? K comma j. 2 comma 4. So what's the R of 2 comma 4? R of 2 comma 4, it is a 3. 3. And this is a k value, and here this is a k value. Again, the left of this one will be R of 0 comma k minus 1, which is 0. What is the R of 0, 0? It's a 0. So there is no element. If there is 0, that means it is a no element. Okay. So here on the left hand side, R of, what's the k value? 1, j value 1. R of 1, 1, again it is 0. So we need to stop here. This is no element. Now consider this one. So R of 2 comma k minus 1, 2. 2 comma 2. It is again 0. We need to consider. Next, R of 3 comma 4. R of 3 comma 4. It is a 4. Right? And here we need to consider R of 3 comma 4 minus 1, 3. It is 0. Should not consider. Here this one, R of k. K means 4. So here it is a k. Okay. So 4 comma 4. Which is 0. So that is no. Now this is the optimal binary search tree. Now replace these k values with the corresponding elements. So here 2 means second element. So 20. Okay. On the left hand side, 1 first element. It is 10. On the right hand side, third element, that is 30. And see, again on the left hand side, it is 40. You can see the third element, fourth element. So this is the optimal binary search tree for the given example. You can observe here the root element will be one thing, and all the left subtree will be the less than root elements, and the right subtree will be the greater than root element. You can consider anything. 20. So left subtree 10, which is less than 20. Right subtree it is 30, which is greater than 20. And again 30 is having 40 on the right hand side. So 40 will be the greater than 30. So this is the optimal binary search tree we can construct from the given elements for both the successful searches and unsuccessful searches. Okay, so just remember this formula to construct the tree. R of ij, which is left hand side it will be I comma k minus 1, right hand side it will be R comma k comma j. So here the k means nothing but corresponding element numbers. Okay, root elements, right? So first we have to consider, or first we have to calculate what is the weight, cost and root. Based upon the weight we are calculating the cost, and based upon the cost we are selecting the root element. So for which for when the k value we are taking, we are getting the minimum cost, we are considering that element as a root element. So from this table we are constructing this particular tree. So this is the optimal binary search tree, so with a less number of comparisons. Today we will see one more concept in dynamic programming, that is all pairs shortest path. So we can consider any graph and we are supposed to find the shortest path between all the vertices, right? So for example, if the graph is in this format, right? So this is a directed graph then we have to find out the shortest. If you select the vertex 1, we have to find out the shortest path from 1 to 2, 1 to 3 and 1 to 4. So the shortest, there might be a direct edge between the 1 and 2. If not, we have to find the shortest path from 1 to 2 using some intermediate node. For example, so here you can see there is no connection between 1 and 3, right? So there is no connection. So there is an edge between 1 and 2 and 1 and 4, but there is no edge between 1 and 3. So this can be computed that 1 to 2, 2 to 3, right? So like that we have to find out the shortest path for all the vertices to all different vertices. So we have to consider first vertex and we have to find out the shortest path from this vertex to all the remaining vertex. And second, we have to consider the second vertex and we have to consider the shortest path from 2 to 1, 2 to 3 and 2 to 4, either direct or indirect. Direct means direct edge will be there, indirect means through intermediate node, right? And consider the third vertex and we have to find out shortest path from 1, 2 and 4. And consider the fourth vertex and find out the shortest path from 4 to 1, 2 and 3. So like that we have to find out the shortest path from one vertex to all the remaining vertices. So for this we are supposed to find the adjacency matrix, and from that adjacency matrix we are supposed to calculate all these things. So here we are using a one formula. Okay, so I'll write that formula first and then we'll apply that one, right? So I'll write the formula here. Example, A of 1 or K, A of K, that means the adjacency node K, right, is equal to, we have to consider a minimum of in between two terms. What is the first term? The first term will be A of K minus 1 I comma j, or A of K minus 1 I k plus A of K minus 1 k j, right? So we need to select either this one or this one. Simple logic. So this is a direct edge. Okay. So this will be the indirect. That means whatever the intermediate node we are taking. So if we are selecting 1 as a first vertex, so the k will be 1 itself, right? So by using the intermediate node, we are supposed to find the cost from I to j. Okay. So this is the thing. So I to j using intermediate via intermediate node k, right? Now, so this is ak of ij. So this is the main formula we need to do. So first step we need to find the adjacency matrix. So find adjacency matrix. So we need to give the cost from one vertex to another vertex. So while finding the adjacency matrix, if there is no edge, okay, if there is no edge from one vertex to another vertex, so fill it with infinity. If there is no direct edge, we have to fill it with infinity. And see, all self loops, self loop means if you consider the vertex 1, so what is the cost or what is the distance from vertex 1 to vertex 1? Similarly, vertex 2 to vertex 2, vertex 3 to vertex 3, right? So all the self loops should be filled with zero. So we have to remember these three things. First, we have to find the adjacency matrix. While finding the adjacency matrix, if there is no edge. So if there is an edge, directly we can give the distance there, right? So if there is no edge, fill the particular rows and columns with an infinity. So take the distance as an infinity. And for all the self loops, so from same vertex to the same vertex, right? So all self loops should be filled with a 0. So that will be A of 0, A of 0. Okay, that's an initial adjacency matrix. And then we have to find out A1. That means considering the first vertex. So in that adjacency matrix of A1, okay, so we are finding the shortest path from 1 to remaining vertices. So A1 means, so this is an initial adjacency matrix. A of 1 means shortest path from vertex 1 to remaining vertices. Vertex 1 to remaining vertices. Similarly, from this one we have to calculate A2. So from this one we have to calculate A1. Okay. From this one A1 we have to calculate A2. So A2 means the shortest path from vertex 2 to remaining vertices. Right? And this will be keeps on moving until it goes with the last vertex. A of n means the shortest path. So all these are adjacency matrix, right? So shortest path from vertex n to remaining vertices. Right? So this should be happens. Keep on moving until you find the adjacency matrix for all the vertices. Right? So just remember this one, and we are going to use this formula. You can see A of k. So initially that will be 0. Right? Initial adjacency matrix will be 0. A of 0. And from A of 0 we are supposed to find A1. So here k is 1 and k minus 1 is 0. K minus 1 is 0. K minus 1 is 0. So with the help of initial adjacency matrix, we are finding out the A1. And with the help of A1, we are finding A2. With the help of A2, we are finding A3. So that should be keep on moving until it reaches to the all vertices. So finding of shortest path for all vertices. Right? Now let us take an example. So I'll explain you. So let us calculate all these things, right? So let us take this example. So this is a small graph, directed graph. So the edges, the distance can also be a negative, right? The distance can also be the negative. So first let us write the initial adjacency matrix. So that is A0. So I'll write here. So 0, 1, 2, sorry, we'll write the vertices, right? So 1, 2, 3 and 4. 1, 2, 3 and 4. Fill out all those things, right? So 1 to 1, which is a self loop. Okay, so we have seen all the self loops should be filled with the zeros. So 1, 1, 0. 1 to 2. There is no edge from 1 to 2. There is an edge between 2 and 1. 2 to 1. There is no edge between 1 to 2. So if there is no edge, we have to fill with infinity. So 1 to 2, it is infinity. 1 to 3. Yes, there is an edge between 1 to 3, it is 1. The distance is 1. 1 to 4, no edge. So simply use infinity. 2 to 1. 2 to 1, there is an edge, the distance is 3. 2 to 2, it is a self loop, so fill with 0. 2 to 3. There is no edge, fill with infinity. 2 to 4, there is no edge, fill with infinity. 3 to 1, 3 to 1, there is no edge, infinity. 3 to 2, 3 to 2, yes, there is an edge, so 2. 3 to 3 is a self loop, so 0. 3 to 4, no edge. 4 to 1, it is 5. 4 to 2, infinity. 4 to 3, 9. 4 to 4 self loop, it's 0. So this is the initial adjacency matrix. So we are calling it as A0, adjacency matrix, initial adjacency matrix. Now what we have to do, we have to find out the A1. So with the help of A0. So A1 should be calculated. So A1 means we have to find the shortest path from vertex 1 to all remaining vertices. So for that we have to do, so we have to keep the first row and first column as it is in the adjacency matrix. Okay, so where A1 is used to find the shortest path from first vertex to all the remaining vertices. So we have to keep the first row and first column as a same, right? So A1 will be having the values, so 1, 2, 3 and 4, 1, 2, 3 and 4. So keep the first row and first column. So the first row is 0, infinity, 1, infinity, column 3, infinity, 5. And see, these are the self loops, we have to go with a 0. So we need to find all the remaining items, okay, remaining places. So what is this place? 2, 3. So A1 of 2, 3 is equal to, so minimum of AK minus 1, A1 minus G1, 0 of 2, 3 and comma A0 of 2, 1 plus A0 of 1, 3. So we need to find the minimum from these two things. Okay, so we have to find the distance from 2 to 3 from A0, and here we need to find the distance from 2 to 1 in adjacency, initial adjacency matrix plus 1 to 3. So that means we are finding the edge of 2 to 3 with 1 as an intermediate node. With 1 as an intermediate node. So you can find out here. So minimum of, so from A0, say A2 to 3, A0 2 to 3, this is a A0 2 to 3, it's a infinity. And coming to this one, A0 to 1, 2 1, 2 to 1, it is a 3 plus 1 3, 1 3, it's a 1. So you can see we have to consider minimum of infinity and 4. So what will be the final thing? So it will be 4. That means the distance from 2 to 3 is infinity initially. So by using the first node, first vertex, so visiting from first vertex, right? So 2 to 3 with 1 as an intermediate node, it can travel from 2 to 1 and 1 to 3 with a distance of 4. So there is, among these two, this one is a minimum, right? 4 is a minimum. So fill that one here. So this will be 4. This will be 4. Now, coming to the 2, 4, we need to find out the 2 and 4. So what we have to do? Again the same procedure. A0 of 2, 4 is equal to minimum of, so A0, A1, right? A0 of 2, 4, direct this one, and A0 of 2, 1 plus A0 of 1, 4. So we are taking 1 as an intermediate node between 2 and 4. So from this one you can find out minimum of, so from A0, what is a 2, 4? 2, 4, which is an infinity. And here 2, 1, 2, 1, it is a 3 plus 1, 4, 1, 4, it is an infinity. So simply you can see both are infinities. Both are infinities. So we can consider the infinity here. So I will consider infinity only. Okay, I will consider infinity only. So you can see from 2, 4, using 1, there is no path. You can see the graph. So from 2 to 1 there is a edge, but 1 to 4 there is no edge. So that's why we got infinity here. Okay. Then next, this one 3 2. So a1 of 3 comma 2 is equal to a minimum of a naught 3 comma 2 and a naught 3 comma 1 plus a naught 1 comma 2. 1 has intermediate node between 3 and 2. So you can consider here minimum of, what is the 3 2 distance? 3 2. It's a 2. And a naught 3 1. 3 1. It's a infinity plus 1 2. 1 2. It's a infinity. So among these, which is the minimum? 2 is the minimum. So just keep the same here, 2. Okay. Now you have to find out this one. 3 4. 3 4, right? So a dash of 3 4, which gives a minimum value of a naught 3 4 and a naught 3 to 1 plus a naught 1 to 4. So you can consider minimum in adjacency matrix 0 3 4 3 4, which is a infinity, and 3 1 3 1, which is a infinity, plus 1 4, which is again infinity. Again we got infinity only. So that means there is no edge between 3 and 4 also by using in 1, right? So we got infinity here. Next, this one 4 2. Hope you understood. Just we are applying the same in this formula. So a1 of 4 2. So minimum of a naught 4 2. Similarly a naught 4 1 plus a naught 1 2. So a minimum of, what is the 4 2 distance? 4 2. It's an infinity. Next 4 1 distance. 4 1, it is a 5 plus 1 2. It's an infinity. Right? So 4 1 is there, but 1 to 2 there is no distance. So again we got an infinity. Place the infinity here. And next one 3. 3. So a1 of 4 3. We need to find the distance for 4 3. So we can consider here minimum of a naught 4 3, and also consider 1 as an intermediate node and find out the path a naught of 1 3. So a minimum of, you can find the distance from 4 3 in a naught. 4 3, it's a 9, and 4 1 it is 5, plus 1 3 it is 1. So 9 and 6, it is 6, right? So by using 1, okay, from 4, by using 1 you can go with the 6 distance, you can reach 3. So 4 to 1 5, 1 to 3 1 6. So minimum distance is 6, you can simply place here 6. So this adjacency matrix gives that from vertex 1 the shortest path to all remaining vertices. Okay, now what we have to do? We have completed A1. Now we have to find out A2. Okay, A2. So what is this A2? Finding the shortest path from vertex 2 to all the remaining vertices. All the remaining vertices. For this also what we have to do? So we have to make use of A1 and we have to fix both the second row and second column. So what is the second row? Second row is 0 3 0 4 infinity. Second column infinity 0 2 infinity. And all the diagonals self loops will be 0. We know that. And we need to find the remaining. So what is that? This one? A2 of 1 3. 1 comma 3 is equal to a minimum of, what we have to do? We have to take the A1 because AK minus 1. So 2 minus 1 means 1. A1 of, what is this? 1 comma 3 or A1 of 1 comma 2 plus A1 of 2, 3. So we need to find the shortest distance, whether it is having 1, 2, 3 or by using the intermediate node 2. So here we are finding the shortest path from the second vertex. So the intermediate node will be 2. So we can find out here a minimum of, what's the value of A1, 3 from A1. This from here 1, 3, it is 1. 1 to 3, it is 1. A1, 2, 1 to 2, it is infinity, plus 2 to 3, it's a 4. So obviously this will be infinity, so this will be the minimum. So fill that one here, 1. Right? Next, A of 1, 4. Okay, we need to find A2 of 1, 4. So that will be a minimum of A1 of 1, 4 or A1 of 1, 2 using intermediate node plus A1 of 2, 4. So we need to select the minimum among these two. So from A1, what is the 1, 4 distance? 1 to 4 distance is an infinity. From A1, 1 to 2, 1 to 2 again it is an infinity, plus 2 to 4 again it's an infinity. So obviously what happens? Infinity. So place the infinity here. Okay. The next one. We need to find A2 of 3, 1. 3, 1. So what we have to find? So minimum of either direct edge from adjacency matrix 1 or by using the intermediate node 2, 3, 2 plus A1 of 2, 1. So what, is there any edge? 3, 1 from A1. 3, 1. It's an infinity. A1, 3, 2. 3, 2 is a 2 plus 2, 1. 2, 1. It's a 3. We have to find out the minimum among these two. Obviously it will be 5. So you can see the distance from 3 to 1. So distance from 3 to 1. Okay. There is no edge. So by using the intermediate node 2, there is a distance 5. So that's what we are finding out. So fill it with here 5 and next find out the value of 4, 3, 4. So A2 of 3, 4, which is a minimum of what we have to do? A1 of 3, 4 and A1 of 3, 2 plus A1 of 2, 4. So we need to find out the minimum among these two. So minimum of 3, 4 from A1, 3, 4 from A1 it is a infinity, 3, 2 from A1, 3, 2 from A1 it is 2 plus 2, 4 it's an infinity. So which is infinity. So from 3 to 4 there is no cost, 3 to 4. By using intermediate node there is no edge from 2 to 4 also. Therefore obviously we will be having infinity. And next we need to find two more values, that is a 4, 1 and 4, 3. So A2 of 4, 1 which will be a minimum of A1 4, 1 and A1 4, 2 plus A1 2, 1. So what we have to do? Minimum of 4, 1. What's the cost between 4 and 1? So 4 and 1, it's a 5. And 4, 2 with the intermediate node, 4, 2, it's a infinity plus 2, 1, 2, 1, it's a 3. So obviously this will be infinity and this will be the minimum, so 5. So you can simply take it as a 5. And now the next one, 4, 3. Find out the 4, 3. So A2 of 4, 3. So which gives the minimum value from the direct edge or using intermediate node. So A1 4, 3 or A1 4, 2 plus A1 2, 3. So from A1, what is that 4, 3? So 4, 3 distance is 6 and 4, 2 distance is infinity plus 2, 3 distance is 4. So obviously this will be infinity and this is a minimum, right? So 6 will be the result and that will be stored here. So this adjacency matrix indicates the shortest path from 2 to all the remaining vertices. Now what we have to do? Again we have to calculate the A3. A3. That means we have to find out the shortest path from third vertex to all the remaining vertices. For this we have to use A2. So 1, 2, 3, 4. 1, 2, 3, 4. So what we have to do, we have to keep the third row and third column in the same from A2. So from A2, what is the third column? So 5, third row, 5 to 0, infinity. Third column, so 1, 4, 0, 6. And we know that the self loop, we are having zeros. And we need to find out all these elements. So A3 of this one, 1, 2, 1, 2. We have to find out a minimum of A2 from the matrix 2, 1, 2, or A2 of, take the 3 as an intermediate node and find out the distance, A2 of 3, 2. So a minimum of, consider 1, 2 distance from 2, 1, 2, it's an infinity. And what about the next one, A2, 1, 3. A2, 1, 3, it is 1 plus A2, 3, 2. A2, 3, 2, it's a 2. So, which gives a 3. So, we need to fill the value. 3 is the minimum among infinity and 3. So, 3 should be here. So, you can check from 1 to 2 with the index 3. Okay, with the intermediate node 3. So, there is no direct edge from 1 to 2. So, in order to reach 2, what is the minimum cost? 1, 2, 3, 3, 2, 2. So 1, 2, 3 is 1, 3 to 2 is 2. So total 3, distance 3. Okay. Next, we need to find out the distance of 1, 4. So A3, 1, 4, which is nothing but minimum of, okay. So A2, 1, 4, and similarly A2, 1, 3 plus A2, 3, 4. So, from A2, 1, 4, what's the 1, 4? It's an infinity. Coming to this one, A2, 1, 3. A2, 1, 3, it is 1 plus 3, 4. 3 and 4, it's again infinity. Right? So, obviously, the result will be infinity, so you can just fill with the infinity only. Okay, so there is no path by taking 3 as an intermediate node, right? From 1 to 4. So, 1 to 4, you can go from 1 to 3. But there is no edge between 3 and 4. So obviously it will come infinity. The next one. 2, 1. A3 of 2, 1. So which gives a minimum A2, 2, 1 or A2, 2, 3 plus A2, 3, 1. So taking 3 as an intermediate node. So from adjacency matrix 2, 2, 1. 2, 1, it is a 3. And A2, 2, 3. 2, 3, it's a 4 plus 3, 1. It's a 5. So you can see we have to consider the minimum, right? Minimum. So obviously 3 will be the minimum. So we can have a path from 2 to 1. From 2 to 1, there is a direct edge, or with the help of 2 to 3 and 3 to 1. Okay. 2 to 3 and 3 to 1. So 2 to 3 means 2 to 3, it's a 4, right? How we are getting 4? So from adjacency matrix 1. So obviously from here we are not having 2 to 3, right? So if you want to reach 3, we can go with the 2 to 1 and 1 to 3. So for that we are having 4. So with that cost also we cannot reach 1 from 2, right? With a 3 as an intermediate node. So 3 and 9. So obviously the 3 will be the minimum value. So fill the 3 here. Okay, hope you understood. So here the edge from 2 to 1. There is 2 to 1, there is a direct edge. And we are also checking whether there is an edge with a minimum cost if you consider 3 as an intermediate node. So we are not having that one. Next. So A3 to 4 is equal to minimum of A2 to 4 or A2 2, 3 plus A2 3, 4. So you can check minimum of A2, 4. 2, 4. Sorry, this one. 2, 4. It is an infinity. Similarly, 2, 3. 2, 3. it's a 4 plus 3, 4. 3, 4, again it's an infinity. So obviously there is no edge, right? Next, 4, 1. We have to find out 4, 1. So, A3, 4, 1, which will select a minimum from A2, 4, 1 or A2, 4, 3 plus A2, 3, 1. So what we are doing? A2, 4, 1, 4, 1, it is a 5. And A2, 4, 3, it's a 6 plus 3, 1, it's a 5. So you can see there is a direct edge with a minimum cost, and if you are taking 3 as an intermediate node, the distance will be more. That means 11, it becomes 11. So we should consider only 5. So fill with 5. And again 4, 2, we have to consider 4, 2. So A3 is equal to, A3 of 4, 2. Which should be considered minimum value from A2, 4, 2 or adjacency matrix 2 with a intermediate node 3, 4, 3 plus A2, 3, 2. So minimum of, you can select A2, 4, 2. In A2, 4, 2, it is an infinity. A2, 4, 3, it is a 6 plus A2, 3, 2, 2, 8. So 2. So obviously it will be 8. So fill here 8. Okay. So hope you understood this one. Right? Next. Find out the A4, adjacency matrix 4, so that we have to consider right. So we have to make the fourth vertex, fourth row and fourth column as a constant, right? 5, 8, 6, 0. Similarly, infinity, infinity, infinity. So you can check 1 to 4. There is a no path, okay? So there is no path. If you go with a 2 also, there is no path. If you go with a 3 also, there is no path to 4. So that's why we got an infinity. And 2 infinity. From 2 also, there is a 2. And if you go with the intermediate node 1, so 2 to 1, there is no edge from 1 to 4. Here also, there is no edge from 2 to 3. Right? So obviously that will be infinity. Similarly, 3 infinity. So 3 to 4, there is no edge. If you consider 2 as a intermediate node, 3, 2, yes. From 2, if you take 1 as an intermediate node, yes. From 1, there is no edge to 4. So there is no connectivity from 3 to 4. That's why we got an infinity. So infinity means there is no path. There is no path. And see, coming to here, what we have to do? So the self loops, it will be zeros. And we have to find these things, right? So A4 of 1, 2 is equal to minimum of what we have to do. So A3 of 1, 2 or A3 of 1, 3 plus A3 of 3, 2. So making 3 as an intermediate node. Okay, sorry. It's a 4, right? So we are taking 4 as an intermediate node. So 1, 4 and 4, 2, right? So what we have to do, so minimum of, you can consider from A3, 1, 2. 1, 2 means it's a 3. And A3, 1, 4. 1, 4 is infinity. Plus 4, 2. 4, 2 is 8. So obviously 3 and infinity, 3 is a minimum. So you can fill it with 3. Okay. Next, find out the A4 of 1, 3. 1, 3 is equal to minimum of A3 of 1, 3 or A3 of 1, 4 plus A3 of 4, 3. So taking 4 as an intermediate node. So minimum of A3, 1, 3. So in A3, 1, 3, it is a 1. And coming to 1, 4, 1, 4, it is an infinity. plus 4, 3. 4, 3. It's a 6. So 1 will be the result. So here you can take it as a 1. Okay. Now coming to the next one. 2, 1. So A4, 2, 1. So it will be a minimum from A3, 2, 1 or A3, 2, 4 plus A3, 4, 1. So which will be taken as minimum of A3 to 1. 2, 1. It's a 3. A3 to 4. 2, 4. It's an infinity. Plus 4, 1. It's a 5. So obviously this is a minimum. So simply consider 3 here. And similarly, A4 to 3 is equal to minimum of A3 to 3 or A3 2, 4 plus A3 4, 3. And you can see the cost from 2, 3 in the adjacency matrix 3, 2, 3, it is a 4, and 2, 4, it's an infinity, plus 4, 3, it's a 6. So obviously this will be infinity and 4 should be taken, so 4 will be filled here. Okay. Next, 3, 1. So A4 of 3, 1, which will be taken from minimum A3, 3, 1 or A3, 3, 4 plus A3, 4, 1. So from this you can see minimum of A3, 3, 1. 3, 1, it's a 5. And A3, 3, 4. 3, 4, it's an infinity plus 4, 1. It's a 5. So 5 will be the minimum because infinity plus something will be infinity. So 5, we can go with the 5. And next, and the last one, A4 of 3, 2 is equal to the minimum of A3, 3, 2 or A3, 3, 4 plus A3, 4, 2. So what will be the value? Minimum of A3, 2. So in the adjacency matrix 3, 3, 2. It's a 2. 3, 4. See infinity plus 4, 2. Which is a 8. So obviously 2 will be the minimum. So you can write it as 2. Right? So this is the final adjacency matrix where all the vertices can be visited with the shortest path from one vertex with all other vertices. So you can see 1 to 1, 0. So 1 to 2. If there is no direct edge between, okay, there is no direct edge between 1 and 2. But the shortest distance is 1 to 3 and 3 to 2. The cost is 3. Okay, initially it is infinity. Now with the minimum cost 3, the person can visit from 1 to 2. Similarly, 1 to 3 there is a direct, 1 to 4 there is no edge, 2 to 1, 2 to 3, coming to 2 to 3. So if 2 to 3, we can reach 3 with a minimum cost with using 1 as an intermediate node, 2 to 1 and 1 to 3. So 3 plus 1, it's a 4. So this is the final adjacency matrix which gives the shortest path from one vertex to all other vertices. Right? So hope you understood. So infinity, here infinity means there is no way to reach from 1 to 4 by using intermediate nodes also. So you can see 1 to 4. So 1 to 4. So there is no outgoing edge from 1 to 2 or 1 to 4. There is an outgoing edge from 1 to 3. So you can consider 1 to 3 and you have to check whether there is an edge between 3 to 4. So from 3 there is no outgoing edge, you can observe. There is no outgoing edge. So it is impossible to reach 4 from 1. So in such cases we are filling with a infinity. The same case comes with a 2 to 4. So it is impossible to reach from 2 to vertex 4. Okay, in this example, in this particular example. So based upon the given graph, you have to draw all these things. So you have to find out all those things. So find out the initial adjacency matrix. With the help of initial adjacency matrix, you have to find out the A1 considering the first vertex as a constant, as an intermediate node, and finding all the shortest paths from 1 to all the remaining vertices. And from this A1, we have to find out the A2, which means taking 2 as an intermediate node and finding all the shortest distance from vertex 2 to all the remaining vertices. And after calculating A2, with the help of A2, we have to find out the A3, which means 3 is an intermediate node. Vertex 3 will be an intermediate node, and we are finding the shortest path from vertex 3 to all the remaining vertices. And after calculating A3, we have to find out A4, which means 4th vertex is the intermediate node, and we are finding the shortest path from vertex 4 to all the remaining vertices. So here we are having only 4 vertices, so we have calculated from A1 to A4. A0 is the initial adjacency matrix, right? So final A4 gives the shortest distance from one vertex to all other vertices. Today we will see the difference between the divide and conquer methodology and the dynamic program methodology. So first I will write divide and conquer, and here we will write dynamic programming. Dynamic programming. So already we have seen the methodology, how these works in our previous sessions. I'll post the link in the description so you can follow that one. And also we have seen different applications which follows this divide and conquer and which follows the dynamic programming. Right? So now we'll see what is the difference. The first is a common thing. So both are the algorithmic methodologies to find the solution for a problem. So the working or the working process is similar in both of these. So what is the first one? So here the problem is divided into subproblems. Divided into subproblems. That's the main thing. To find the solution, the complete problem will be divided into subproblems. The same thing will be applied here also. Okay, the same thing will be applied here. So here also a problem is divided into subproblems. Okay, but what is the difference? So here the solution for these subproblems are independent. So one subproblem will not depend upon the another. But that doesn't happen in this dynamic programming. The solution of one subproblem will be used in another subproblem. Okay, so here there is no overlapping. We are calling it as a overlapping if the subproblems are independent. Okay, based upon the dependency, we are calling it as a overlapping, right? So subproblems are independent. So which will not be dependent on other. That means here we can say no overlapping, or we can call it as a non-overlapping subproblems. Okay, but here what happens? The one subproblem will dependent on other. Okay, the solution of one subproblem may be used for other. So here subproblems are dependent. That means one subproblem will depend on another. So we can call it as a overlapping subproblems. We'll call it as a overlapping subproblems. Here there is no overlapping. There will be having a overlapping. Now here the combination, or after getting the solution for each subproblem, combining of these solutions will form the final solution. Okay, sometimes the solution of the individual subproblems may also lead to the solution. Okay, so solutions of subproblems. So we are saying every problem is divided into subproblems. So we need to find the solutions for subproblem. So solutions of subproblem combines to produce overall solution. Overall solution. That's the final solution. And sometimes the solution of only single subproblem may also lead to the overall solution. But here this is also same thing. Solutions of subproblem combines to produce the overall solution. So the same thing here. So solutions, and see here we should call it as a optimal solutions. Optimal solutions of subproblems. Optimal solutions of subproblems combines to produce optimal solution. Optimal solution. So that is the most important. So here in the divide and conquer, we can't say that solution is an optimal. Okay, there will be only one solution. So we can't say that is an optimal solution, and that will be obviously the optimal solution. Right? So whenever we are saying it as an optimal solution means, so whenever we are having a multiple solutions, among those multiple solutions, if we want to get the best solution, then we are calling it as an optimal solution. But divide and conquer is not like that. If you see an example, let us take some quick sort or a merge sort. Merge sort is a best example for the divide and conquer, right? So whatever the process we are using, we will be getting only one solution, which is the sorting of elements. So there are no multiple solutions there. For if you consider binary search, so we are dividing the complete solution into two halves, and we are processing only one category. That means only one half, and finally we are getting the result. So there also we are not having a multiple solution. There will be only one solution, whether the element is present or not. So here we will be having only one solution. There will be no feasible solutions. But in dynamic programming, we will be having the feasible solutions. So we need to select the optimal solution, and this optimal solution will be getting only combining of optimal solutions of subproblem. So we are saying that problem is divided into subproblems, and we need to find the solutions for this subproblem, and thus solutions are also should be optimal here. Right? So the next one. Solutions of subproblems will not be stored in memory. Solutions of subproblem. These solutions of subproblems will not be stored in a memory. But here the solutions, the optimal solutions of subproblems will be stored in memory, because so here we are supposed to retrieve the data whenever it is required, because each subproblem is dependent on another subproblem. So we need to combine all the solutions of all subproblems to get the optimal solution. So here the solutions of subproblems will be stored in a memory. But here the solutions of subproblems will not be stored anywhere else. Okay. And here, and this divide and conquer uses top-down approach. Okay, top-down approach. But here, the dynamic programming mainly uses a bottom-up approach. Bottom-up approach. So here, this process we are calling it as a memorization. Okay, and the applications of divide and conquer, and before going to the application, the time complexity. So the complexity will be more in divide and conquer when compared to the dynamic programming, because it requires a more number of computations, because all the subproblems are independent. So the recursive calls should be more in order to solve each and every subproblem, right? So it is less efficient than dynamic programming. And as it requires more computations. Okay, so because of independent nature, we need to calculate a more number of computations. But here that doesn't happen, because we are calculating, or we are solving the subproblem, and we are storing the solution in the memory. So whenever it is required, just instead of reconstruct or recalculate, we can automatically retrieve the data from the memory itself. So for that purpose, the efficiency will be high when compared to the divide and conquer. So here only comparing dynamic programming and divide and conquer, right? So more efficient than divide and conquer, as it avoids redundant computations. That means once you've done that, so that will be stored in a memory. So once again, we need not calculate the same thing, right? So we can make use of the existing. We can retrieve the data from the memory itself, right? So here, the last one, the applications. So what are the applications that uses this divide and conquer? We know that quicksort, binary search, merge sort, etc. Okay, lot of applications. And here the applications which use these dynamic programming is optimal binary search tree, OBST. Okay, optimal binary search tree. So that is the one thing we can use by using this dynamic programming. Okay, and etc. There are more number of applications which uses the dynamic programming, but among these two, the dynamic programming is efficient than the divide and conquer because of the overlapping subproblems. So it will be having a feasible solutions. So among the feasible solutions, we are selecting the optimal solution. Okay, so hope you understood the difference among divide and conquer and dynamic programming. We'll see the difference between two problem solving methodologies in algorithm, that is dynamic programming and greedy method. So the first one is dynamic programming, and the second one is greedy method. So we'll see the differences. So the first difference is which kind of problems we have to use this dynamic programming and this greedy method. So both are same. So that means both the cases, both the approaches can be used to solve the optimization problems. So where the problem should have the optimal solution, in such cases we are going to use this dynamic programming or the greedy method. So in order to solve the optimization problems, these two approaches will be used. So it solves optimization problem. And here also the same thing, solves optimization problem. So optimization problem means getting the best solution, optimal solution. So there will be a lot of solutions. So among that lot of solutions, we have to select the best solution. That is called the optimization problem. And the second difference is also same. So that means the complex problem will be divided into subproblems. So the second difference, problem is divided into subproblems. Coming to this one, here also divided into subproblems. And see which kind of subproblems these are. In dynamic programming, these subproblems depends on one to other. So there will be a dependency upon the subproblems. So that we are calling it as overlapping subproblems. So there will be overlapping nature. So these subproblems are overlapping subproblems. Whereas greedy method, no overlapping will be there. No overlapping. So that means here one subproblem will be depending upon other. That means if you want to solve one subproblem, it will take the result of another subproblem. And here there will be no overlapping. That means here the problem solving approach, is finding feasible solutions and selecting optimal solution. Finally, we will be getting the optimal solution. But here, at each and every stage, it will be selecting the optimal solution. Each and every stage. So, each stage, it selects optimal choice. Rather finding all the feasible solutions and selecting the optimal solution, it will be selecting the optimal choice at each and every stage. And here, so memorization will be there. That means the results will be stored in a memory. So the results of subproblems will be stored in memory, because as we are saying that this is a overlapping subproblems. If you want to solve one problem, it may require the result of another subproblem. So that's why, in order to avoid the recomputation, so it will store all the results of subproblems in a memory. We usually call it as a memorization. And here there is no option of backtracking. So results will not be stored because there is no overlapping, right? So results will not be stored in a memory. And one more difference. So in order to apply this dynamic programming, we'll be using bottom-up approach. So it follows the bottom-up approach. And here, so it will be using the top-down approach. And obviously, when compared to the dynamic programming, greedy method works fast. So it is slow when compared to greedy. When compared to greedy method, this will be slow. And when compared to dynamic programming, works fast. It works fast. Okay, and the next very important thing is the next important thing is guaranteed of finding optimal solution. So if you are using this dynamic programming approach, it is guaranteed that we'll be getting the optimal solution. But here, no guarantee of getting optimal solution. There is no guarantee, right? Because here each and every stage we are getting this optimal choice. So there will be no guarantee of getting the optimal solution in greedy method. But dynamic programming definitely will be getting the optimal solution. Okay, but time taking. It's a time taking process because we are storing the complete results in the memory. So some memory will be required to store and retrieve the data. But here results are not stored in the memory, right? So there is no concept of memorization. So that's why it will be very fast, but it will work with very slow. And some applications here we can say it is 0-1 knapsack. One such kind of application which will be using dynamic programming is 0-1 knapsack problem. So that means 0-1 knapsack problem means this problem will be having to solve the non-divisible products. Non-divisible products. So we can't divide them, right? So this can be worked with fractional knapsack. Fractional knapsack. So fractional knapsack means for all the divisible products. Fractional knapsack means all the divisible products. So these are the major differences among dynamic programming and greedy method. So only one thing, here it goes with the memorization, here there will be no memory. So that's why this works slow, this works fast, and it follows the bottom-up approach, it follows the top-down approach. And one major thing is there will be a guarantee of getting the optimal solution in dynamic programming. There will be no guarantee of getting the optimal solution in greedy method, right? So hope you understood. So both will be working for solving the optimization problems. That's the first and most important thing.
So graphs in a data structure is also similar to a trace, but here we can have a closed loop, right? So whereas in a tree we can't go with a closed loop, but here graph can have a closed loop, and here the graph is defined as a set of V comma E pairs, where V is a set of vertices, E is a set of edges. So a graph can be defined as a set of vertices and a set of edges. So every graph will be having a vertices and a edges. So vertices can be represented as circles, and these are also known as nodes. Edge is represented as lines, and also so lines which are connecting two vertices or nodes. Two vertices or nodes. So a graph can be defined as vertices and edges. So vertices are represented as circles and the edge is represented in the lines. So let us take an example for this graph. This is a simple graph. This can be called as a graph. So here B and C are vertices or nodes, and the connectivity between the vertices AB and AC are, so AB, A comma B, A comma C. These are called edges. So edges means the connecting two nodes, right? So this can be considered as a graph. And if you have a line between this B and C, so BC it also forms a pair, that means it is also an edge. So this is also a graph but not a tree. So in the absence of this one, in the absence of this edge, this can be either a graph or a tree, right? So if you have an edge between B and C, it is a closed loop, it's a closed surface, right? It forms a cycle. So if it forms a cycle, it cannot be called as a tree, it is a graph. That's the only difference between the tree and a graph, right? So here the nodes and edges. So let us see, first let us see the terminology of a graph, and then we will go with the types of graphs, different kinds of graphs. Graph terminology. The first one is node. First one is a node, which is nothing but a vertices represented as a circle, and then edge, which is a line, it's a connection between two different nodes, right? The third one is adjacent nodes. Adjacent nodes. So if you consider any edge, that means there will be, so let us take an example, A, B, and similarly A, C, similarly B, C. So there are three edges, right? Three edges. So for this edge, the node A and B are the starting and ending points. For this edge, the node B is the starting point, C is the ending point. For this edge, A and C are the end points for this particular edge. So that's why the adjacent nodes means which connects an edge, those nodes we call it as adjacent nodes. In this example, A and B are adjacent nodes. Similarly, A and C are adjacent nodes. Similarly, B and C are adjacent nodes. So this is how we can have the edge. So degree of a node. So how to calculate a degree of a node? So it represents the number of edges corresponding to that particular node can be considered as a degree of node. Number of edges connected to that node. For example, let us take this one, A, B and C, right? Now, degree of A, what is the degree of A? So, A is having two nodes, so degree of A is 2. So, degree of B is also having two nodes, so degree of B is 2. Similarly, degree of C is also having two nodes, 2. So, in the absence of this one, so degree of A is 2, degree of B is 1, degree of C is 1, because B is having only one node towards A, C is also having one node towards A. So that's why we call this degree as the number of edges connected to that node. Size of a graph. Size of a graph. So size of a graph represents the total number of edges, the total number of edges in graph can be considered as the size of a graph. So let us take this example. So there are 3 edges in this graph. So size of this graph is 3. So size is 3. What about this example? Only 2 edges are there. So the size for this graph is 2. So the total number of edges in the graph represents the size of a graph. Path. Path means the sequence of vertices, so from starting node to ending node. So sequence of vertices. From source node to destination node. Source node to the destination node, right? So let us take an example here. So if you take this one, A, B, C, D. So if you want the path from A to C, right? A to C. So this is the source, this is the destination. The path will be A to B to C, or A to D to C. So whatever the edges or the sequence of vertices from source node to destination node. So here the source is A and the destination is C. So we can have that the path can be A to B, B to C, or A to D, D to C. Right? So this is called a path. Okay. Then, so these are the basic terminologies we need to know before starting the graphs concept. So hope you understood the definition of the graph. So graph is a set of vertices and edges. Right? Now we'll go with the different kinds of graphs, different types of graphs. Types of graphs. So the first one, directed graph and undirected graph. Right. Directed and undirected. See, coming to this undirected, so there will be no directions specified on the edges. So let us take an example. So A, B, C, D and A. Let us take one more thing. So this one. Right? So this is also a graph. It contains vertices and edges. Right. So in this example, there is no directions specified on the edges. So we can travel from A to B or B to A. So here A comma B is equal to B comma A. Right? Similarly, B comma C is equal to C comma A. So that means there is no direction specified in this graph. So we can consider that A and B, A to B is one traversal and B to A is another traversal. So in both the directions we can travel, right? In both the directions we can travel. So coming to the directed graph, as the name indicates, so every edge will be having a specific direction. That means, so this we can call as a bidirectional, right? This we can call as a unidirectional. So in only one direction we can travel through the edges, right? See, let us take an example here. A, B, C, D, A. So this is called a directed graph because So here every edge is specified some direction. So only one direction we can travel. So there is a node between A and B. So A and B is not equal to B comma A, because here we have specified the direction from A to B, not from B to A. So here B to C. So direction is only from B to C. So B is the starting point and C is the ending point, but not the vice versa, right? So this is the only difference between the directed graph and undirected graph, right? So hope you understood. It's a bidirectional, it's a unidirectional. It's a bidirectional, it's a unidirectional. So only one way we can travel. So this is the difference between directed graph and undirected graph. Now we'll go with the another kind, right? Weighted graph and unweighted graph, weighted and unweighted. So here we have to specify some weight or a cost for the edge. See, let it be either it may be a directed graph or undirected graph. So there is no any cost specified for that edge. So here we can specify some cost for every edge. So in order to travel from A to B, the cost is 2. That means here we are specifying some weightage for every edge. So if you specify some weightage for every edge, that is called a weighted graph. So here weight is specified for every edge. No weight is specified. So either it may be a directed or in undirected, whatever it may be. So in the directed also we can have the weighted, and in the undirected also we can have the unweighted, right? So whatever it may be, if the edge is having any weight or a cost, then that graph is called as a weighted graph. And if the graph doesn't have any cost or weight specified for the edge, that is called unweighted graph. So this is the difference between weighted graph and unweighted graph, right? Now we'll go with the third one. Cyclic graph and acyclic graph. Cyclic and acyclic. So cyclic means it should perform the loops. Loop means, so if you find the path from source to destination, the starting point and the ending point should be the same vertices. I will show the example. So if you consider this one, find the path here. So here you can form, so A to B, B to C, C to D, and again D to A. So the starting vertex and the end vertex both are same. So that means it forms a cycle. It forms a cycle, right? So hope you understood this one. So if the starting vertex and the ending vertex are same, then that forms a cycle. And if our graph consists of the cycles, then it is called a cyclic graph. If our graph doesn't have a cycle, then that is called a cyclic graph. See, so here it doesn't form any cycle. It doesn't form any cycle. So this is called a cyclic graph. So similarly we can say this one. So if any graph doesn't have the loops, that we can call as a acyclic. So in the acyclic also, this graph can be either directed or undirected. It can be weighted or unweighted. So whatever it may be, if our graph consists of the cycles, then we call it as a cyclic. If it doesn't have any cycles, it is called as acyclic graph. Right? So hope you understood this one. So weighted, unweighted, directed, undirected, cyclic and acyclic. So these are the different kinds of graphs available in our data structure. Right? And also we have seen a few terminologies. So what is meant by an edge, what is meant by a graph, and what is meant by a node, what is meant by path, and degree, how to find the degree, how to find the size, and everything we have seen in this session. So if you are having any doubts regarding this terminology and different kinds of graphs, so feel free to post your doubts in the comment section, so that definitely I will try to clarify all your doubts. And if you really understood my session, like my sessions, share my sessions with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. So our topic is graph traversals. So what is meant by this traversals? So traversal means visiting all the nodes. That means traveling around all the nodes in the graph. So here we will not have any root node. So we can assume any node as a starting node. Any node as a starting node. And from that starting node we have to visit all the nodes without any repetition. That means every node of a graph should be visited only once. Right? Now we are having two types of techniques in this traversal, graph traversals. So the first one is depth first search traversal. It is called as DFS. And the second one is breadth first search. Which is called a BFS. Right? So based upon the depth we will travel all the nodes of a graph, that is called a DFS. Based upon the breadth, that means level. So we have to visit all the nodes of a same level, then only we will shift to the next level. So that in such a way we will go with the BFS. We will implement this BFS. So in order to implement this DFS and BFS, we will use the stack data structure. For implementing the DFS, we will use queue data structure for implementing the BFS. Right? So now let us take an example and we will see the procedure, how the DFS will work and how the BFS will work. It's a very simple topic. Right? Now, coming to this DFS. See, let us take an example here. A, B, C, yes. So you can go with this one. Okay. So you can go with this one. This is a graph. So graph is also similar to a tree. But a graph can contain cycles. That means loops. So this is a graph, of course. Alright. So now first let us assume this one is a start. So we can assume anything. Any node can be a start. Okay. I will assume that a start for simple understanding. Right. So I will visit one by one. Okay. So after visiting this one, so I will place a weight as 1. I have visited A, I have placed it as 1. Now I am coming to C. Right. So you can go with the B or C, anything else. Okay. Both are same. you can visit either B or C. So we can get a different outputs. Okay. So I will visit C. So the C weight is 1. Now from the C, again there are two adjacent nodes. So we can visit any one node. Okay. So I will go with the G. And the weight of G is 1. Now it is a leaf node. There are no nodes. Okay. There are no adjacent nodes. We should not say it is a leaf node. We are not having any adjacent nodes. So backtrack C and go with another adjacent node, right, and mark it as 1. So here also there is no adjacent nodes. Again backtrack, so again the node is visited, so go with the adjacent node. So B will be 1. Now again B is having two adjacent nodes. We can go with the D or E, anything. Okay, so I will go with the D. Mark as D1. Again, there are no adjacent nodes. Backtrack, right? Again, go with the E and go with the 1. So there are no nodes. Okay, there are no adjacent nodes. Backtrack and again backtrack. Again we came to the start node and there are no adjacent nodes. So this is how we can use this DFS. So first we have visited A, then C, then G, again backtrack C. So already C is visited, so we should not write C. Next F, right? Next, no adjacent nodes. Again C is visited. Again A is visited. B, and then we have visited D. No adjacent nodes. Backtrack B, already there. No E. So E, there are no adjacent nodes. Again backtrack to B. B is there. Backtrack to A. A is there. So there are no adjacent nodes. Any other adjacent nodes. So this is the DFS of a given tree. So right here. Okay. So this is the DFS for the given graph. Right? Now we will go with the implementation part. So for implementing this one, we will use the stack. So for the step 1, consider a stack and consider the DFS expression. Right? So starting node, push the starting node into a stack. So A will be presented here. So A is pushed here. Now pop the A and place it in the DFS expression. Right? So this is the DFS expression. So step 2. In the step 2, so popping the A and placing A here. Now place the adjacent nodes. Here. So we'll go with adjacent nodes B, C. Push the adjacent nodes of A. So what are the adjacent nodes of A? B and C. So we can write B, first we can push the B and then C, or we can push C and B. So if you push C and B, the output will be different. So both are same. So here both are the adjacent nodes, we can visit any node. Right. So next step we have to pop the, so already C is visited, so we have to pop the C and push the adjacent nodes of C onto the stack. So step 3, B, A and C. Now what are the adjacents of C? F and G. So F and G. Right? B, F and G. So we can write first, we can push first F and then G, or we can push first G and then F. Anything is correct. Okay. So I am pushing the F first and G in the next. Now remove the element and push the adjacent nodes of that node. So here G is a leaf node, right? So it doesn't have any adjacent nodes. So just pop that node and place in the DFS. So step 4, A, C, G, so B and F are there. B and F are there. A, C, G. Okay. Then step 5. Same. So here G is not having any adjacent nodes. Leave it. Now F. Remove the F and push all the adjacent nodes of F. So already the DFS expression is having A, C, G, and now we are placing F here. So F is also having no adjacent nodes. Leave it. Now B. Step 6. Stack is empty. A, C, G, F and B. So just pop the element and push the adjacent nodes of that element. So what are the adjacent nodes of B? That are D and E. So first I will push E and then D. So anything we can do. First D and then E, or first E and D, because both are the adjacent nodes. Right. So after that step 6. Now step 7. What we have to do? Again, pop the element and push the adjacent nodes into the stack. So here D is having no adjacent nodes. Just pop the element. So step 7, E, and in the DFS A, C, G, F, B and D. Right? Now only one element in the stack. The same thing, apply the same thing. Pop the element from the stack and place the adjacent nodes of that node into the stack. Here E is also having no adjacent nodes. So just after step 8, the stack is empty and the DFS traversal is B, D and E. Right? So stack is empty. Stack is empty. Right? So don't get confused. Just I have written empty. Okay. Okay. This is empty stack. Empty. Right? So if you observe this one, we got the same thing. A, C, G, F, B, D, E. So by using the stack, we can implement this DFS approach. Right? So this is one way we can implement this one. So one more thing I just want to say here, both are the adjacent nodes. Need not worry to push the order of, pushing the order of nodes into the stack. So we can follow any order. So you can push B first and then C next. We can push first C and then B, so that we'll get a multiple number of outputs. So if you push first C, so here we have applied, push operation first on B, then C. So we got this one. If you apply first C, then B, we'll get the next one, another one, another output. So don't get confused, right? So hope you understood this session, a simple DFS approach, depth first search. For implementing this depth first search, we'll go with the stack. So which is called a BFS. So in order to implement this BFS, we'll use the queue data structure, which is a first in, first out queue. So let us take the same example and then the same procedure is followed. So here also we have to visit all the nodes only once. So we can assume the start from any node, and then we have to start traveling, and we have to visit all the nodes only once. The same thing, we'll take that A, B, so the same example I am taking, D, E, F, G. Right. So first, travel from A, so mark it as 1. So then visit the adjacent nodes, all the adjacent nodes. So first 1, and there is one more adjacent node, 1, right? Then coming to the next level, visit the adjacent node of B, and then visit the adjacent node of E, backtrack, right, because there are no adjacent nodes here. So backtrack to A, again backtrack, come to C, so visit F and backtrack to C, visit G, backtrack to C, backtrack to A, so that all the adjacent nodes have been visited. So here we have to visit the nodes in level wise. So first complete the level top level, level 0, and then level 1, level 2, level 3. So top level we have to complete all the visiting all the nodes, then go with the second level, go with the third level. Now we'll go with the implementation. So here after visiting all these things, we'll get the same order A, B, C. So A, level 0, level 1, level 2. So level 0 visit the node, level 1 visit all the nodes, B, C, level 2 visit all the nodes, D, E, F and G. So we have to visit all the nodes level by level. So that's why we call it as a breadth first search. Okay, so in the previous session we have seen a depth first search. We have to go in a depth. Right. Now we will see how we will get this one with the implementation of queue. So step 1, so this is a queue and this is a BFS, queue and BFS. So first, so let us assume this one is a start node. Okay, the same thing, start node is A. So A, right, insert A into the queue. So this is a queue. Okay, step 2, remove the element from the queue and place in BFS. So as it is a queue where we have to remove the element, so both the insertion and deletion will be applied on same end. Okay, so sorry, so deletion will be from front end, insertion will be from back end, rear end. Okay, so A is removed and placed in BFS. Now insert all the adjacent nodes of A in Q. What are the adjacent nodes in A? B, C, B and C. So this is a BFS and this is a Q. So in the step 3, and remove the element from the queue. So here we have to remove the element from the front end. We have to insert the element at the rear end. Okay. So we have to remove the element. So the C will be in the top and place here A, B. Now what we have to do? We have to insert all the adjacent nodes of B into the queue. What are the adjacent nodes of B? D and E. So D, E. So the insertion will take place at the rear end. So this is a front. At the rear I have inserted D, and next at the rear I have inserted the E. So at the rear end I am inserting the nodes, adjacent nodes of B, because we are removing B here. Next, in the step 4, remove the element from the queue. Remove the element from the queue. So C is removed because the element is deleted from the front end. So D, E, A, B, C. Now what is the element we have removed? C. Now place the adjacent nodes of C into the queue. Place or insert the adjacent nodes of C into the queue, because we are removing C from the queue. So what are the adjacent nodes of C? F and G. So insert them into the queue, F and G. So apply the same procedure. Step 5. Right. So already A, B, C are there. Now remove the element. So deletion will be done from the front end. So D is deleted and placed here. Now there are only 3 elements, E, F and G. And we have removed D. So we have to add the adjacent nodes of D into the queue. So here D is a leaf node. So here D doesn't have any adjacent nodes. So just ignore. Next, follow the same procedure. Step 6. So A, B, C, D, and remove the element. So element is removed from the front end. So E will be removed, and we have to insert all the adjacent nodes of E into the queue. So what are the adjacent nodes of E? There are no adjacent nodes. Ignore. So there are only 2 elements in the queue. Step 7. Remove the element from the queue and place it in the BFS. So what is the element? F is removed here and placed in BFS. And we have to insert all the adjacent nodes of F into the queue. So there are no adjacent nodes for F. So remove, just remove. Next, step 8. Step 8. So A, B, C, D, E, F. So G is removed. So G is placed here, and we have to insert all the adjacent nodes of G into the queue. So there are no adjacent nodes for G. So here queue is empty. So this is the queue and this is the BFS. So the same thing we got here, A, B, C, D, E, F, G, A, B, C, D, E, F, G. So this is how we can implement the BFS, breadth first search, using queue. So hope you understood. So here we are visiting all the nodes level by level. So we have to visit all the nodes in level 0, then only we have to go with the level 1, then only we have to go to the level 2. Right? So here A is in level 0, so we have visited A in level 0. In the level 1, there are 2 nodes which are adjacent to A. So A, B, C. So we have visited B and C. And then we will go with the level 2 because only 2 nodes are there in level 1. In the level 2 there are 4 nodes and we have to visit all these 4 nodes before entering into the next level. So visit all these nodes because all these nodes are adjacent to B and C, all the nodes of level 1. So D, E, F, G. So we are visiting D, E, F, G. And go with the next level. So there are no other levels, right? Because level 2 is the last level. So this will be the answer. And this will be implemented by using the queue. Just insert the node into the queue and then first insert the node into the queue if the queue is empty. If not, remove the element or remove the node from the queue and enter into the BFS. Place it in the BFS and insert all the adjacent nodes of that particular node into the queue and follow the same procedure. So first we have inserted A and we have removed the A and placed it in the BFS, and we have to insert the elements of adjacent nodes of A into the queue. There are two adjacent nodes B and C, so B and C. Right? In the next step, we have to remove the element from the queue. So where we have to remove the first element from the front end. So from the front end, we will remove the node from the queue, and we will insert all the adjacent nodes of that particular node into at the rear end. Right? Because here we are using the queue, all the insertions will be done on front end, all the deletions will be done from the rear end. Right? So we have to delete the element and we have to place it in the BFS. So this is a very simple traversal technique, BFS, breadth first search. So this is also one problem solving technique which is used to solve the problems based upon the brute force approach. So it's a problem solving technique. Which follows the brute force. Brute force approach. So what is meant by this brute force approach? So brute force approach means checking all the possibilities to get the solution. So brute force checking all possibilities. Checking all possibilities. For example, so imagine you are having one lock and you are having some 5 keys. So you don't know the exact key which opens the lock. So what we'll do usually, so we'll try with each and every key. So at some point of time, so the lock will be opened with only one key among those 5 keys. That approach, that means without having any knowledge, just applying all possibilities is called the brute force. And here the backtracking will work with the help of a brute force, with some sort of additional technology will be used for this brute force to calculate, to solve the problem using the backtracking. So here the name itself indicates the backtracking means if the current position is not, if the current solution is not viable or is not proper, then immediately we can undo. That means we can backtrack to the previous point and we can go with the alternate path. Okay, so if the current solution, that means whatever the solution we have solved, right? If the solution is not suitable, then backtrack and choose alternate path. Okay, you can choose an alternate path. So mainly this algorithm is suitable whenever there is no time limit to find the solution for a problem. So this works well when there is no time limit. There is no time limit to find solution to a problem. Right? There is no time limit. Then only this particular backtracking will be possible. And here we'll be getting all feasible solutions. Here we'll find all feasible solutions. So we have studied about these feasible solutions, right? So one problem can have a lot of solutions, but based upon the constraints, we are supposed to select the optimal solution. So all possible solutions, we call them as a feasible solutions. So here we are supposed to find these feasible solutions. And the solution for a problem will be obtained step by step and incrementally using recursive calls. This is also most important. So here the solutions will be obtained by using recursive calls. So step by step solution will be taken as well as in the incremental fashion, so using the recursive calls, right? So the three possible categories where we are going to use this backtracking, right? So three categories where we use backtracking. So the first one, decision problems, and these are the problems so which will be worked with the help of a decisions, right? So all feasible solutions, a feasible solution can be considered as a decision problem. Okay, so this is a feasible solution. And the second one, optimization problems. Optimization problem. So we have studied about these optimization problems. That means we can have a lot of feasible solutions, but based upon the constraints given, we have to select the optimal, that means a best solution. So that is an optimization problem. So best or better solution. So the first one is a feasible solution, and that may not be an optimal. And coming to the second one, it is a best or a better solution, optimal solution. And the third one is enumeration problems. This is nothing but all feasible solutions, all possible solutions. So if you want to find all possible solutions for a particular problem, then also we are going to use this enumeration problems. That such type of problems we call it as a enumeration problems. And if you want to solve a problem and get the optimal solution, that is called as an optimization problems. And if you want to solve a problem to get a normal solution that may be optimal or may not be optimal, that is called as a decision problems. So this backtracking problem solving technique will be used to solve these kind of problems: decision problems, optimization problems, and enumeration problems. And in order to find this feasibility, feasible solutions, here we are going to find out the state space tree. This is most important. So what is a state space tree? So this is a tree with all possibilities. So we need to construct the tree. Tree means nothing but a path. Okay, a path with all possibilities. Either it may be a solution or a non-solution, right? So path with all possibilities. A solution which gives a solution or non-solution. So everything will be constructed in this state space tree. So with the help of this one, we are going to find out the solutions. So initially the backtracking will start with an empty set. Okay, initially the backtracking will start with an empty set, and after finding one solution, that solution will be added here. So this is nothing but the solution plus solution 1. So if it is feasible, then it will be inserted into this set. So it will be getting it as a S1. And afterwards, again the second solution. So if second solution is added here, so if it is feasible, second solution is feasible, then S2 will be added into this particular set. Otherwise, it will be just discarded, right? So these are nothing but a possibilities, possible solutions. S1, S2, S3, and so on. Sn. Let it be. All are different solutions for a single problem. So initial set is empty set. So if S1 is a feasible solution, so based upon our constraints, right, S1 will be inserted into a set. And if coming to the second solution, if it is not feasible, okay, if it is not feasible, it doesn't meet our constraints, then S2 can't be inserted here, so we can simply avoid this S2. Then S3, the next solution. If this solution is feasible, which obeys all the constraints given by the user, then S3 will also be added to the initial set. That means this set, right? So in such a way, only the feasible solutions will be added into this initial set, and the solutions which are not viable or not suitable, they will be discarded. Okay. Now let us see the algorithm, a simple algorithm, how the backtracking will be applied. Okay. Simple algorithm. So step 1, only the 3 steps will be there. Step 1, if the current position is the desired output, if it is a desired output, then success. Okay. Step 2, and if it fails, so else, and again if current position is not further explored or generated, then it is failed. That means if the path is not extended, okay, if the path is stopped, that means a dead end, then obviously we can say it as a failed. And step 3, else, that means this condition is also failed. If the current position is not a dead end, then backtrack with alternate path, explore and repeat steps 1, 2, 3. So again we have to repeat the same process. So one is if the current path or current position is the solution, that means a desired output, then we can stop, it is success. And if the current position is not further explored, right? So we are talking about the state space tree, right? So initial state, for example, it is A, B, C. Okay. Now, if it is a dead end, so we can say it is failed. If it is not dead end and it is again C, it is further explored, then we can backtrack and we can choose another path. Okay, so this is a way, and we can backtrack and we can go with the another path. And if it is here, then it is a dead end. It is not been explored further, right? But here there is an alternate way. If not C, we can move with the E. So that in such cases we need to backtrack and explore with the another alternate path. So this is a simple algorithm. So that means if we reach to the dead end, okay, and if there is no further exploration, automatically we can stop. If there is an exploration, we can just backtrack and move with the alternate path. Now, what are the applications of this backtracking? So we'll see the applications. What are the different applications? Applications of backtracking. So, by using this backtracking, we can solve the n-queens problem. N-queens problem. So, in our further sessions, we are supposed to solve this one, right? So, sum of subsets problem. Sum of subsets problem. Hamiltonian cycles or Hamiltonian paths. Finding Hamiltonian paths in a graph. Graph coloring problem. So, etc. All these are the different applications where we are going to use this backtracking. Okay. So, hope you understood the general method of this backtracking introduction. So, what is exactly the backtracking? So, it is similar to our dynamic programming, right? It is similar to our dynamic programming. In the dynamic programming also, we are supposed to find the optimization problems, right? Solve the optimization problems. And here also, we are trying to find the optimization problems. But if our current path is not suitable, then again we can backtrack and we can choose the alternate path. So, that is only one thing which is different from this backtracking and the dynamic programming. N-queens problem. So first let us discuss about what is a problem exactly, and then we can see how to solve it by using the backtracking methodology. So in our previous session we have discussed about the introduction to backtracking. So how we can proceed for the backtracking. So that means getting all possible solutions by using the brute force approach, and if one solution is not viable or not suitable, then automatically we will backtrack and we'll choose the alternate path. And by means of a state space tree, we are going to solve the problems by using the backtracking. So state space tree is a tree which gives all the possible paths, including the solutions and non-soluted paths. So now let us see what is meant by this n-queens problem. So arranging the queens in a checkboard or a chessboard, right? So we know that in chess game we will be having a queen. So usually we call it as a mantri. So we know the steps that can be done by the queen. So the queen can move towards a row, a number of steps, towards a column, number of steps, and towards a diagonal way, number of steps, right? So here the problem is how we can arrange the number of queens in one chessboard so that there will be no attacking mode. That means no two queens should be in a same row, no two queens should be in a same column, and no two queens should be in the same diagonal path. So there should be no attacking mode, right? So n queens means arranging queens on a chessboard or a checkered board, right? Chessboard without attacking mode. So that means without attacking mode means no two queens should be in single row or a same row. Similarly, no two queens should be in a single column, and no two queens should be in diagonal path. Diagonal path. So if we arrange the queens, number of queens, let it be 4, 6 or 8, whatever it may be. So we have to arrange the queens on a board so that no two queens should be in a single row, no two queens should be in a single column, and no two queens should be in a diagonal path. So for this we have to consider the n by n boxes, a table with n by n columns or cells, we can say, right? For example, if you consider 4 queens, so we need to consider 4 rows and 4 columns, right? See, so we need to arrange the 4 queens in this board so that no two queens should be in the same row. For example, 4 queens are Q1, Q2, Q3, Q4. For example, if I arrange Q1 here, I can't arrange Q2 here or here or here, because the steps that can follow the queen is towards the rows, towards the columns, towards the diagonal. So number of steps, n number of steps, this queen can move this side or this side or this side. So where we can keep the queen 2, so you can arrange queen 2 here. Okay, so here also this queen can move this side, this way, and this way, right? So in such a way we have to arrange all the queens so that no two queens should be in a single row or a column or a diagonal path. For example, if queen 1 is here and if queen 2 is here, so that will be a diagonal path. So this is an attacking mode. Okay, so if Q2 is placed here, that is also attacking mode. And if Q2 is placed here, this will also be attacking mode, right? So we have to avoid all these things and we need to solve the problem. That means we have to arrange the queens, the number of queens on the board. For example, here we have considered 4, so we need to arrange the queens in 4 by 4 checkerboard. And if we consider 8 queens, so that should be arranged in 8 by 8 checkerboard or a chessboard. Similarly, if you consider 16 queens, so that should be arranged in 16 by 16 table. So without the attacking mode. So in general we are saying that it has a n queens problem, right? So now we will see the 4 by 4, right? In order to easy understanding and in order to solve the problem very easily. So let us consider 4, and by following the same procedure you can practice with 8 by 8 so that you will be getting it. Okay, now so for solving this one we are going to use the methodology called a backtracking. So here we can have a multiple solutions. So here now I am not talking about the optimal solution. So solution, it's a feasible solution. That means whatever it may be, the source will be, the element will be reaching to the destination. Okay, so it is not an optimal. I'm not talking about the optimal solution, best solution, right? So all the feasible solutions are the answers for this n queens by using the backtracking. So there will be a number of possibilities. So in order to, while solving that one, if it may not lead to the solution, it will backtrack and go with the another procedure, another path. So like that we have to solve the n queens problem, and so I'll show you for 4 queens problem, right? So let us take the 4 queens problem and let us solve it. So I'll draw here. So I am taking 4 by 4 table. Okay, just now we have seen that we have to consider n by n table. So I am taking a 4 by 4 table. So 1, 2, 3, 4. Similarly 1, 2, 3 and 4. So these are the rows and these are the columns. And 4 queens, Q1, Q2, Q3, Q4, right? And now the problem becomes not n queens, it is 4 queens problem. Okay, now consider, so starting with the root, let us consider it as a root. So from root we can travel first here. I will go with so there are 4 columns, let it be 4 columns. If Q1 falls at first, okay, so that means place here Q1, then where the Q2 should be placed, so then let it be, if Q2 placed in 2, okay, because Q2 can't be placed in the first column, okay, so just here you can see no 2 queens in row, column, diagonal. Right? Now, if you place a Q2, now we have placed a Q1 at the first position, right? So starting with the first column. Next, where we have to insert the Q2. So if Q2 is placed here, okay, what is the problem here? You can see both the queens will be in the same column, violet this one, right? So we should not place here. And if you place here, so here, and then also the Q1 and Q2, for example, I write here, okay? Now see, Q1 and Q2 both place in the same row, so we should not place here. Q1, you should not place here. Q1, what happens here? Here also we can't place because diagonal. What about here? Yes, there is no problem. So here you can see both Q1, Q2 are not in the same row, not in the same column, and not in the diagonal position. Yes. So here we are placing Q2. So Q1, Q2. Q1 in the first column, Q2 in the second column. Okay. Next, what about the Q3? Q3. So what about here? Q3. If you place Q3 here, what happens? Q2 and Q3 are diagonal, so we should not place here. What about Q3 here? Again it's a diagonal, so we should not place here. What about a Q3 here? Yes. So we can't place Q3 here also because both in the same column, right? So this is a safe. So sorry, here also we can't place here, right? Q3 cannot also be placed here because Q1 and Q2 both equal, right? So see, there is no option for Q3 to place Q3. Hope you understood. So if you place Q3, it violates the same column. So if you place Q3 here, what happens? Diagonal. If you place Q3, again both are in the same column. And if you place Q3, diagonal. So there is no position to place Q3. So this path doesn't suit or doesn't give the proper solution. So backtrack. So here we can't place the Q3. Now go back. Go back. This is a backtracking. Go back and change the position of Q2. Change the position of Q2 because so if you place Q2 here, we can't place Q3 in the next one, right? Next step. So we need to backtrack and we need to change the Q2. So I'll change the Q2 here. So if I place Q2 here, diagonal, this is not possible, and if you place Q2, this is also not possible. So if I place Q2 here, yes, there will be no problem. Now the second path, Q2 in fourth position. So Q1 in first column, Q2 in fourth column. Yes. Now, so this is a backtrack. Okay, this is a backtrack. And now, what is the next step? Q3, where we have to place the Q3. So I'll write the boxes. Right? If you place Q3, again, both fall in the same column, so we should not place here. And if you place Q3, is there any problem here? No problem. So Q1, Q3 both are in a different rows and columns, and Q2, Q3 both are in different columns. There is no diagonal path, there is no column, there is no row. So Q3 can be placed in Q2, second one, right? So Q3 in the second one. Now, what about the Q4? Where we have to place the Q4? Again, I'll draw the same thing. So now we need to place the Q4, the last queen. Let us start with here. We can't place here, right? Because both fall in the same column. Here also both fall in the same column. There is only one position, Q4. There is only one position, that is the third position, right? So where we can place the Q4. But what happens? Again, Q3 and Q4 falls in the diagonal path. So this is also wrong place. And here we can't give the Q4 because again two queens will be in the same column. So this, if you place Q3 here, we can't place Q4 anywhere else. So it stops here. Again, backtrack. So we need to change the position of Q3. We need to change the position of Q3. So this is a backtracking, right? So it will be removed here. It should be removed here. Where we can place, there is no position here. So if you place a Q3 here, diagonal, in this position, there is no possible position to place the Q4. So this is also not correct position. And here also we can't do this. So again, go to backtrack. Right. So here we got the backtrack here. Again, there is no position. So backtrack to Q2. We need to change the position of Q2. So there is no possibility. If you place here, there is no possibility here. If you place here, already we have taken here. See, if you change the position of Q2 here, there is a diagonal. So we can't place here. If you place here, there is also violation of rule. So the only position is Q2, third position. Already we have done, but we are not getting the solution if you place Q2 in the third position. So again, backtrack. We need to change the position of Q1. So let us change the position of Q1 now. So move to the second one. Right? Then what about the position of Q2? So here we can't place diagonal, and in this position we can't place because both falls in the same column. Here also we can't place, and here we can place it. So Q2. Q2. Then what about a Q3? Okay, Q3. So there is only two possibilities, Q3 in this place and in this place. So Q3, Q3. What happens? See, so this is a diagonal, so we can't place here. What about here? Yes, we can place a Q3 here. There is no violation of rules because no other queen is available in the same row, same column and diagonal. So Q3 can be placed in first position, and from this we can go with the Q4. Now Q4. So only one option. If you place Q4, is there any problem here? So there is no problem. So you can observe no two queens fall in the same row or same column, either in the diagonal. So there is no attacking mode here. So Q4 can be placed in 3 with a safe, without any attacking mode. So you got a solution here. So placing the Q1 in 2 placing the Q2 in 4, placing the Q3 in 1 and placing the Q4 in 3. So this becomes one possible solution. This becomes the one possible solution in order to place or arrange the 4 queens without any attacking mode. Right? So what happens here? So we have started from the first position. We have started from the first position and we have gone through, but there is no place of Q3 without any attacking mode. So we have taken the backtracking. We have taken the backtracking and we have changed the position of Q2. Sorry. So here we have backtracked this one. Okay, we have changed the backtrack here, right? So the backtrack will be this one, right? Backtrack. And similarly, we changed the Q2 position from third column to fourth column. And again, we have started the procedure, but here we got a problem for Q4, arranging of Q4. So we have backtracked to Q3, and even we can change the position. We didn't get the location where we have to place the Q4. So again, backtracked, and again we have changed the position of Q1. So what happens for finding the solution? If we are not getting the perfect solution, just we are backtracking and we are keep moving on to the next alternate path, alternate solution. Okay, so this is how we can solve the n queens problem. Okay, the same thing you can apply by using the state space tree. So this is not only the solution, there might be multiple solutions. Okay, there might be multiple solutions. For example, if you draw the state space tree for this one, see, one is a root. From this root, there are 4 possibilities. 4 possibilities. Q1, the first level is a Q1, placing of Q1. Okay, so if the Q1 is placed in a first column, second column, third column and a fourth column. 4 possibilities. Okay, after that, from Q1 we can get 3 more paths. Q2. And from here also we can get 3 more paths. Q2. 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 From here also we can get 3 more paths. Q2. 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 And from here also we can get 4 more paths. 3 paths. That means, see, possibility. So if Q1 is at 1, position 1, in the second column, if you place Q2, third column, fourth column. Second, here the first column, second, third column and fourth column. Here first column, second column, fourth column. First column, second column, third column. So all the possibilities. So 1 in Q1, 2 in Q2. 1 in Q1, 3 in Q2. So like that. And similarly, from here again we can have a Q3, and here also 2 possible things. Q3, see, this is the state space tree for 4 queens. That means these are the lot of all the possible paths. So some may have the possibility solutions, feasible solutions, and some may not have the feasible solutions, right? So previously we have gone through the directly backtracking method, and we found one solution, that is placing of Q1 in second column and placing of Q2 in fourth column, placing of Q3 in first column and placing of Q4 in third column will give the arrangement of queens without the attacking mode. But here you can see all the possible paths. So 1 in Q1, 2 in Q2 and 3 in Q3 and 4 in Q4. So we can check all the possibilities here, right? So let us take these possibilities. For example, consider this one by using the state space tree. How we can find out? See, first possible paths 1, 2, 3, 4. So placing Q1 at 1, placing 2 in a Q2, Q3, Q4. So this completely violates the rule because we have said that no two queens should be in the same row. But here all the 4 queens will be in the same row. But that is one possible path. So this is not valid, right? So this path is not a valid path. So we may not consider this one. We may not consider this one, right? Now, second possibility. What is the second possibility? So let us check the second possibility here also. So place the Q1 and 3 in Q2. See, 2, yes, 2 in Q2, sorry, Q3. Okay, and 4 in Q4. So again it violates the rule, right? Diagonal. So this possibility is not possible, right? So this possibility is also not, this path is also not possible, right? So like that we can check each and every path here and we can find out the solution. So one solution, let us check one solution. So we found that 2. So Q1 in 2, right? So whatever the solution we found, just we will see Q1 in 2 and Q2 in 4, Q2 in 4, Q2 in 4 and then Q3 in 1, so Q3, so Q3 in 1 and similarly Q4 in 3. So this is a possible path. This is a possible path. So we will see one more possible path. So just a reflection 3, 1, 4, 2. Right? So let us check the reflection, mirroring, right? So placing Q1 in 3, Q1, Q2 in 1, Q2, Q3 in 4. Sorry. Q3 in 4. Next Q4 in 2. So this is also one possible solution. So here also we didn't get any attacking mode, right? So we have placed the queens so that there is no attacking mode for all the queens, right? So like that, this is the complete, this graph is somewhat clumsy, please excuse me. So these are all the possible paths, okay? How many ways we can arrange the 4 queens in this particular checkbox. And from this, so some may have the possible solution, feasible solutions, and some may not lead the solutions. So like this, we can find the possible solutions in a solution set. So here we are not talking about the feasible, optimal solution. So we are talking about just the feasible solutions. What are the feasible solutions, right? So this is a small example for solving the 4 queens problem. So just try the method for 8 queens problem, to solve the 8 queens problem. So that today we will see one more concept in backtracking, that is a sum of subsets problem. Sum of subset. So we know that a subset, right? So we'll take a set of elements, some x1, x2, x3 and so on, xn, and from this particular set we are supposed to find out the subsets, right? So all the combination of subsets, right? Let it be x1 comma x2 is one subset, x1 comma x3 is another subset, x1, x2, x3 are one subset, and similarly so on. There will be a lot of combinations, right? So here what we have to do is we need to consider a sum, right, which is denoted as m, and we need to form the subsets whose sum is equal to this m, right? For example, let us take 3, 4, 5, 2. So these are the elements in the set. Okay, these are the elements in the set. Now the total sum is 9. So we need to form the subsets where the sum of elements of that particular subset should be equal to 9. So here you can see 3, 4 and 2. So this is a subset of this main set whose sum is equal to 9. Similarly 4 comma 5. 4 comes before now. So 4 comma 5. This is another subset whose sum is equal to given 9. If m is equal to 8, we need to form the subsets where sum of all the elements of subset must be equal to 8. So it will be 3 comma 5. Any other possibilities, any other solutions? No, there is no solution. So to find these subsets where sum is equal to given total is the problem of this sum of subset problem, and this will be implemented with the help of backtracking. So we have studied about the introduction of backtracking, and also we have seen one example of one application of backtracking, and here we are supposed to find the sum of subsets using a backtracking. So in this backtracking we are supposed to use the brute force. Brute force means checking all possibilities, right? And we need to find out the state space tree. So in this state space tree we will get all the combinations. So some paths may lead to the solution, some paths may not lead to the solution. So all the possible paths which may lead to solution and not solutions will be there in this state space tree. From there we will be getting the solutions, and here we are not finding the optimal solution, but we are finding all the feasible solutions. So here we can see this is not an optimal solution, because optimal solution is only one solution, best solution. So in this backtracking we are not finding the optimal solution, but we are finding all possible solutions. So in this one we can get the 2 possible solutions, right? Now we'll see the state space tree first, and then we'll write the step by step procedure, right? So we'll take the same example, and I'll draw the state space tree so that you will be getting the solutions, right? So let us consider it as W. So by observing this, you may having an idea about the 0-1 knapsack problem. So there also we are taking weights and a profit. So we need to consider the optimal solution by considering less number of weights with a more profit, right? So the same way here we are calling them as elements, and we are simply finding the sum of subsets. So the elements are 3, 4, 5 and 2, and m means a total which must be equal to 9. Yes. Now we are supposed to find the solution, state space tree, right? For example, consider them as x1, x2. So if x is equal to 0, that implies not consider. If x equal to 0, that implies not consider. If x equal to 1, it implies consider. So we need to check each and every possibility for all the elements with inclusion and without the inclusion. That means with consideration and without consideration, we need to find out the state space tree, right? See, first let us take the sum as 0, okay, right? 0 subset, and weight is 9, sum is 9. So this is the root. That means subset with 0 elements. Subset with 0 elements. Now, let us consider
if you add one element, the first element, for example, let us consider only first element. What is the first element here? I'll write here x1, x2, x3, x4. 4 elements are there. Consider x1. x1 is equal to 1. So if x is equal to 1, we are considering, right? So what is the first element? 3. So 3 will be added into this one, and from the weight we need to reduce the, from the sum we need to reduce the weight. What is the weight? 3. So 9 minus 3, it is 6. So we are considering two arguments. One is a subset, another one is a weight. Now check whether the sum of subset is equal to 9. No, right? So we can again further consider. See, x2 is equal to 1. Always this backtracking will be following the depth first search. Okay, this is most important. Always we need to find in a way that depth first search. So this element we need to find out this element. Now x2 is equal to 1. That means second element should be considered. So now the subset will be having 3, 4. And 4 will be reduced from 6. So it will be 2. Consider 3 plus 4, 7, which is not equal to 9. So it can be further down, right? Again depth first search. x3 is equal to 1. We can consider x3 also because the sum is less than 9, right? So x3 is 5. So here 3, 4, 5. 5 minus 2 minus 3. You can check the weight goes to the negative. So that implies the sum of subset is greater than the target value. So let it be, this is a target. Sum of subset is greater than the target. So we should not consider this one. So this is not a feasible, right? So not feasible. So what we have to do? We need to backtrack and move with the another direction. So backtrack towards this one and let us consider x3 is equal to 0. That means without considering x3. Without considering x3, so we are moving with 3, 4, 2. The same thing will be appear here. Again depth first search. Again you have to go with the depth first search. Now x4 is equal to 1. Okay, x4 is 2. Consider 3, 4, sorry, we have to consider 2 also. 2 and 2 minus 2, it is 0. You can say that sum of subset 3 plus 4 plus 2, it's 9, and also the target, the total value is 0. That means 9, right? So this is one solution. We got a solution, so we can stop here. And we need to find another possible solutions, right? So we need to find all the possibilities. So backtrack and consider if x4 is equal to 0, then it will be 3, 4, 2. What is the sum of subset? It is 7. So it can be further executed, right? Further evaluated, but it reaches to the last element. So not feasible. Not feasible. So what we have to do, if it is not feasible, we need to backtrack. So move to the backtrack, and here again there is no position. So again backtrack, and again backtrack, and here you can consider x2 is equal to 0. So previously this path is considering x1, x2 0. Now the path, the elements are 3 and 6. From this again we need to find the depth first search. Consider x3 is equal to 1. Okay, depth first search means left side root. So x3, what is the third element? It is 5. Now 3 comma 5, 1. So we need to reduce the weight from the target sum. So 3 plus 5, it is 8. Again, still it is less than the target. It can again furtherly divided, right? x4 is equal to 1. So consider x4, 3, 5, x4 is 2, it is minus 1. You can check the total value, it becomes 10, which is greater than 9. So this is not feasible. This is not feasible. Backtrack and possible position. x4 is equal to 0. Without considering x4, it will be 3 comma 5, 1, and this cannot be further divided because x4 is the last element. So this is also not feasible. Again backtrack, this was completed. Again backtrack, and here we can consider x3 is equal to 0. x3 equal to 0. x3 is equal to 0 means again we will get 3, 6. So sum of subset 3, which is less than 9, further divided. So again x4 is equal to 1. So 3 comma 2 comma 4. What happens here? Sum of subset is 5. It can't be further divided because this is the last one. So this is not feasible. Similarly backtrack. So without considering x4 is equal to 0, this becomes again 3 comma 6. This is also not feasible. It can't be further divided because this is the last element. Now again backtrack. Check all the possibilities. No, here also there is no possibility. Backtrack, and again it moves to backtrack, and now we are supposed to consider x1 is equal to 0. So this complete path, these are all the possibilities when we consider x1 is equal to 1, and we need to consider the second one, that is x1 is equal to 0, right? So if x1 is equal to 0, the set will be again empty set with a 9, and we need to follow all the same things. So again consider x2 is equal to 1. What is x2? 4. 9 minus 4, it is 5. Sum of subset is less than 9. So further divided. x3 is equal to 1. Let it be 4 comma x3 is 5. Okay, and it will be 0. Right? What happens? 9. 9 becomes 9. So this is one solution. This is one solution. So I'll mark with a double circle, right? This is one more solution, and we need not move further. So backtrack for alternatives. Again x3 is equal to 0, not considering. So it will be 4, 5. Again further can be divided. So x4 is equal to 1, 4 comma 2 comma 3. It can't further divided because x4 is the last element. So 4 plus 2, it says 6, not equal to 9. So this is not feasible. So backtrack and check with the alternative. x4 is equal to 0, and it will be 4 comma 5, which is also not feasible. Now again move with the towards a backward, and here, and consider now x2 is equal to 0. x2 is equal to 0, right? Now what happens? Again empty set with 9. x3 is equal to 1. x3 is 5, 4, So 5, sum of subset is 5, which is less than 9. Further it can be divided. Consider x4 is equal to 1, 2. So then it will be 5 comma 2. So which is not further divided. So it is a not feasible. It's not a feasible. So move towards backtrack and consider x4 is equal to 0, and it will be again 5, 4, which is also not feasible. Not feasible, right? Again backtrack, and now I'll write here, right? So consider x3 is equal to 0, x3 is equal to 0, x3 is equal to 0 means again it will becomes 9. So again it can be further divided. So x4 is equal to 1, so it becomes 2 comma 7. It's not feasible. Backtrack, again x4 is equal to 0, it will be blank, and 9, which is not feasible, right? So we are having only two possible solutions. One is 3, 4, 2 and 4 comma 5. Okay, manually we have seen all these things, right? Now the solutions will be, what are the solutions? How we can write down the solutions? So one is 3, 4, 2, 3, 4, 2, right? So this can be represented 3 comma 4 comma 2. This can be represented as 1, 1, 0, 1. 4 elements. We are considering the first element, second element, and we are not considering the third element, and again we are considering the fourth element. So 3, 4, 7 plus fourth element 2, total becomes 9. Similarly, the second one, it is a 4 comma 5. So this can be represented as 0, 1, 1, 0. So this is not a binary. Okay, don't get confused. This is not a binary representation. So this represents which element should be considered and which element is not to be considered, right? So again this becomes 9. So these two are the solutions of sum of subset problem for a given example, right? So what we are doing, so first we are starting with an empty set. We are inserting or adding one element to the empty set, and we are checking whether the sum of subset is equal to the target sum, and if it is not, or if it is less than, it can be further evaluated. That means again we can add one more element and we can check the total sum with the target sum. And if it is also not equal, if it is equal, then we can stop and we can consider that as a solution. And if it is not equal and it goes beyond the target, then obviously we have to stop and we have to backtrack and we have to select the alternate path. So in this state space tree, you can see we have considered all the possibilities. So some paths are not feasible. So you can check this path is not feasible, and this path is not feasible, this path is not feasible. So this state space tree will be having all the paths which leads to the feasible solutions and not feasible solutions. And backtracking is mainly to identify the multiple feasible solutions, not to the best or optimal solution, right? So hope you understood this one, and practice with a more number of examples so that you can understand and you can get a complete clear-cut idea about this sum of subset problem using backtracking. So today we will see one more application in backtracking, that is finding Hamiltonian cycles in a graph. Hamiltonian cycles. So this is also one of the applications of backtracking. So backtracking main motto is to find all the feasible solutions, not the best solution, using backtracking. Okay, so we'll check all the possibilities
And if one possibility doesn't suitable, the solution is doesn't suitable and it does not lead to the feasible solution, we are supposed to backtrack and we'll start with the alternate solution. Right. Now coming to this particular Hamiltonian cycles, let us consider a graph. Okay. See. Let us consider this graph. Let us consider this graph. So this graph means a combination of vertices and edges. Okay. So this is a graph and this graph forms a cycle. Right. So forms a cycle and this graph will be having a lot of cycles. But here our main problem is finding of Hamiltonian cycles. So what is meant by Hamiltonian cycle? So consider a starting vertex, visit all other vertex at least once, exactly once, and come back to the original vertex from the source vertex. So this called as a Hamiltonian cycle. So I'll write what is a Hamiltonian cycle. Start from source vertex, visit all vertices exactly once, and come back to source vertex. This is called a Hamiltonian cycle. So we need to find out how many Hamiltonian cycles were there in this particular graph by using backtracking. Okay, so the same thing we have learned somewhere else, right? Yes. So the same problem, that means starting from source vertex, visiting all vertices exactly once and coming back to the source vertex, is a solution of the traveling salesperson problem. But there we have to solve this with a minimum cost. That means the traveling salesperson have to start from the source vertex, visit all other vertices in the graph and come back to the source vertex with a minimum cost. So there also will be getting a lot of cycles, lot of paths, but we are going to select only the optimal solution, right? But here we are finding all the possible paths. Okay, so this is a Hamiltonian cycles. So how we can find out these Hamiltonian cycles? See, let us start with the source. Let us consider this source. Don't change the source. So if you change the source, the cycle may be equal, right? So we should not consider that one. Fix the source vertex and find out all possible paths, feasible solutions. So let it be. So first I will write the outgoing edges, okay, of every vertex. For example, consider A. So A is having outgoing vertices to B and C. B is having the outgoing vertices A, C, D. A, C and D. And C is having outgoing vertex A, B and E. A, B and E. So it will be very easy. Okay. So D is having the outgoing vertices B, E, F. B, E, F. And E is having the outgoing vertex C, D, F. C, D, F. And F is having the outgoing vertices D and E. So with the help of this one, so usually we call it as an adjacency matrix. Okay, adjacency matrix. So instead of writing the adjacency matrix, I have written the complete nodes, adjacency nodes, right? Now start with the vertex, source vertex. So let it be my source vertex is A, right? A. So here
we are starting from source vertex A and we have to visit all other vertices exactly once. So from A, what are the outgoing edges? B and C. Let it be. This is B and this is C. And we know that the backtracking will work on depth first search. So first we need to find out the depth. So yes, A and C. Now B, what are the outgoing edges? A, C and D. See, A, C and D. A is already visited because we are at B from A itself. So A is visited. So you need not consider A. So what are the outgoing edges? C and D. So C, D. Okay, C and D. Now we need to find out the depth. So C. C is A, B, E. So A, B were already visited. So if you are at C, we are from B. If you are in B, we are from A. So A, B are already visited. So only one vertex is not unvisited, that is E. So C is having E. Now check this E. E is having outgoing edges C, D, F. Among that, C is already visited. So there are only two possibilities, D and F. So D and F. Coming to D, B, E, F. So E is there, B is there. There is no F. So here we can have F. So F, D, E already visited, right? Now you can observe in this path A, B, C, E, D, F. So how many nodes are there? 1, 2, 3, 4, 5, 6 nodes are there. So you can see 1, 2, 3, 4, 5, 6. All nodes have been visited. So here the last step is F is the last node visited. So we need to check whether there is an edge between F and A. Then only it forms an Hamiltonian cycle. So start with the source vertex, visit all other nodes exactly once and come back to the source vertex. So start from the source vertex, visited all vertex exactly once, and now it have to visit back to source vertex. So F having edges D and E. So there is no direct connection from F to A. So this path is not feasible. So backtrack. So there is an alternate way. Okay, here from F there is D and E. In this path, check whether D and E have been visited or not. E is already visited, but D is not visited. So there is a path from F to D. Again check. So here you can see 1, 2, 3, 4, 5 and 6. So all nodes have been visited. And now it should go back to source vertex. So check whether D is having an edge to A. So D is having no edge to A. So this is also not feasible. So again backtrack. So here also one possibility, backtrack, and there is another possibility. So A, B and D. So from D, check B, E, F. B is already visited. So E and F. E and F. Now E. So depth first search, right? E. C, D, F. D is visited. So C and F. So here it will be C and it will be F. Coming to C. Edges are A, B, E. Check out. A is there, B is there, E is there. So how many nodes we have visited here? 1, 2, 3, 4, 5. So this is not feasible because there is no edge from C. Okay, because C is having an edges towards A, B, E which are already visited. A, B, E in this path. So backtrack and follow this one. Okay. F. So from F there is an edge between D and E. So in this path A, B, D, E, F, check whether D and E are visited. Yes, D and E are visited. Now count the nodes 1, 2, 3, 4, 5. So total nodes are 6, but only 5 are visited, and there is no other edge which is used to visit the unvisited node. So this is also not feasible. Backtrack, and go with the another possibility. So in order to reach F, we have to travel from A, B, D, F. So from F there is a D and E. So in this path, D is already visited. We have to visit E. So there is one path. It is E. Now from E there is a C, D, F. Check. D, F are already visited. There is no edge to C here. So the next one is C. And you can check C, A, B, E. So A, B, E, all the three have been visited in this path. Now we have to check whether the 6 nodes have been visited. So 1, 2, 3, 4, 5, 6. Yes, all the nodes have been visited. So there might be a chance of having the Hamiltonian cycle. So there should be an edge from C to A. Then only we can say that is an Hamiltonian cycle. So check out C. A, B, E. So there is an edge towards A. So this is the one possible solution. So it forms a Hamiltonian cycle. And now go with the backtrack and move with the alternative. Next alternative, C. A, C. So C is having an edges from A, B, E. A is already visited. So there will be edges from B and E. Now B, depth for search. B is having edges towards A, C, D. A, C has already visited. So D. D, B, E, F. B is already visited. So E and F. E, C, D, F. C, D is already visited. F. F, D, E. D, E is already there. Now check the total number of nodes. 1, 2, 3, 4, 5, 6. So all nodes have been visited. So there is having a chance of getting the Hamiltonian cycle. So check out the edge from F to A. If there is an edge from F to A, then we can say this is a Hamiltonian cycle. So F didn't have the edge from F to A, right? So this is not feasible. Backtrack, go with the alternate solution F. So coming to F, D and E. So D is visited in this path, but E is not visited. So you can write it here, E. Now check E with C, D, F. C is there, D is there, F is there. So all nodes have been visited. So count the nodes. A, C, B, D, F, E. Total 6 nodes were there. So that implies there is a chance of getting Hamiltonian cycle. So we can say this is a Hamiltonian cycle if there is an edge between E and A. So E doesn't have an edge towards A. So this is also not feasible. This is not feasible. Now backtrack. And here we are having an alternative. So E, A, C, E. E is having edges C, D, F. C is already visited. So we can have an edges towards D and F. Depth for search. So we need to find out the depth. D. D is having B, E, F. B, E, F. So in this path A, C, E, D, we are having only E. There is no path from B and F. So give the B here and F here. Coming to B. A, C, D. A is there, C is there, D is there. So not possible. So there is no new edge to unvisited nodes. So there is it's not a possible solution or a feasible solution. Move on to the backtrack towards this one and go with the alternative. F. F is having again D and E. So in this path A, C, E, D, F, we are having already D and E have been visited. See, E and D have been visited. So there is no edge towards the unvisited. So this is not a feasible solution. So backtrack and move with the alternative F. So F is having the edges D and E. So F is in this path A, C, E, F. There is no D. Okay, F is visited to D. Now you can check a D. B, E, F. In this path A, C, E, F, D. E, F are visited, B is not visited, so you can have B here. Now B, A, C, D, A is there, C is there, D is there. So all nodes visited, right? Now check the total number of nodes. 1, 2, 3, 4, 5, 6. So total nodes, all nodes have been visited exactly once. So it may lead to the Hamiltonian cycle. Now check the edge from B to A. Whether B is having an edge to A. Yes, it is having. So this forms the Hamiltonian cycle. This is one solution. Right? So all the possibilities we have compared and we got two Hamiltonian cycles for this particular graph. I'll write here the solutions. See, solutions, Hamiltonian solutions. The first solution is, see, A to B towards D towards F towards E and C and A. So this is the one Hamiltonian cycle. So starting from the source vertex, I am considering the source vertex as A. So starting from A, visiting B, D, F, E, C, that means all the remaining vertices exactly once, and coming back to the A. So you can check here A to B. So this is one solution. A to B, B to D, D to F, F to E, E to C, C to A. So this is the solution 1. I'm just for representation, I am representing it as 1, just for understanding, right? This is the first solution. And the second solution, let us take this one. A to C, C to E, E to F, F to D, D to B, and B to A. So this is a one more solution. That is a one more Hamiltonian cycle. So let us draw the here. A to C, A to C, C to E, E to F, F to D, D to B, and B to A. So this is a second solution. Second solution, right? So in this particular graph, we are having two possible solutions. That means two Hamiltonian cycles. So starting from source vertex, visiting all vertices exactly once, and reaching the source vertex is known as a Hamiltonian cycle, right? So here once again I am saying, in this backtracking we are not finding the optimal solution. We are finding all the feasible solutions with the help of brute force approach. That means checking all possibilities. So for that we are drawing the state space tree where we can get all the feasible and non-feasible solutions. So this is a state space tree. Okay, from here we are able to find out all the feasible solutions. So here we got the feasible solutions, two solutions, right? So let's stop here. Hope you understood these Hamiltonian cycles, finding the Hamiltonian cycles in a graph. And we'll solve this graph coloring problem using a backtracking methodology. So imagine if you want to represent a map with different colors, so we need to take care that no two adjacent regions should be colored with the same color. So if that happens, so two different regions will be considered as a single region. So that we have to color a graph or color a map which is having a different regions with different colors without any overlapping, right? So similarly, let us take here a graph and we need to color each and every node or vertex such that no two adjacent nodes or vertices should be colored with a similar color. See, let us take an example. There are 4 regions or 4 nodes. So these are the 4 nodes, and we need to color these 4 nodes with some 3 colors. So red, green and blue usually we call it as a RGB, right? Let us take the three colors. First, if we color the region A or node A with red, the adjacent node B should not be colored with red. So you can color it with green. And coming to the C, the third region, it should not be colored with green because it is adjacent. So it can be colored by using red or blue. Red or blue. And here, this should not be colored with a red because the adjacent region is filled with a red color. So it can be colored with green. Green, right? For example, let us take here, it has a red, okay? And here we can fill with a blue, right? So you can observe we have filled this one such that no adjacent nodes are colored with a similar color. See, A is colored with a red. What are the adjacents? So D and B. So both are with the different colors. And see, B is green. What are the adjacent? A and C. So A and C were not colored with a green. And C is red. What are the adjacents? D and B. Both are not colored with a red. And D, which is colored with a blue. So adjacent are A and C. A and C are not colored with a red. So this is one option. For example, if you consider here blue, if you color this region with a blue, then what happens here? D should not be colored with a blue or red because D is having adjacents A and C. A and C are colored with red and blue. So we should not color D with red and blue. It can be colored with a green. So this is another solution. So like that, we have to color all the regions with the different colors so that the two adjacent nodes should be colored with a similar color. So for this we are supposed to use the state space tree where we are having all possibilities, and from that we are finding the feasible solutions. And if one solution or one path may not lead to the feasible solution, there we are going to backtrack and select the alternate path. So like that we have to solve the problem and we need to find multiple paths, that means a feasible solutions, right? Yes. Let us take the same example. I'll draw the example here. A, B, C, D. So these are the four regions or four nodes. So let us represent it as a 1. Okay, 1, in order to avoid the confusion, because we are also representing the colors with RGB. So in order to avoid the confusion, we can name it as 1, 2, 3, 4. Okay, 1, 2, 3, 4 are 4 nodes or 4 regions, and we need to color with red, green and blue. Red, green and blue. So root node, state space tree, first root node. From this root node, first we have to fill the node 1. So 1, 1, 1, right? And this one we are filling with red and green and blue. So 3. So we can fill the first region with either red, green or blue. So we need to write down all the possibilities, right? So I'll tell only this possibility, so you will be practicing with the remaining 2 possibilities, right? So first consider this one. If the, see, always the backtracking will work with the depth first search. So we need to solve it using depth first search, right? So 1, and from here there are 3 possibilities for filling the second node. See, these are the different nodes, or simply depth first search. So go with the x2 is equal to red. Okay, x2 is equal to red. If 1 is filled with red and R2 and node 2 is also filled with R, that means
the two adjacent nodes comes with a similar color. So this is not a feasible solution. So we should not fill the second node with red. So backtrack, move with the alternatives. So there is a one more alternative, that x2 can be green, red and green. Is it possible? Yes. So 2 is an adjacent of 1 and 1 is filled with R. So 2 is not filled with R, 2 is filled with green. So this is possible way. Again, what is the next possibility? x3. That means the third region. Third region is red. Third region is red. Is it possible? Yes. So third region having a two adjacents, 4 and 2. 4 is not filled so far. 2 is filled with green. So 3 can fill with red. This is also possible. And again, fourth, x4 is equal to R. So x4 is equal to R. That means fourth region is filled with R. So is it proper? No, because 4 is having the adjacent nodes 1 and 3, and 1 and 3 nodes are filled with R. So we should not fill the 4 with R. So this fails. This is not a feasible solution. So backtrack and move with the next alternate path. That is, if x4 is filled with green, so x4 is filled with green. Is it possible? Yes. So 4 is having the adjacent nodes 1 and 3. So fourth region having the adjacent regions 1 and 3, both are filled with R. So 4 is filled with green. Yes, it's possible. So this will be one solution. So next possibility. If x4 is filled with blue, that means a fourth region filled with blue. So this is also possible because adjacent nodes 1 and 3 filled with R, so 4 can be filled with blue. Yes, so this is second solution. Backtrack, move with the alternate. So 2 is filled with red and we have proceeded. Now, 3 is filled with red. Okay. Now 3 is filled with green. Let us take 3 is filled with green. The next possibility. Right? So is it feasible? No, because 3 is having the adjacent regions 4 and 2. 4 is not filled so far and 2 is filled with green. So 3 can't be filled with green. So this is not feasible. Similarly, move on with the next possibility. The third region filled with blue. We have to check. So third region is filled with blue. Okay. So is this may lead to the feasible solution? Let us check. 3 is having the two adjacent regions 4 and 2 and 4 not visited. 2 if is filled with green. So obviously 3 can be filled with blue. So this may lead to the feasible solution. Yes. So further depth for search. So we need to fill the fourth region. So let it be filled with red, R. So it may lead to feasible. So 4 is having adjacent regions 1 and 3. So 1 is filled with R. So 4 should not be filled with R. So this is not a feasible. Next possibility. Sorry, this is 4, right? So 4 is filled with green. Let us take 4 is filled with green and check whether it is a feasible. So 4 is having the adjacent regions 1 and 3 and 1 is filled with R, 3 is filled with blue. So obviously 4 can be filled with green. There is no overlapping. Yes, this is a third solution. And the next possibility, if the 4 is filled with blue, see, 4 is having the two adjacent nodes 1 and 3, 1 is filled with R, 3 is filled with blue, so 4 can't be filled with blue. So this is not possible. This is not possible, right? So again backtrack, and there is a one more possibility for 1. If x2 is filled with blue, see, the second node is filled with R, no solution. Second node filled with green, we got some two solutions, and now we are moving with second node filled with blue. So the next alternate is second is filled with blue. Okay. So x2 is equal to blue, and here x3 is equal to r. x3 is equal to r. Is it possible? So 3 is having, third region is having two adjacent nodes, 4 and 2. 2 is filled with blue and 4 was not visited. So 3 can be filled with red. Yes, it is possible. Again, 4, x4 is equal to red. x4 is equal to red. So this is not possible because 4 is having adjacent nodes 3 and 1. Both are filled with red. So 4 can't be filled with red. So this is not possible. So backtrack and go with the alternate. x4 is equal to green. Now let us take green. Is it possible? See, 4 is having adjacent nodes 1 and 3. 1 and 3 both filled with R. So the fourth region can be filled with green. Yes. So this is one more solution. And what is the next alternative? If x4 is filled with blue, what happens? It may lead to feasible or not. So it is filled with blue. You can check for the adjacent nodes for 4 are 1 and 3. Both are filled with red. So 4 can be filled with blue. Yes. So this is one more solution. And we have completed this, all the three possibilities from region 3. Backtrack and move with the next possibility. If x3, that means the third region is filled with green. A third region filled with green. Is it possible? Yes, because 3 is having adjacent nodes 4 and 2. 4 is not visited, 2 is filled with blue. So 3 can be filled with green. Yes. Now x4 is equal to red. Is it possible? No, because 4 is having adjacent node 1 which is filled with R, so it can't be possible. So it is false. Again, G, that means a green. So if it is green, this is also not possible because 3 is adjacent to 4 which is filled with green. So 4 can't be filled with green. Next, blue. If this one is filled with blue, is it possible? Yes, because 4 is having adjacent nodes 1 and 3 which are filled with red and green. So it can be filled with blue. So this is one more solution. So here we have checked all the possibilities. Coming to the second node, only two possibilities we have checked. So again we have to go with the next possibility. That means if x3 is blue. So if it is blue, is it possible? See, 2 is an adjacent of 3 which is filled with blue. So this can't be happened. This can't be happened. Right? So here we have checked with all possibilities. Right? x3 is equal to blue, which is not possible. So we have checked all the possibilities here. Okay, these all possibilities have been fixed when the first node is fixed with R. First node is filled with R. So we have to repeat the same process and find out all the solutions if the first node is filled with green. And similarly, the next possibility if the first node is filled with blue. So there are three possibilities. The first node can be filled with either red or green or blue. So all these things we have done so far is if the first node is filled with red. Right? So here the solutions 1, 2, 3, 4. So what is the first solution we got? This one. That means R, G, R, G. So R, G, R, G. This is the first solution. And the second solution, R, G, R, B. R, G, R, B. Third solution, R, G, B, G. R, G, B, G. And the next solution, R, B, R, G.
RB, RG. Next solution, RB, 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 RB. The next solution, RB, GB, RB, GB. So these are all the different solutions. Okay, these are all the different solutions. You can see, so without any overlapping, that means without filling the adjacent nodes with the similar color, so we can fill all the regions by using these combinations. If the first node is fixed with R, that means if it is filled with R. Similarly, we have to find out if the first node is filled with green, what are the possible solutions? And if the first node is filled with blue, what are the possible solutions? So I am just stopping here. You just practice with these two nodes, right? And solve this and comment all the possible solutions for this particular graph and all the possible solutions for all these possibilities. Branch and bound. So we'll see what exactly this branch and bound and which type of problems can be solved by using this branch and bound, and what are the characteristics of branch and bound, and what are the applications, that means which type of problems can be solved, right? So first let us see what is this branch and bound. Usually this can be represented as BB. It's a branch and bound, or BNB. N stands for N, branch and bound, or B and B, right? So we can represent in any one of these forms, okay? And mainly this branch and bound is used to solve the optimization problems. So it is used to solve optimization problems. So we have seen different category of problems. Among that we have seen the decision problems and the optimization problems. So decision problems are nothing but all the feasible solutions, right? The problem which gives all the feasible solutions. So backtracking is mainly used to find or solve the decision problems. So in apart from this optimal solution, backtracking will find all the feasible solution with the help of state space tree. And coming to this branch and bound, so it is mainly used to solve these optimization problems. Already we have seen what is meant by this optimization problem. That means a complex problem can be divided, complex problem can be divided into small subproblems, and each subproblem can be solved, and we are going to find out the optimal solution. So these solutions for subproblems can be solved by using a backtracking in this branch and bound. Okay, this can be done by using a backtracking. So we know that backtracking, what is meant by backtracking? So backtracking means checking all the possibilities by using the state space tree. So this depends on state space tree. So what is meant by state space tree? So state space tree is a tree structure which gives all possible paths. So those paths may have a feasible solution, or those possible may not have the feasible solution, right? So that is the state space tree. So this branch and bound will use all these things, but there is only one difference. Among these subproblems, the solutions for these subproblems, based upon the boundary levels, that means lower boundary and the upper boundary, we are supposed to eliminate or ignore the subproblem, and we have to find only the optimal solution. That means, so we need to find optimal solution. So use it to find optimal solution. That means the best solution. So one problem can have multiple solutions. One problem can have multiple solutions. Among that, we are supposed to select the optimal solution, which is the best solution. In order to find out that optimal solution, we are going to draw the state space tree where we are having all possibility paths, right? And we are also using the backtracking. So we are just expanding the nodes in the tree, and if it doesn't lead to the feasible solution, backtrack and go with the alternate path. So that is called the backtracking. So in this branch and bound, we are going to use all these things. So you can see branch and bound. That means we are just drawing the state space tree. That means a branching levels in terms of levels. And then we are applying the bound. That means a boundary levels. Excuse me. Boundary levels, lower boundary and upper boundary. So based upon the lower and upper boundaries, we are going to ignore some sort of solutions which are not being executed or which are not useful to get the optimal solutions, right? So we are going to apply all these things. So now, what are the characteristics? What are the characteristics of branch and bound? The first one, just now we have seen, that is a backtracking. So we are starting with one node, just we are expanding that node, okay, and while expanding, if it doesn't lead to the feasible solution, we are just backtracking to the previous node and we are going with the alternate path. So this is one characteristics of branch and bound. So we are going to use this backtracking process. And the next one, pruning. Pruning is nothing but ignoring, right? So just now we have said, so while creating the path, so if there are any not feasible solutions, we are going to ignore. Pruning means ignoring. And the next one, lower bound and upper bound. So we'll use some boundaries, lower bound values and upper bound values, in order to select or in order to get the optimal solution. So if by applying this lower boundary and upper boundary, if the solution, the current solution or current path is not viable to the feasible solution, so obviously we'll prune it and we'll backtrack. And the last one is optimal solution. So finally, the result should be optimal solution. So finding the optimal solution. So finding the optimal solution with the help of lower boundary and upper boundary, which are not feasible, then just ignore it and backtrack with the alternate. So these are the characteristics of branch and bound. Now we'll see the applications. That means which kind of problems, what are the problems we are supposed to solve by using the branch and bound. So applications. So the first one is a knapsack problem. So already we have solved it, and the same kind of problem we can solve using the branch and bound in order to get an efficient, that means optimal solution. And the next one, traveling salesperson problem. So the same thing, we have already solved this one, but the same problem can also be solved by using this branch and bound to get the optimal solution. Similarly, there are a few more, like game playing. Game playing is one more problem. Okay, next, n-queens problem. So whatever the applications we have done in this backtracking, everything can be solved by using this branch and bound. Then what are the advantages? What are the advantages of using this branch and bound? First one is performance, because it leads to the optimal solution. The next one, reducing search tree, that means a state space tree. So it is not required to create the complete state space tree. Okay, and the disadvantage, only one disadvantage, the complexity, it is an exponential complexity. So this branch and bound gives the exponential complexity, the time complexity. So this is a one drawback of using this branch and bound. And one more thing, this backtracking will be using, or the backtracking methodology uses the depth first search. So in all our previous applications we have seen, while solving the problem we are just going with the depth first search. Okay, depth first search. But here in this branch and bound, these problems can be solved with the help of breadth first search, not the depth first search. So completion of one level, then only it will move with the next level. Right? So this is all about our branch and bound methodology. So this is a one more important problem solving methodology you have to learn in algorithms concept. So in our further sessions we will see the knapsack problem and the traveling salesperson problem, how we can solve by using this branch and bound methodology. Channel. So today we will see one of the application of branch and bound, that is traveling salesperson problem using least cost branch and bound. So traveling salesperson problem. So already in our previous sessions we have seen this traveling salesperson problem, which has been solved in different methodology. In this session we will see how can we solve this traveling salesperson problem by using branch and bound. So once again recalling the problem, so traveling salesperson means starting from one vertex or one city, so traveling or visiting all other cities or nodes exactly once and coming back to the origin. That means wherever the person starts, so the final destination will be the source. So that means, for example, A, B, C and D. So traveling salesperson is starting from the source. Let us take A as a source, visiting all other vertices exactly once. So A, then B, then C, then D, and finally come to the source. So from D to A. So this is one possible path. Okay. Similarly, A, D, C, B, A. This is one more path, another path, right? But here the optimal solution means with a least cost, minimum distance, or we can say minimum distance, right? So the traveling salesperson have to visit all the cities and come back to the source with shortest distance. So that we call it as a traveling salesperson. And now we are going to solve this problem using branch and bound. So in this branch and bound we are supposed to go with a state space tree, but we need not construct the complete state space tree. So we are supposed to expand the nodes which are having the least cost. So that's why we are calling this as a least cost branch and bound. So let us move on to the problem. So I have taken the cost adjacency matrix, this one. So I have taken the cost or the distance from one node to another node, right? So I have represented an infinity where the node doesn't exist. So here vertex A to A, there will be no edge. Okay, so this we called it as an infinity. Similarly, there will be no edge between B and B. So this will be represented as infinity. C and C, this will be represented as infinity, and D and D, it is infinity. There might be have a chance of getting the distance from other nodes, A to B, A to C, A to D, similarly B to A, B to B, B to C, etc. etc. Now we will see how we can find the optimal solution. So for this we have to construct the state space tree. In a breadth first search approach. Okay, usually in our previous sessions we have seen the state space tree expanding along with the depth first search, but here we are going to use breadth first search. And first one we have to find the reduction cost. Okay, reduction matrix. So we will call it as a reduction matrix. What is this reduction matrix? So here two things should be identified. So one is every row should have 0. Every column should have 0, right? If not, what we have to do? Find the minimum in row and subtract with every element. Similarly, find the minimum in each column and subtract with every element in that particular column, right? So after applying these, we will be getting the reduction matrix, and from this reduction matrix we are supposed to calculate the reduction cost. So this is the first one, and the second one, calculate reduction cost. That means how much value we have subtracted from the rows and from the columns. We have to add both the things so that we'll get the reduction cost, and this will be the initial reduction cost for source vertex, and from that vertex we are supposed to expand the nodes based upon breadth first search. So first we have to do this one. So let it be, this is the adjacency matrix. Okay, so every row should have 0. Observe, this doesn't have 0, this doesn't have 0, this doesn't have 0, this doesn't have 0. What we have to do? We have to find the minimum in row and subtract with each element. So what we have to do? So what is the minimum element? 10. In this row, 5. In this row, 6. In this row, 8. So what we have to do? We have to subtract with every element in that particular row. So we have to subtract 10 from infinity, 10 from 10, 10 from 15, 10 from 20. Similarly, second row, third row and fourth row. After that, again we have to check every column should have a 0. Whether every column is having a 0. If not, again find the minimum in the column and subtract with every element in that particular column, so that finally we'll get the adjacency matrix. Now, I am erasing this one. Let us move on to the problem. See. Yes. So first we have to eliminate the rows. So 10, 5, 6, 8. I'll write here. So infinity minus 10, obviously it will be infinity. 10 minus 10 is 0. 15 minus 10 it's 5. 20 minus 10 it's 10. Similarly, 5 minus 5 is 0. Infinity minus 5 infinity. 9 minus 5 4. 10 minus 5 it's 5. 6 minus 6 0. 13 minus 6 is 7. Infinity minus 6 infinity. 9 minus 6 is 3. And 8 minus 8 0. 8 minus 8 again 0. 12 minus 8 is 4. And again infinity. So this is the matrix we got with the row reduction. Okay, we have to do the column reduction and row reduction. So this we got after a row reduction. Now from this we have to calculate the column reduction. Okay, so from this we are calculating the column reduction. So this is a row reduction, right? So let us check whether every row is having a 0 or not. Every row is having a 0 or not. So sorry, every column reduction. So this one, yes, 0. This one, yes, 0. This one, there is no 0. So find out the minimum value. What's the minimum value? 4. And here, no, the minimum value is 3. Now we have to subtract the value from each and every element of the column. So write down the column wise. So first column, infinity, 0, 0, 0. And next second column, 0,
infinity, 7 and 0. Third one, 4 is the minimum, 5 minus 4 it's 1, 0, infinity and 0. 3 is the minimum, so 7, 2, 0 and infinity. So this one is the matrix we got after row reduction and a column reduction. So this is called as a reduction matrix. Reduction matrix. So first step, we have to find out this reduction matrix after performing row reduction and column reduction. Right, hope you understood. Now, what is a cost reduction? Cost reduction is equal to whatever the values we have subtracted from each row. So that is 10 plus 5 plus 6 plus 8 plus from row or columns 4 plus 3. So you can calculate 15, 21, 29. Yes, yes. 14, 19, 29. So this is the 29 plus 7. So total 29 plus 7, it is a 36. So the cost reduction initially was 36. The cost reduction initially was 36. Right? Now start expanding. Let it be. Start with A, which is a source. The cost is 36. So here we are having only one source. So we need not go with the alternate. So that node will be expanded. So the next node or the next city to be visited is either B or C or D. Right? So the traveling salesperson can visit from A to B or C or D. So we need to cost of B, C, D. So cost of AB, cost of AC, cost of AD. Right? So let us take this value. Okay, I'll once again write here. So alpha infinity 0, 1 and 7, 0, infinity 0, 2, 0, 7, infinity 0, 0, 0, 0, infinity. So this is the matrix. Okay. From this we have to find out the cost between A and B. So we need to find the cost. So cost of A to B. What we have to do is we have to find out again the reduction matrix, and instead of taking the reduction matrix, first we have to consider this is a row and this is a column. So fill all the row values and the column values with infinity. So A row A means the first one, right? So fill all the things with infinity, right? And column B column is second one, fill with infinity. So the person can't travel from B to A, so this will also be infinity, B comma A. Okay, now fill the remaining values from this particular matrix. So here we'll get 0, 0, and here we'll get 0, infinity, 0, and here we'll get 2, 0, infinity. Now consider the cost reduction, row reduction and column reduction. So this is completely infinity, no problem. And here we are having a 0, and here we are having a 0, and here also we are having 0. From the column this is 0, so this is completely infinity. Okay, so here we are having 0, and here also we are having 0. So that means already cost, this is a reduction matrix. Now the cost of AB, the cost of A comma B will be the cost of parent plus edge, or the cost between A comma B plus cost reduction. So how we are getting the cost reduction? Previously we have seen adding all these minimum values and these minimum values. That means whatever the minimum values we are getting in the row reduction and the column reduction should be added, and that is a cost reduction. In this case the cost reduction is 0 because there is no minimum value, all the minimum values are zeros itself. Right. Now what is the value of cost of AB? Cost of parent is nothing but 36. Cost of A comma B. So we should not consider this one, right? This is a cost reduction matrix. So we need to find out this cost of AB from A. So cost of AB, which is 0, plus cost reduction here, adding all the minimum values, which is again
0, that will be 36. So cost of ABE is 36. So cost of ABE will be 36. The same thing should be applied for C and D also. C and D. Okay. Now, I will write the cost of A comma C. So we need to find the cost of A comma C. So for this, we have to first write down the matrix. Complete row A should be filled with infinity, and C, column C means the third one, should be filled with infinity, and the traveling salesperson can't go back, right, to the same node. So it will be visited twice. So C to A should also be infinity. Fill all the values from this one, right? 0, 0, infinity, 7 and 0, and 2, 0 and infinity. Now find out the cost reduction. So here, yes, infinity, and here it is 0, here it is 0, here it is 0, and here also it is 0, 0, infinity, okay, so it's 0. So here also the cost reduction is 0, because already every row is having some 0 value and every column is having some 0 value. So the cost reduction will be 0 here also. Now the cost of A comma C will be cost of parent 36, cost of A comma C from this one, A comma C cost is 1 plus cost reduction which is 0, so which is equal to 37. So the now cost of AC is 37. Okay, now find out the cost of A to D. So I'll write here. Okay, cost of A to D. Again, write down the matrix. So the complete row, A row will be infinity, and row D, column D will also be infinity, and the column D to A will also be infinity. And fill all the columns with respect to this one. 0, 0, infinity, 7 and 0, and 0, infinity, 0. Right? Yes. Okay. Now you can see row infinity, and second row 0, third row 0, fourth row also 0. First column 0, second column 0, third column 0, and fourth column all are infinity. Okay. Then this is also a cost reduction. Cost reduction is 0 here. Now the cost of A comma D will be cost of parent, which is 36 plus, right? Next, what is this one? Cost of A comma D. Here it will be AD. Cost of AD from this matrix. Okay, not this one, from this one. Cost of AD 7 plus cost reduction. So here all is 0. So obviously it is 0. So this will be 43. So the cost of AD will be 43. Right? So hope you understood. Now we are expanding based upon breadth first search. So we have calculated the cost of A comma B, A comma C, A comma D. So among these three paths, we need to find the least cost, and we need to expand that particular branch itself. So that's why we are not performing the complete state space tree. So we are calculating based upon boundaries. What is the bound here? So we are selecting the least cost. So least cost is the boundary. So with the help of boundary itself, we are reducing the state space tree. So here 36 is the least cost. Now we can expand the node B. So from node B, the next node can be either C or D. Again, we have to find the cost from B to C, B to D. B to C and B to D. So what is the B matrix here? So this is the B matrix. Okay, this is the B matrix. Now you can erase this one. This is a reduction matrix, and we are expanding B, so we have to consider this one. If C is having the least cost, we have to consider this one. And if B is having the least cost, we have to consider this matrix. Now I am writing this one, right? Infinity, 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 and infinity, infinity, 0, 2, and 0, infinity, infinity, and 0. 0, infinity, 0, infinity. So now this is the reduction matrix of B. So we are supposed to expand this one, okay, node B. So apply the same procedure to find the cost from B to C. So this is a B, okay. So we have to find the cost of B to C and B to D. So first B to C means write down the reduction matrix. Consider B, row B with all infinities. So infinity, infinity, infinity and infinity. And C column, that's the third one. Infinity, infinity, infinity. And again, C can't go to the first one. So C to A. So this is also infinity. A is already visited. So remaining values fill from this particular, this one. So 0, 0 and infinity, infinity. And here also it is infinity, infinity and 0 and infinity. See, all are infinities and zeros. So there is no reduction matrix. Okay. So here you can see yes, 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 and so here we are having a 0 and here also we are having 0. From column wise, this is having 0, this is having infinity, this is having infinity and this is having 0. So this is already cost reduction. So what we have to do? We have to find out the cost from B to C. So cost from B to C, that is a cost of parent. Cost of parent is, so C parent is 36, so 36 plus cost of B comma C. Cost of B comma C, B, C, 0. So we should consider the cost of B comma C from this one, not this one. Plus cost reduction. So here all the rows and columns are 0. So don't worry if your graph is having a different values. Again, if for example, if here it is some 5, okay. So this row, this column will be having a 5. So we have to subtract this column with 5. So the cost reduction will be 5. For example, if it is 5, okay. Now in our example, it is 0. So we did not go with the reduction, right? So that's why I am having a 0. So 36. So here also it will be 36. And coming to the next one, cost of B comma D. So what we have to do? Fill all the second row with infinity and fourth row with infinity. And the person can't go with D to A, so D to A will also be infinity. Now fill the remaining terms. So it is infinity, the third one it is 0 and this is completely infinity. What about this row? It is infinity and 0, right? So here also the cost reduction is same 0 and here it is infinity, here it is 0, and here it is infinity. Row wise it is infinity accepted and here it is infinity accepted and here it is 0 and here it is 0. So the cost reduction is 0. Then the cost of parent, which is 36, cost of B and D, B to D, which is 2 and cost reduction is 0. So which is 38. So here it is 38. Okay. So again see, we have calculated the second level, okay, breadth first search. So B to C and B to D. Now again we have to find out the least cost and we have to expand that particular node. So among these two, what is the least cost? This one. So this will be expanded. So A, B, C and here it will be D. And this should not be expanded because this is a high cost and this is a high cost. This is a high cost. So this should be expanded. Now we have to find out the cost of C to D. So C should be selected. So what is the C? This one. Okay. This one is the C and we can erase everything else. So this is a C and we need to find cost of C to D. So first what we have to do? We have to fill all the row C should be with infinity and column D should be infinity and DA should be infinity. Now fill all the remaining with this one, right? So infinity, infinity and infinity, infinity, infinity. The third one also it is infinity infinity, infinity, and you can see, so every row and column satisfies. Okay, so either it should be 0 or infinity, right? Okay, so what we have to do, cost of CD, the parent, which is 36 plus, okay, parent 36 plus cost of CD from this one, CD. See, you can see A, B, C, D, A, B, C, D, C to D, which is 0. 0 plus cost reduction here, again 0, which is nothing but 36. So it is also 36. And you can see all the 4 vertices have been visited here. All the 4 vertices have been visited. So you can check the path. The shortest path is A to B, B to C, C to D, and D to A. So this is the last vertex, and from here it will move to the A. Okay, so A to B, B to C, C to D, and here. You can observe here A to B, the cost is 10, B to C, your cost is 9, C to D, its cost is 9, and D to A, its cost is 8. So the total cost, you can observe 10 plus 9, 19, 28, and 36. So with this 36 cost, okay, so the person can visit from source to destination and come back to the source, right? So this is the procedure to find the shortest distance, okay, using branch and bound. So one thing we have to remember is we are finding the cost, but we are not getting all the possibilities. That means we are not expanding the complete state space tree. So we are just selecting the boundary, that means least cost as a bound, and we are restricting or we are reducing the state space tree. So in the first level, you can observe 36, 37 and 43, these 3 are the cost we got. And we are expanding only the node with the least cost, that is 36. And then further, again we are having 2 parts, one is 36 and another one is 38. Again we are expanding the node with the least cost, that is 36. So finally we have reached the destination. That is knapsack problem. So 0, 1 knapsack problem. So already we have seen what is this knapsack problem in our previous sessions, and again once again I'll tell you what is a knapsack problem and how we can use this, solve this knapsack problem by using branch and bound. So knapsack problem using BNB. So BNB stands for branch and bound. So branch and bound is an algorithmic approach which gives the optimal solution, so which is used to find the optimal solution among different solutions. And here also we are going to use or draw the state space tree, but we are not expanding each and every node. So we'll use some boundary values, and based upon that boundaries we are supposed to expand only those particular nodes. So the complete state space tree will be reduced with the help of the boundaries. Okay, and here we are using the least cost branch and bound. Least cost branch and bound. That means we'll find out the cost for each and every node, and we are supposed to expand the node which is having the least cost. And see here, we in this knapsack problem we'll be having a different weights and different profits, and there will be one knapsack, and we are supposed to push the weights into the knapsack so that finally we should get the maximum profits. And here everything will be the maximizations, but here we are considering the least cost. So initially we'll consider the complete profits with a negative value, and finally we'll get the positive. Okay, see, knapsack will be having one knapsack that means a bag structure, okay, with a capacity, alright, with a capacity, a fixed capacity, and we'll be having some profits and weights and the corresponding profits, and we need to add these weights into this knapsack so that the corresponding values should be more profit, okay, more profit. So we can say it as a fill knapsack which gives more profit. Okay, so here the boundary, so here what is this 0 1 knapsack, 0 1. So we are supposed to consider 0 as push, or consider the corresponding weight 1, 0 for consider and 1 for consider. It's not consider and consider. For example, if we are having the weights as x1, x2, x3 and x4, and the profits with the p1, p2, p3, p4, then simply we will represent the solution with 1, 0, 1, 1. So how it represents means we are considering x1, okay, we are considering x1 and x3 and x4. So we are pushing all these three weights into the knapsack so that we'll get the profit as p1 plus p3 plus p4. That is a more profit. So if 1 represents considering the particular weight, 0 represents considering the not considering the particular weight. So here 1, 0, 1, 1 means x1 is considered, x2 is not considered, so we have not written here. So p2 is also not available here, and 1, that means x3 is available, x4 is available. So for that representation we are considering, we are using this 0, 1. 0 means not considered, 1 means considered. So we need to expand the state space tree for both the cases. Okay, now we'll see an example of this knapsack problem. We'll solve that by using branch and bound. Okay, that's also least cost branch and bound. See, this is an example we are supposed to solve this. So profits are 10, 15, 7, 8, and the weights are 2, 3, 1 and 5, and the capacity of knapsack is 5. So we need to consider only the weights which gives the total weight 5 and which gives the possibility of more profit. For example, here you can see we can push the 2 and 3 into a knapsack so that the total weight will be 5. So the corresponding weights you can see 10 plus 15, which is nothing but 25. Okay, and there is one more possibility, pushing the last item only 5 into the knapsack because the capacity is itself 5, right? What is the profit? 8. So we can fill the knapsack with a 5 weight. So that 5 can be filled with single, pushing only the fourth element into the knapsack or the first 2 elements into the knapsack. So here we are having 2 different solutions. Among these 2, what we have to consider? We have to consider the optimal. Optimal means with a high profit. So if you push the 4th element into the knapsack, the profit will be 8. And if you push 2 and 3 into the knapsack, the profit will be 25. So which is an optimal? So obviously this will be the optimal. So we have to find these optimal solution with the help of a state space tree. Okay, so in that we are supposed to find the least cost BNB. So initially we consider the profit as a negative values. So the negative values are minus 10, minus 15, minus 7, minus 8. Okay, now let us consider initial node, which is a root node. So from that root we are supposed to find the 2 paths. One is whether we have to consider the first element
and we should not consider the first element. So we'll be getting 2 nodes. Okay, and here for each and every node we are supposed to find the 2 things. One is upper bound and the lower bound or cost. So U for upper bound, cost is for lower bound. U is for upper bound, cost is for lower bound. And see, upper bound means the profits without fractions. For example, see, consider second and third elements. So 3 plus 1 is equal to 4. So still the knapsack can hold 1 weight. Okay, so it is 4. The capacity of knapsack is 5. So still there is a vacancy of 1 weight. So we can consider this 1 from the next element. So not the complete element can be pushed into the knapsack here, right? So here there will be some sort of fractions. So upper bound means the profits without considering the fractions. So we have to consider the complete element or we can ignore it. But coming to the lower bound, that is a cost, which is a profits of corresponding weights considering the fractions. Okay, so we'll calculate both, but we will be depending on the upper bound. So which node will be having the least cost, that will be expanded more. Okay, now we'll calculate the U and C for both the nodes. First, coming to this one, see, if it is x is equal to 1, that means we have to consider the first element. So what is the first element here? So 2 is the first element. So we'll consider the profit. If you insert this 2 into the knapsack, what is the profit? It is a minus 10. So there will be still 3 possibilities. I mean, the capacity of knapsack is about 3. So move to the second element, 3. If you push 3, we will get the profit as a minus 15. So check whether the knapsack has been filled or not. So 2 plus 3. So obviously it is 5, which is the capacity of knapsack. So no other element will be pushed into the knapsack. So if you add this one, the profit will be minus 25. Okay, minus 25. The profit is minus 25. So here we are not considering any fractions. So upper bound will be minus 25. And coming to the lower bound. So this is the upper bound, this is the lower bound. We need to consider the fractions if necessary. But here 2 is the first element and 3 is the first element. So there is no place in the knapsack. So there will be no fractions. And obviously the lower bound will also be minus 25. Okay, coming to this one, this node. So here we should not consider the first element. So without considering the first element, let us go with the cost. That means a lower bound. Okay, with fractions. So we should not consider first element. So push 3 into knapsack so that we'll get the profit as minus 15. Then there is again vacancy of 2. So push the next element, that is 1. Okay, so that we'll get a profit of minus 7. And see, again we are having one weight. Okay, but the next element is a 5. The next element is a 5. So we need to take 5. Okay, 1 from 5, 1/5. So that we have, how we can take it as minus 8 divided by 5 into 1. So we require only 1. Okay, we need to get the profit of 1/5. Okay, so minus 8. So what it will be? So this is nothing but a 5. So 3, 1 and 1 from 5. So minus 15 minus 7. So minus 22. And here, what is this one? So 5, 8. Okay. So minus 0.4. Sorry, not 0.4. So 1.6. Yes, 1.6. So total it will be minus 23.6. That is the cost. Minus 23.6. Okay, hope you understood why we are getting the fractions. So here in this case, we didn't get the fractions because the first two elements fills the knapsack equally. So 2 plus 3, total 5. So there is no fraction. But here, coming to here, we should not consider the first element. We are not considering the first element. We should consider from the second element. So 3 plus 1, 4. And still there is a 1 element remaining, right? So we need to take 1 element from this 5 profit. So that's why we are getting here. And coming to the upper bound, we should not consider the profit. So we have to insert 3 so that we'll get a profit of 15. And we'll insert 1, we'll get a profit of minus 7. And there is no other element to be pushed because here we are having 5. If you push 5, total it will be getting a 9, which is beyond the capacity. So we should stop here, and the upper boundary is minus 22. So here we should not consider the fractions. So it will be minus 22. So among these, which is the least? Now you can observe why we are considering the negative. So here these are the profits, maximization profits. We need to get a maximum profit. So that's why initially we are considering that as a negative. So you can observe among these two, so upper bounds, consider the upper bounds. What is the least cost? So minus 22 or minus 25? Obviously it is a negative. So minus 25 will be the least number when compared to the minus 22. So this is the minus 25 is the least one. So we need to expand this node. That means final solution will be including the first element. So we need to expand this one. So I'll expand here. So third and 4. This is the second stage. Here we need to consider x2 is equal to 1 and x2 is equal to 0. That means we need to find whether we have to consider the second element, not to consider the second element. So repeat the same process. We have to repeat the same process. So here we have to find the upper bound. Here we need to find the lower bound. Here we need to find the upper bound, lower bound. For example, so in the previous case we have considered the first element, right? So here also we need to consider the first element. So first element is fixed. So inserting 2 will return a profit of 10 plus, if you consider the second element 3, which will give the profit of 15. And see the total capacity of knapsack filled, right? So we have to stop here, and the profit is minus 25. But for both the upper bound and lower bound, it will be the minus 25 itself. And now we need to go with the second case where we should not consider the second element. So here we are not considering the second element. So you can observe we are considering the first element, we are not considering the second element. So we are considering the first element 2, insertion of 2 gives the profit of minus 10 plus we should not consider the second element. So this node is not considering the second element. So we need to consider third element 2 plus 1, which gives the profit of minus 7. So is there any vacancy in the knapsack? Yes, the total weight of knapsack is 3. So there is a 2 more vacancy. So we need to take 2 from 5. So 2, 5. That means what we will get? Minus 8 divided by 5 into 2. Okay, so this will be minus 17 and plus how much we'll get? So previously we got some 1.6, right? So 3.2. So which will be minus, okay. So which will be minus 20.2. Okay, so 8 by 5, which is 1.6 into 2. So that will be 3.2. Okay, 3.2 and 3.2 plus 17, 20.2, negative 20.2. So it will be minus 20.2. And here upper bound we should not consider the fractions. So we should not consider this one, right? So what is the cost here? Minus 17. Minus 17. Again, consider among these two nodes. So we should not consider this node. Okay. So among these two nodes, what is the minimum cost? What is the minimum cost? So here among this one, you can observe u is equal to minus 25, u is equal to minus 17. So minus 25 is the least cost. We need to expand 3 again. So in the third case, so we'll give 5 and we'll give 6 here. And we need to consider x3, or we should not consider x3. We should consider x3 or we should not consider x3. Both we have to find out. So we need to find the upper bound. We need to find the cost. Here also upper bound, cost.
So here you can see x1 is equal to 1. So see, consider x1 is equal to 1, x2 is equal to 1, x3 is equal to 1. So if you consider x1 and x2, that means the first two elements if you consider, so 2 plus 3. And here the third case is we need to consider the third element also. If you consider the third element, the total cost will be 6, which is beyond the capacity. So we should not consider this. So we need not calculate that one, right? Because we should not consider. So here itself we got the total capacity, the knapsack has been filled. Coming to here, x3, if you are not considering the 3, see, considering 1, 1, 0. So 1, 1, 0, that means x1, x2, x3, 1, 1, 0. This is the case we are finding, right? So x1 is considered, so 2, we'll get a profit of minus 10, plus x2 is considered, we'll get a profit of minus 15, and x3 is not considered, so x4 should be considered. So if you consider x4, the knapsack capacity will be beyond. So we need not fill this one also. Okay, right? So the value will be minus 25 itself. So here it will be minus 25, and here also it will be minus 25. And among these two, which one is the lowest? Obviously minus 25 will be the lowest. So again, expand. So here there is another case, x4. So whether we need to consider x4 or whether we should not consider x4. So here also we have to find the upper bound and cost. Upper bound and cost. So you can see here at this position, what is this one? x4, it is 1. So we are considering 1 and 2 and 4. So 1 is 2, 3, and we are not considering this one, and the fourth one is 5. So if you add this one, what is the knapsack weight? So it becomes around 10, but the capacity of knapsacks is only 5. So we should not consider, and the weight will be minus 25 itself. And here also, if you are not considering the x4 also, okay, we should not add this one, right? So this cannot be expanded. We need not expand this one. Okay, and coming to this one, that means x4 is equal to 0. So we should not consider this one. So we are not considering this one. The knapsack weight is full. So with a profit of minus 25. So upper bound will be minus 25 and the lower bound will be minus 25. So that is the last step. So this is the solution for the problem. So pushing or considering the elements first and second will give the maximum profit. So previously we have seen the two cases, 2, 3. Inserting 2, 3 will be giving minus 25 as a profit, and inserting only the 5, single 5 will give the profit of minus 8. So you can simply remove this minus. Okay, you can simply remove this minus, so we will get the optimal solution. The highest profit is 25. So you can see by considering 2 and 3 we will get the more profit. And here also the same thing, we have expanded. See, we have expanded, we are considering, so we have not considered the second one, fourth one, fifth one and seventh one. So we have considered the node 1, 3, 6, 8. So node 1 by considering x1 first element, node 3 by considering the second element, node 6 considering 0, not considering the third element, and node 8 not considering the fourth element. So 1, 1, 0, 0 will be the solution to get the maximum profit. And in this case we are not giving the complete state space tree. We are not drawing the complete space state tree. So we are limited to the boundary, that is we are considering the least cost value of upper bound, and we are expanding only that particular branch instead of expanding all the nodes, right? So that's why we are calling it as a branch and bound. So we need to divide that branches, that means we need to draw the state space tree by considering the boundaries. And what is the condition? Least cost. And here we need to get the maximum profit. So obviously we are supposed to take initially them as a
negative values, and finally we can ignore the negative values so that we'll get the optimal solution for this knapsack problem. Right? So hope you understood what is a knapsack problem, what is a 0 by 1 representation, what is a branch and bound, what is a state space tree, and what is the constraint we are using the state space tree to be expanded, the each node to be expanded. Right? So practice more problems so that you will be getting strong knowledge on this branch and bound. Today we will see one more concept in branch and bound, that is a 0-1 knapsack problem using FIFO branch and bound. So in our previous session also we have seen the same problem, but we have solved the problem by using least cost branch and bound. And now we will see the FIFO branch and bound, that means a first in first out. Okay, so let us see what is a 0-1 knapsack. So already we have seen in our previous session. Once again I will repeat what is this 0-1 knapsack. So here a knapsack is a just like a bag or a container, okay, where we can insert some sort of elements. Okay, there will be two things. One is weights will be there, which are represented with let it be W1, W2, W3, etc. So these are the different weights. And the another thing is profits. So what is the profit we'll be getting if you insert the weight into the knapsack? So the corresponding profits will be represented with the P1, P2, P3 and etc. Right? So here the problem is we are having a container that we will call it as a knapsack with a small capacity. So we are supposed to place these weights into the knapsack, so which doesn't go beyond the capacity, and getting the more profit. That's a main constraint, right? So this is a complete knapsack problem, and we have to solve this by using a branch and bound, that is also FIFO branch and bound. And in this particular branch and bound, we are supposed to draw the state space tree in order to find the optimal solution. Okay, so some solutions will be infeasible, so we'll eliminate that one, and we'll get only the optimal solution by expanding each and every node of a state space tree. So here we are going to draw a state space tree. Okay, and here we'll be having a nodes, and at every node we are supposed to calculate the two things. One is a lower bound and upper bound. Lower bound and upper bound, right? So this is a knapsack using FIFO branch and bound. Okay, right. So every node we are supposed to find the lower bound and upper bound values, and here the lower bound values will be calculated with fractions. So fractions will be allowed here, and upper bound without fractions. So this should be calculated without calculating the fractions, right? So for every node we have to calculate this one, and in this particular FIFO branch and bound, for every node we have to check two conditions. So the first step is find upper bound. Okay, upper bound value, which we usually call it as global upper bound. So right, global upper bound. And for every node in the state space tree, we have to compare with this global upper bound. We need to check two conditions. So the first condition, if the new upper bound is less than, I'll erase this one, less than global upper bound. So we are calculating the lower bound and upper bound, right? So once you calculated this lower and upper, we need to compare this new upper bound with the global upper bound, which is calculated initially, right?
So if the new upper bound is less than the global upper bound, then update global upper bound. So I am using small words like UB with new upper bound. New upper bound. So that means we have to replace this global upper bound with the new upper bound whenever the new upper bound value is less than the global upper bound. So always the global upper bound should be the minimum value. So that is the first thing we have to calculate. And the second condition, two conditions we are supposed to use, and there is the first condition, and the second condition, if the lower, so every node we are calculating the lower bound. So if the lower bound is greater than the global upper bound, global upper bound, then we are not we should not expand that particular node. So if after calculating the lower and upper bounds, we have to compare this lower bound with the global upper bound, right? With a global upper bound. If the lower bound value is greater than the global upper bound value, then that particular node should not be expanded. So we have to kill that particular node. So then the node should not be expanded. That means kill the node. Right? So these are the two conditions, most important conditions we have to check while solving the 0-1 knapsack problem using FIFO branch and bound. So initially find the upper bound and initialize it to the global upper bound, and now for each and every node we have to calculate the lower bound and upper bound, and if the new upper bound is less than the global upper bound, then update this global with a new upper bound, and if the lower bound is greater than the global upper bound, then immediately that node cannot be expanded. So that is a kill node. I mean, we have to kill that particular node. That means that node cannot be expanded. So with this you can observe that we are not expanding each and every node of a state space tree. So at some particular point we are comparing and we are deciding whether the node can be expanded or it can be killed. So the state space tree is not completely finding. Okay, we are not calculating the complete state space tree. Okay, so just remember these points, these conditions, so that we'll see the example. So whatever the program or whatever the problem we have taken in our previous session, the same thing we'll take, and I'll show you this one. So I'll write here the two conditions. So I'll write new upper bound is less than global upper bound, then update. So simply I'll write it as an update. And the second condition, lower upper bound is greater than global upper bound, then kill. So these are the two conditions we have to remember, right? Now we'll see the problem and we'll find the state space tree. We have to calculate the lower bound and the upper bound values. See, this is the problem we have solved in our previous session. That means using the least cost branch and bound. The same thing we have taken. So weights given, the 4 weights. So one is 2, 3, 1, 5, the capacity. And the profits, corresponding profits at 10, 15, 7 and 8. And here we are supposed to find the optimal solution. And here this is a minimization problem. So for that we are just using the negative values. So I am just putting the negative sign, right? So minus 10, minus 15, minus 7 and minus 8. Now the capacity of knapsack is 5, given as a 5. So we have to insert the elements into the knapsack so that the knapsack weight should not exceed the 5. Okay, so here also we are having two different solutions. we can consider 2 and 3, which gives a profit of minus 25, and considering only one element, that is 5 directly, which gives the profit of 8. So here we are having a two different solutions, possible solutions. Among that we have to go with the optimal solution, right? So we'll see. First we have to calculate the upper bound and the lower bound, initial global value. So upper bound. So upper bound is without fractions. I'll write here. Upper bound without fractions. Lower bound with fractions. So two things we have to remember. Okay. First let us take with the upper bound. The complete knapsack weight is a 5. So I am inserting the first element, that is a 2, with a profit of minus 10, and then 3 with a profit of minus 15. Okay, you can observe the weight of knapsack becomes 5. Okay, if you insert the third element with weight 1, the total knapsack total capacity will be 6, which is beyond 5. So we should not consider the third element. So upper bound value is minus 25. The upper bound value is a minus 25. So simply we can say the global upper bound value is minus 25. Okay, so consider the root, and now we have to check. Okay, we have to check whether we have to consider the element or we should not consider the element. So there will be two positions, two paths. So node 1 and node 2. So here x1 is equal to 1 and here x1 is equal to 0. So here 0 and 1 represents considering or not considering. So this branch is x1 is equal to 1. That means we are considering the first element. And this branch is x1 is equal to 0, which is we are not considering the first element, right? So node 1, see node 1, right? So here we need to calculate upper bound and the lower bound. Okay, so upper bound, coming to the upper bound, consider the first element. So I will push 2 into this one knapsack with a profit of minus 10, and then 3 with a knapsack with a minus 15. So we can't push the third element, right? So the upper bound value will be minus 25. Coming to the lower bound also the similar, but here we can consider the fractions, right? So insert the first element with a profit of 10. So remaining, there is a 3 capacity remaining. So automatically the second element also is 3 with a 15. So there is no need of fractions, because after inserting first element and second element, the knapsack value becomes complete 5, right? So here also the lower bound is also minus 25. So you need to write it here. Upper bound is equal to minus 25 and lower bound is equal to minus 25, right? Hope you understood. And the same thing we have to calculate for the second node also. So first in, first out. So we have to find this one and we have to compare. Okay, after comparison, then go with the next one. Now compare. After calculating the upper bound and lower bound, we have to calculate whatever the new upper bound less than the global upper bound. New upper bound is minus 25. Global upper bound is minus 25. So minus 25 less than minus 25. So it's a false. So no need to change. And if in case if the new upper bound is some around 30, minus 30, you can know that minus 30 is the lowest value than minus 25. So we have to replace this minus 25 with minus 30. But in this case, it is minus 25, there is no change. Coming to the second one, lower bound is greater than global upper bound. So lower bound minus 25 greater than minus 25. That's also no problem. Okay, so we can expand this node. Coming to the second node, go with the second node. Okay, so you need to calculate the upper bound value and the lower bound value. So at node 2, so calculate the upper bound, calculate the lower bound. So this is the upper bound value, this is the lower bound value. So we should not consider the first element. Okay, for node 2, we should not consider the first element. So avoid the first element, inserting the second element. So with a profit of 15, and the knapsack still have 2 capacity, and the next one we can get it. So with a profit of minus 7 and 4, and there is still one remaining, but the third element is 5. So here we should not consider the fraction. That means we can't insert a part of element into this particular knapsack. So for example, if this element is having the 5 kgs, the weight is 5 kgs, we can't insert 1 kg among these 5 kgs to the knapsack. So that is a fraction. So that is not possible here. So we need to stop here, and the upper bound value will be minus 22. Minus 22. And that can be done in the lower bound. So lower bound also we are inserting the second element because we are not considering the first element. So 3 with a profit of 15 and 1 with a profit of minus 7 and then 5. So inserting 5. 5 means, see, how much capacity is still there? 1, right? So 1 by 5 into minus 8. Okay, 1 by 5 into minus 8. So which gives it as a 1.6. 1.6. So minus 1.6. Lower bound will be minus 22 minus 1.6, which will be minus 23.6. 23.6. So update the same thing here. Upper bound value minus 22, lower bound value minus 23.6. So check the two positions, two conditions. New upper bound minus 22 less than global upper bound. Global upper bound is minus 25. So minus 22 less than minus 25. So this is false. Okay, because it is a negative value, minus 22 is greater than minus 25. And similarly, lower bound greater than global upper bound. Lower bound is minus 23.6 greater than minus 25. So this is true because this lower bound value is greater than the global upper bound. What we have to do? We have to kill. So that means node 2 should not be expanded. Node 2 should not be expanded, right? So that means we have killed that particular node. Only node 1 should be expanded. Now coming to the node 1, expand this one with the second element. So 3 and 4. So here x2 is equal to 1 and x2 is equal to 0. That means considering the second element, not considering the second element. So let us calculate for this one. Node 3, upper bound, lower bound. Okay, this is upper bound, lower bound. So upper bound without fractions, lower bound with fractions. So what we have to do? So we have to consider the first element in both the cases. So I am considering the first element. So insertion of 2 with a profit of minus 10 with a profit of minus 10. What about the second node? Second element. So we are considering third branch. That means node 3 comes with the considering the second element. So second element, if you consider second element, then it will be 3 with a profit of minus 15, and here also 3 with a profit of minus 15. Now you can observe the weight of knapsack becomes 5 with a maximum capacity. So we can't insert the third element. So upper bound will become minus 25 and lower bound will also become minus 25. So update it here. Upper bound is equal to minus 25 and lower bound is equal to minus 25. So check out the condition. New upper bound less than global upper bound. New upper bound is minus 25, global upper bound is minus 25. So that's a false. Next, lower bound is greater than global upper bound. Lower bound value is minus 25, global is minus 25. Minus 25 greater than minus 25. Again, it's false. So nothing happens here. Coming to the node 4. Node 4. So in this node 4, what we have to do? So here we need to consider, yes, see, coming to the node 4, we have considered x1, right? So that means we have inserted the second element with a profit of minus 10 in both the cases, and the second one we should not consider. So we have to consider only 1. So the third one, right? So third one means 1 with a capacity, with a profit of minus 7, and here also with a capacity with a profit of minus 7. So what is the capacity of knapsack here? 3. Okay, only 2 is the remaining, but fourth element is 5. Here we should not consider the fractions. So here the total weight is minus 17. Okay, the profit total upper bound value will be minus 17. But here we can consider the fractions. So among these 5, we can go with the 2 by 5 third of value, right? So what we have to do, 2 by 5 into minus 8. 2 by 5 into minus 8. Okay, so this gives minus 3.2. Okay, minus 3.2. So the lower bound value will becomes minus 17 minus 3.2, which is minus 20.2. So update here, the upper bound value will be minus 17, lower bound value will be minus 20.2. Check out the condition. New upper bound value minus 17 is less than global value. So minus 17 is less than minus 25. So false, because minus 17 is a greater than. And coming to the lower bound should be greater than global. So minus 20.2 is greater than minus 25. So this is true. Minus 20 value is greater than the global upper bound. What we have to do then, kill that particular node. So we have to kill the fourth node. That means the fourth node cannot be expanded. So we are not supposed to expand the fourth node. We are killing that particular node. So only node 3 will be expanded right now. So expand node 3. So here the first come first serve means first we have to calculate for 3, then only we need to go with 4, and then only we need to go with the next one. So here we are killing, so we are expanding here again. So it will be 5 and it will be 6, and the third element x3 is equal to 1, and here x3 is equal to 0. And what we have to do, so first we have to calculate with the 5 and then we have to calculate with the 6, first in first out. So node 5, right? So in this node 5 we are considering x1 is equal to 1, x2 is equal to 1, x3 is equal to 1. Okay, node 5. So this is the upper bound value and this is the lower bound value. So this is the upper bound, this is the lower bound. So we are considering the 3 elements. Here we are considering the 3 elements. So considering the first element, what is the first element? 2 with a profit of minus 10, and then considering 3 with a profit of minus 15, and we can't insert the third element. So in this node 5, we have to consider the third element, but here if you consider the third element, the knapsack weight will be 6, which is beyond the maximum capacity. So this is infeasible solution. Infeasible, that means there is no proper path will be done. So this node cannot be expanded. So coming to the node 6, we have to calculate for the node 6, and in this node 6 we have to avoid this x3. That means we should not consider the third element. So we need to consider the node 6. So for getting the node 6 we should not consider the third element. So it will, upper bound will be minus 25, and coming to the lower bound also we have to consider 1 and 2. So 2 with a profit of minus 10 and 3 with a profit of minus 15, and the knapsack becomes total weight is 5. So lower bound value will also be minus 25. So update this one, upper bound is minus 25 and lower bound will be also minus 25, right? Now check the conditions. Upper bound, the new upper bound is less than a global upper bound. So minus 25 is less than minus 25, false. So nothing should be updated. A lower bound should be greater than global upper bound, then we have to kill. Lower bound is minus 25 and the global upper bound is minus 25. So minus 25 greater than minus 25 is also false. So we can expand the node 6. Okay, the node 6 can be expanded. If the value is greater than global upper bound, then this 6 should be killed. But here it is not the same, right? So we have to expand with the node 6. Okay, and here we need to consider the fourth element, and here we need to consider we should not consider the fourth element. Now coming to the calculation of upper bound and lower bound values for node 7. Okay, node 7. So here you can see x1 is equal to 1. In order to get it, x2 is equal to 1, x3 is equal to 0, and x4 is equal to 1. So we should consider 1, 2 and 4th elements. So consider the upper bound values and lower bound. We have to calculate the upper bound and lower bound. So consider the x1, 2 with a profit of minus 10 and 3 with a profit of minus 15. So there is no possibility to insert 4th element. If you insert 4, okay, if you insert the 4th element, so 5 will be inserted, which becomes the total knapsack as a 10. So which is beyond the capacity. Actually the knapsack capacity is only 5. So we can't insert this 5. That means 4th element. So obviously we can say it as a infeasible solution. Infeasible solution. So it can't be done, right? So we have to calculate the upper bound and lower bound for this node 8. So node 8, and here also the fourth one should not be considered. Should not be considered, right? So this is the upper bound and lower bound. Upper bound and lower bound. You can see we need to consider x1 and x2. So 2 will be inserted with a profit of -10. 3 will be inserted with a profit of -15, and the total capacity of knapsack becomes total 5. And we should not consider x3 and x4. So we should not consider the two weights 1 and 5. So upper bound value will be -25. And here also lower bound also we have to insert the first element with a profit of 10 and insert the second element with a profit of 15. So here also we'll get the lower bound value with a -25 because the total knapsack becomes 5, which is a maximum capacity. So here upper bound value will be -25 and lower bound value will be -25. So again check the condition. Upper bound less than the upper bound false, lower bound greater than the global upper bound false. So this is the solution. And because we have considered up to the 4 elements, x1, x2, x3, x4. So 4 levels we have calculated. So if there are 5 elements, then again this 8 will be expanded. Okay, and again we have to calculate the upper bound and lower bound, and we have to check the condition. And this is a FIFO branch and bound for solving the 0-1 knapsack problem. And here the solution is considering, here the solution for this problem is considering x1 as a 1. So see, this is a solution. So this is a x1, x2, x3, x4. So considering 1, 1, 0, 0. So that's what we have said this about 0, 1. 0 is not considering, 1 means considering. So in this is a solution, that means we are considering only x1 and x2, which gives the maximum profit. So what is the profit here? So the profit by inserting the 2 elements is -25. So which is the maximum profit. So here we should ignore the sign so that will be the maximum profit. So we are converting the maximization problem to minimization problem and finding the solution. So by giving some negations to each and every profit, and finally we are just discarding the negative value so that we'll get the maximum profit here. So by inserting the first 2 elements, we are getting the maximum profit. So this is the optimal solution. This is the optimal solution. So you can see x1 is equal to 1, x2 is equal to 1, x3 is equal to 0, and x4 is equal to 0. So this is the path where we can find the solution. And here we got the 2 infeasible solutions where we can't process further. And these 2 are the killed nodes. Node 2 and node 4 are killed nodes, dead nodes which are not being expanded. Right? So these 2 statements or these 2 conditions are most important, where for every node, after calculating the upper bound and lower bound, we have to check with the these 2 cases so that the complete state space tree cannot be calculated. So some sort of nodes will be discarded here. So reducing the state space tree will be done. Point sets. Disjoint sets. So we know that a set is a collection of elements, right? So a set is a collection of elements. Collection of elements. So then what we call it as a disjoint sets. So if you consider any two sets, right? Let it be S1 and S2. So these 2 sets are having a different elements like 1, 2, 3, and here it is 4, 5 and 6. And when we say that S1 and S2 are a disjoint sets, so when the S1 intersection S2, that means the common element, right? So is equal to 5. That means there is no common element in both the sets, right? There is no common element. Then we can say these 2 sets are disjoint sets. That means no common element. So we usually, the intersection means we need to get the common element in both the sets, right? So there is no common element in S1 and S2. Then S1 and S2 called as disjoint sets. Disjoint sets. So there should not be any common element in both the sets. Right? Now, what are the operations that can be done on these disjoint sets? So the operations that can be performed is the first one, simple union, simple find. That means we know that union means combining both the sets. So we will combine both the sets and we'll get a new set with all the elements of both the sets, S1 and S2. So that is the union, simple union. That is a simple union. So there is no constraint, right? And next is simple find. So we need to find the parent of that particular element. So why we are calling it as a parent means any set can be represented in terms of a tree data structure. Okay, a set is represented as a tree data structure. So as we are calling it as tree, definitely there will be a root node. Okay, and usually we can call this as a parent node. Root node or a parent node. For example, let us take 1, 2 and 3. We can say 1 is a root node or 1 will be the parent of 2 and 3. Okay, so that's why we can call it as a parent node or a root node. So simple find means we need to find whether the element is available in the set or not, and if yes, we will return the parent node, the parent of that particular element. And the next one, weighted union. Weighted union. So there will be some sort of weightages, and based upon that weights we have to perform the union operation. And the fourth one, collapsing find. Collapsing find, which is a slight different from a simple find, which is a slight difference from the simple find. And in this session, we will focus on simple union and simple find. So how can we perform this simple union between the two different sets, and how can we perform the simple find operation? So one thing, we are working on the disjoint sets. Disjoint sets means we need to take a more than one set, and there should not be any common element in both the sets. For example, S1 and S2. So let us consider S1 is having some A, B, C, and S2 is having some E, F, G. So these two are called as a disjoint set because there is no common element. For example, if this is having one more element like 3, 4, 5, 6, we can't say S1 and S2 are the disjoint because here S1 intersection S2 is having one element called 3. So if there is any common element, we can't say those sets as a disjoint set. If the intersection is 5, that means no element, then only we can say these two are the disjoint sets. Now it will be the disjoint sets. So 1, 2, 3 in one set, 4, 5, 6 in another set. Right? So hope you understood this one. Now we will see the simple union and simple find. First, simple union. Let us consider the simple union. So simple union means we are supposed to apply the union operation between the elements. So simple union. So first what we have to do, we have to consider all the elements as a individual elements, right? So consider all elements as individual. So usually we will represent this one with a tree data structure. So tree data structure, right? So obviously there will be a root node or parent, right? So consider P of I is the parent of node I. So usually the P of I is represented as a parent of node I. Okay, if you consider any node, P of I will be represented as a parent. And see, initialize P of I is equal to -1 for root nodes. If the node is a root node, the parent will be -1. Okay, if it is a root node. So obviously, if it is a root node, there will be no parent, right? So that will be the first node, right? So we have to initialize to -1 for such root nodes. And fourth, so we have to collaborate, or we have to perform the union operation with one by one. Okay, perform simple union for every element. And finally, update the parent after union operation. Right? So these are the steps we need to follow, right? The first one, consider all the elements as a single elements, individual elements. Next, let us represent the P of I is the parent of node I, and then initialize the parent -1 for the as a parent. I mean -1 for the parent nodes. That means a root node, and then perform the simple union for every element one by one. Okay. Then update the PI after union operation. See, for example, if you apply the union operation, so the -1 should be only for the root node. So only one node should have the -1, right? So remember all these points. Now we'll move on with the example so that you can understand that one. Simple union. See, let us take the elements. The elements as 1, 2, 3, 4, 5 and 6. These are all the different elements. So now what we have to do? So we have to consider the tree structure. 1, 2, 3, 4, 5, 6. So this is a tree. Now we have to find out the table of all the parents. So I'll write here. I'll write here. So 1, 2, 3, 4, 5, 6. This is a I value. This is a parent of I value. So this is the parent of I value. What happened? Now, what we have to do? Initialize -1 to the parent. So here, all these are the individual elements. So these are all the roots. Okay. So this is one tree with only one element. So what is the value of parent of this one? It will be -1 because it is a root. Parent of 2, again it's -1 because it's a single element. And it is also -1, -1, -1 and -1. Okay, initially this is a -1. What happens? Now perform the union operation between 1 and 2, union operation between 3 and 4, union operation between 5 and 6. Okay, now you can take 1 as a root and 2 as a child, 3 as a root, 4 as a child, 5 as a root, 6 as a child. So that means we are joining, we are performing the union operations in between 1 and 2, 3 and 4, 5 and 6. We are combining the elements, right? Now update the value, update the parent of nodes. So what is the parent of 1? Here 1 is a root node. So parent of 1 is -1 only. What is the parent of 2? Parent of 2 is 1. Parent of 2 is 1. So it will be -1, it will be 1. And parent of 3, -1. Parent of 4, it's a 3. Parent of 5, it's a -1 because this is a root. 6, it's 5. See, after combining these one, we got the values in this manner. Okay. So after completion of the union operation between 1, 2, 3, 4, 5, 6. Now what we have to do? You have to perform the union between these two things. So union of, okay, 1, 3. So what happens here? So 1 with a 2 and take one more child which is 3, which is having 4. So this is a union of 1, 3. Here 1 is a root node, 3 is a root node. 1 is a root node, 3 is a root node. So we are combining these two things. Okay. So now what happens? 1 becomes the root node. 1 becomes the root node. So update the parents. So the parent of 1 is a -1 because it's a root. Parent of 2 is a 1. Parent of 3, again it's 1. Parent of 4, it's a 3. Okay. And similarly, this is a -1 and 5. -1 and 5. You can observe again, we are having two -1s. But if you perform the union operation, what we have done, so only one root should be there. So again we have to combine union 1 and 5 and 6. See, union of 1 and 5. So 1 is this one. So 1 which gives with a 2, another child with a 3, which is having a child 4. And now 5 and 6. One more child you can give, it's a 5, and it can give it as a 6 as a child. Now what happens? Again update the parent table, which is root of 1, it is a -1. Root of parent of 2, it is 1. Parent of 3, it is 1. Parent of 4, it is 3. Parent of 5, it is 1. Parent of 6, it is 5. Right? Now you can observe there is only one -1 here. That means only one root. So this is a root. So after joining all these things, after performing the union operation of all these elements, we got this particular tree, which is having only one root followed by different children. So for this, the algorithm will be simple, which is a union of I, j, which gives the parent of j is equal to I. That's it. So this is a simple algorithm to perform the union. So one by one, we have to join the elements. We have to combine the elements. That's called as a union. And the resultant after every joining, after every union operation, we have to update the parent table. Right? So this is how we can perform this simple union. So initially all these are the individual elements, so individual trees, only one root node is there. So gradually we are combining one node with another node, one set with another set. Okay, and we are updating the parent table. For every node we are giving the parent. So P of I represents the parent. So this is a simple algorithm for simple union. Now what we have to do? We have to perform the simple find. We have to find the element. So our next operation is simple find. So I'll erase all these things. I will erase all these things. See the final one is this one. 1, 2, 3, 5, 4, and 6. So the same thing here. Okay, the same thing here. I am erasing this one also. So what we have to do? We have to find the element from this particular table, right? So see, the algorithm for this one is find of I. We need to find I, and we have to repeat the steps while the parent of I is greater than 0. Simply what we have to do? So we have to initialize this parent of I to I and close, and finally you can return the I value. So this is a simple algorithm for find. See, you can check. First, if you want to find a 4, okay, so what is the parent of 4? What is the parent of 4? The parent of 4 is 3. 3, okay, which is not a -1. We know that the parent of root node is -1. We know that the parent of root node is -1. So we need to repeat this process. We need to find every element parent until it reaches to -1. So that's why we have written this one. So we have to repeat the process until the parent node is greater than 0. So if the parent is greater than 0, that implies there is another level of parent, right? See, for example, if you want to find the 4, the parent of 4 is equal to 3, which is greater than 0. What we have to do? So I is equal to parent of 4. So that is equal to 3. Now I is equal to 3. I is equal to 3. Now perform the same operation here. I is equal to 3. So parent of 3 is equal to, what is the parent of 3? It is 1. So parent of 3, you can see here. Parent of 3 is 1. 1, which is also greater than 0. So simply initialize the parent of 3 to I, which is equal to 1. Now I becomes 1, and see P of 1 is equal to, what's the parent of 1? What's the parent of 1? It's a -1 because it's a root node, right? So it is a -1. So which is less than 0. Which is less than 0. So simply what we have to do? So you have to return I. Return I means it's a 1. So 1 is a root node. 1 is a root node. So if you got that root node, that implies the value is available in our union. Okay, in our set of elements. So this particular find will return a root element. It will return the root element. So this is a simple logic for applying the find operation. So we need to keep on moving until the P of I, the parent of I, is less than 0. If it is greater than 0, simply we have to repeat this process. Okay, so whenever it becomes less than 0, immediately we can say that the root is I. The root is I. So this is a simple find operation. So simple union and simple find. Okay, so hope you understood this. These two operations are in disjoint sets. So once again, the disjoint sets, when we call it as a disjoint sets, means if the intersection of both the sets are 0, that means there is no common element between two different sets, we call it as a disjoint sets, and we can perform a few operations on the disjoint sets, that is a simple find, simple union, and weighted union, and collapsing find. So in this session we have seen the simple union and simple find algorithms, and how we can find out the root of the element and how we can perform the union of all the elements. So one thing we have to remember, we have to represent any node in this disjoint sets as a roots, as a tree structure. So we are using the tree data structure to represent the set. So in our previous session, we are discussing about the disjoint sets. What is the disjoint set? So if you consider two sets, if there is no common element between these two sets, then we can say that set as a disjoint set. And there are different operations that can be performed on disjoint sets. So that is a simple union, simple find, and weighted union and collapsing find. So in our previous session, we have discussed about the simple union and simple find. So union means combining the elements from both the sets, two different sets. Okay, and find means it will find the index, that root element of that particular set. Okay, we can call it as a set representative. So whatever the root element in that particular set, so that will be returned in the find operation. So that we have seen in our previous session. Now we will see the third operation, that is weighted union. Weighted union. So there is a slight difference between the simple union and the weighted union. So in the simple union, what we have done, so just we are merging two different sets and forming a single union. Okay, so we are merging one set with another set. So merging means here union, right? So, and we said that the root element, the parent node of root element will be -1 there. But here in the weighted union, the name itself indicates the parent of root element will be the number of nodes of that particular element or that particular set. Okay, for example, consider S1 is equal to 1, 2, 3, 4, and S2 is equal to some 5, 6 and 7. So we know that there are no common elements in between these two sets, no common elements. So that means S1 intersection S2 is equal to 5. 5 means an empty set. Okay, so we can say S1 and S2 are the disjoint sets. So these two comes under disjoint sets. Disjoint sets. Now, if you want to give a union S2, S1 union S2, that means combining both the elements. So which should be given as a child to which set? So which will be the parent and which will be the child? So simply, if you perform this one in weighted union, so if number of elements in S1 is greater than number of elements in S2, that means S1 is having more number of elements than S2. So here S1 is having how many elements? 4 elements. And S2 is having how many elements? 3 elements. So here this example reaches, right? S1 is greater than S2, then S1 will be the parent and S2 will be the child. So we have to insert or merge the S2, the elements of S2 to S1. That means the number of elements, which set is having the more number of elements, that will become the parent. And the set which is having the less number of elements, that will become the child element. Right? For example, consider the same thing. Okay, so remember this one. If number of elements in S1 is greater than number of elements in S2, S1 will be the parent and S2 will be the child. Else means if number of elements in S1 is less than number of elements in S2. So now more number of elements are in S2. So S2 will be the parent and S1 will be the child. So I'll give you an example. Let us consider this one. So as we discussed in our previous session, the set is represented with a tree structure. Set is represented with a tree structure. For example, I is the root element and here 5 is the root element. So S1 can be denoted as 1, which is a parent of 2, which is a parent of 3, which is a parent of 4. and the next one 5, which is the root or parent of 6, and it's also parent of 7. Now the number of elements, this is the S1 and this is the S2. Now what happens? S1 union S2. So which will be the parent? S1 is having 4 elements, S2 is having 3 elements. So S1 is greater than S2. S1 is greater than S2. Right? Then S1 will be the parent, S2 will be the child. So what happens? 1 having a child 2, 3, 4, and 5 will be the another child. The 5 will be the another child, which will be having 2 more children, 6 and 7. So this is how we will perform the union operation. So only one thing. So that means based upon the number of nodes in that particular set, we will be deciding the parent set and the child set. Okay. Now what happens? What is the root? Okay. What is the parent of that particular root? See, I will erase and I will show you. For S1, the elements are I and P of I. Let us consider I as an element, P of I as a parent. So how many elements are there? 4 elements. 1, 2, 3 and 4. So total 4 elements are there. Similarly, S2 is having I and P of I. I is the number of elements and P of I is a parent of that element. So 5, 6 and 7. Now consider the parent. So parent of 1, here you can see 1 is the root node. 1 is the root node. Then in normal simple union we considered the parent of root node will be -1. But here the parent of root node will be the count of that particular set. So parent of I will be minus count of I. That means that particular set. Okay, that particular set. So how much it will be? -1. And how many nodes are there? 4 nodes. So it will be -4. So -4 is the parent of node 1. So in simple union we are giving -1 as a parent, right? But here we are giving the number of count. Okay. Then parent of 2, it is 1. Parent of 3, again it's 1. Parent of 4, again it's 1. Coming to here, the second set. Okay, the second set. So coming to the second set, parent of 5. 5 is a root node. So if it is a root node, what we have to do? We have to count the number of elements of that particular set. How many elements are there? 3 elements. 5, 6, 7. So the parent of 5 will be -3, as it is having some 3 elements. Parent of 6 is 5. Parent of 7 is again 5. Parent of 7 is 5. Now what happens? See, S1 union S2. So what are the elements? 1, 2, 3, 4, 5, 6 and 7. And similarly we need to write the parent. We need to write the parent of all these nodes. Alright. Now what happens? Parent of 1. Parent of 1 will be, so here we are performing the union operation. So these two becomes this one. Okay. Now parent of 1. How many nodes are there now? 1, 2, 3, 4, 5, 6 and 7. Total 7 nodes are there. So what happens here? -7. -7. Right? So that means what we have to do? If P of I is greater than P of J. Okay. If P of I is greater than P of J. So for example, here it is I and here it is j. Okay, I and j. So here you can check -4 greater than -3. True or false? False. That implies, so j is having less number of elements. J is having less number of elements. So what we have to do? We have to make the parent of j to I. Okay. So we have to make a parent of I to j. Right? See what happens? 1. It will be now total elements are. I'll go with this in the next one. Okay. Yeah. So what happens here? Total 7 elements. So it will be -7. And what about the parent of 2? It remains same. 1, 1, 1. And what about the parent of 5? Parent of 5. So parent of 5 becomes 1. Okay. Here you can observe. Parent of 5 becomes 1. And parent of 6 becomes 5. And 7 becomes 5 itself. So in this case, let us see. For example, ij. I value is -4. J value is -3. Okay. So let it be P of I is equal to count, and similarly P of j is equal to minus count of j. Okay, minus count of j. So you can observe this is minus count of I means total it will be -4 and it will be -3. So if you perform the union operation, what will be the total count value? So that will be, let us take temp is equal to P of I plus P of j, which will become -7. You can observe total 7 elements are there. And this -7 will be the parent of the root. Now we have to decide what is the root, either S1 or S2. So for that decision, what we are doing, simply you can check if P of I, in this example, we'll check in this example, is less than P of j. P of I less than P of j. P of I is -4. Okay, so here it is -4 less than -3. What happens? True. That means you can see I is having more number of elements. So here don't confuse about the less than and greater than symbol, because here we are saying P of I is less than P of j. That implies this is the negative values. -4 less than -3 is obviously true. So 4 elements are having in first set, 3 elements we are having in second set. So what we have to do, what we have to change? We have to change the parent. Okay. Parent of j is equal to I. So parent of j will be I. So what is the parent of j? Parent of, what is the j here? 5. Parent of 5 will be I. I means 1. Okay, parent of 5 will be 1. You can observe now. And similarly, what about the parent of I now? Parent of I will be 10. After completion of union, it will be -7. Okay, hope you understood. Check this condition. P of I less than P of j. That means -4 less than -3. That implies, so this implies set 2. Set 2 is having a less number of elements, and I set is having more number of elements. Then simply what we have to do, we have to initialize I to as a parent of j. So what we have done here like this, right? J is 5. Parent of 5 will be 1. Parent of 5 will be 1. 1 is nothing but I. And parent of I will be temp. Temp is nothing but total number of elements, -7. So here we got it. Else. That means if P of I is greater than P of j, that means here we are having 3 elements, here we are having 4 elements. What it becomes? S2 becomes the parent, S1 becomes the child. So what happens here? P of I is equal to J. We have to initialize J as a parent of I. So we are merging S1 to S2. We are merging S1 to S2. And then P of J, this is the root node which is nothing but a temp. So these are the two conditions we need to take care while implementing the weighted union. So only one thing we have to remember, so S1, if you want to combine or if you want to perform the union operation between S1 and S2, first we have to count the number of elements in S1 and S2, and which set is having the highest number of elements, that becomes the root or that becomes the parent, and the less number of elements set will becomes the child. So that we have to update the values, the parent nodes, right? And as the name itself indicates, a weighted union, the root node, the parent of root node will be the number of elements in that particular set. Now I'll write the algorithm here so that you can understand. So I'll erase this one. I'll write here algorithm weighted union, which takes the values I and j set. So initially P of I is equal to minus count of I. Similarly P of j is equal to minus count of j. So here we are taking the number of elements. Now what we are doing, we are just combining these two things, P of I plus P of j. So after performing the union operations, we will be getting the total value. Now what we have to do? So we have to check the condition if P of I is less than P of j. That means P of I is having a more number of elements than P of j. Then what happens? We have to initialize this one. P of j is equal to I. That means we are assigning I value as a parent of Pj. That means we are appending the second set to the first set. And what will be the I value? P of I is equal to 10. P of I is equal to 10. So I'll erase this one also. And what about the second? That means else. Else. So this means S1 is greater than S2. Okay. Let it be I belongs to S1 and J belongs to S2. So then it becomes P of I is equal to J. Okay, that means, so this part S1 is less than S2. That means number of elements of S1 is less than number of elements of S2. Now S2 becomes the parent, S1 becomes the child. So S1 should be union, that means merged to S2. So that's why J value will be the parent of P of I. And similarly P of j is equal to 10, which is the parent of root becomes the total value. So this is a simple algorithm for weighted union. The only difference between weighted union and the normal union means, so here based upon the number of elements of a set, we are deciding which set should be merged to which set. So larger elements set will be the parent, lower elements set will be the child. So similarly we have to change the parent of each and everything, and root, the parent of root will be the number of elements of that particular set. So we have to remember these points, and this is a simple algorithm to implement the weighted union in disjoint sets. Hello friends, welcome back to our channel. So today we will see one more operation on disjoint sets, that is a collapsing find. Collapsing find. So in our previous session we have seen what is a disjoint set and what are the operations that can be performed on the disjoint sets. So in that we have seen the three operations, that is a simple union, simple find and a weighted union. And the fourth operation is the collapsing find. So before going to the collapsing find, let us know about the simple find. So if the disjoint set in this format, So if our tree structure is in this format, right? And if you want to find 70, so we know that in disjoint set, if you are performing the find operation of any particular element, if it is available in the set, it will return the set representative, which we call it as a root node. So the find of 70 will be the root node of this set 10. Similarly, if you apply the find of 40, then also it will return 10. And if you apply find of 50, then also it will return 10. That means the find operation will return the set representative, which is a root node. Now, what we have done in the simple find, so simple find of I, what we have done, so we are checking the parent node is greater than 0 or not. So we are checking the parent node, the parent of I is greater than 0. If yes, it is greater than 0, that implies I is equal to parent of I. Because in the disjoint set, so the parent node of a root, okay, the parent node of a root will always be a negative value. Either it can be -1 if it is a simple union operation, and it will be the total number of elements of a set if it is a weighted union. But it is a negative value. So that means we are always checking that the parent of I is greater than 0. If it is greater than 0, that implies that is an intermediate node, that is not a root node. So we are just iterating everything until the condition becomes false. That means until the P of I greater than 0 is false, it becomes negative. Then we can say that the root node, it reaches to the root node. For example, find this one for this simple find. So find of 70. So what we have to do? So P of 70 greater than 0. That implies what is the parent of 70? So I'll write here the values. So 10, 20, 30, 40, 50, 60 and 70. So these are the values, and these are the I, and this is the parent of I. So what's the parent of 10, which is a root node, so which will be -1. Parent of 20, it is 10. Parent of 30, it is again 10. Parent of 40, it is 30. Parent of 50, it is 10. Parent of 60, it is 50. Parent of 70, it is 60. So this is the table of the complete elements and corresponding parents. Right? Now parent of 70 is 60. So 60 greater than 0. 60 greater than 0. It is true. Then I becomes parent of 70, which is 60. Again, now find of 60. So parent of 60 greater than 0. What is the parent of 60? It is 50. So 50 greater than 0. True. Then I becomes a parent of 60. So which is 50. Now becomes 50. I becomes 50. Now again find of 50. So parent of 50 greater than 0. What is the parent of 50? It's a 10. So 10 greater than 0. It's 2. Now I becomes 10. Now parent of 10 greater than 0. So what is the parent of 10? Which is a -1 or -7. So it will be -1 greater than 0, which is a false. So then I is a root node. It will return the I. So that we have done in the simple find algorithm. So here, how many comparisons we are doing? There are 3 comparisons we are doing. So in order to find 70, we are finding 60, we are finding 50, and then we are finding 10. So 3 comparisons are being done. Okay. So for find of 70, if it is a simple find, it requires 3 comparisons. For example, in our logic, if it requires to apply 4 times, okay, if it requires some 4 times to apply the find operation, how many comparisons? 4 into 3, which gives a 12 comparisons. 12 comparisons, right? So what is the result? Obviously, find of 70 will be 10, find of 60 will be 10, find of 50 will be 10. So why not we change this tree so that 70 can be directly given as a child to 10. Similarly, whatever the intermediate nodes in this particular path, for example, this path we are having 50 and 60. So all those nodes can be associated as a children for that particular parent, so that the number of comparisons will be reduced. So for the first find it requires the 3 comparisons, and from the next find onwards it will require only 1 comparison, because we are just collapsing this tree structure and we are giving 70 as a child to the parent 10. So directly from the next find onwards we will be having only 1 comparison. So for doing such type of things, we need to change the algorithm. That means by using this collapsing find, the name itself indicates we are collapsing the tree structure. So what we are collapsing all the intermediate nodes of that particular path, and we are associating each and every node as a children to that particular root node, because always whatever the element we are finding, the result will be the set representative. That means only the root node. So if you find 70, it will be root node 10. If you find 60, it will be root node 10. If you find 50, then also the result will be 10. So that's why we are just collapsing the tree, all the intermediate nodes, and we are associating them to the root node. So for that purpose, we are just changing a small algorithm. We are changing a few things in the algorithm. See, let us write the collapsive find. Collapse find. So first, let us take some root is equal to some I, and find out the root element. What is the root element? Because we have to assign the root as a parent of 70, right? So while P of root is greater than 0, simply we can say root is equal to P of root. So this is a simple find operation. This is a simple find operation. And after that, simply check while root not equal to I. Root not equal to I. Then assign take some temporary variable, right? Some S is equal to P of I. The parent of node I will be assigned to S, and then the root will be assigned to the parent of I. The root will be directly assigned to the root of parent of I, and then I is equal to S. So I assign S to I now. Okay, recursive call. And simply after completion of this, that means whenever the root becomes I, simply return the root element. That will be the result, right? So this is the collapsive find. What we are doing? So some operations we are doing, and again some operations we are doing, so that we are collapsing all the elements in the intermediate elements of that particular path, and we are assigning that to the parent. Now we will check with this one how the tree will be collapsed, how the elements will be collapsed by using this one, right? So let us check with this one. C find of 70. We know the result will be 10 because 10 is the root element. So what happens here? So I is 70 and root is equal to I, which is 70, right? So initially I is equal to 70, root becomes also 70, right? Now P of 70 greater than 0, parent of 70, which is 60, 60 greater than 0, true. What happens? Root is equal to P of root. Root is equal to P of 70. Okay, so P of 70 is 60. Now again find operation. So again go with this one. Parent of root. Parent of root is 60 now. Parent of root is 60. So now 70 becomes 60 here. So P of root 60 greater than 0. Parent of 60 is 50. So 50 greater than 0. True. Then what happens? Root is equal to parent of root. Root is equal to parent of root. Parent of 60. That's the parent of 60, 50. Now root becomes 50. Root becomes 50. Now parent parent of 50 greater than 0. So which is parent of 50? It is 10. 10 greater than 0. True. That implies root is equal to parent of root. Okay, what's the parent of root? 10. Parent of 50 is 10. So root becomes 10 now. So now it becomes 10. Now parent of 10 greater than 0. So we know that the parent of root, here 10 is a root. So in this disjoint sets, the parent of root will be negative value. Negative value. Parent of root will be negative value. So that will be either -1 or the total number of elements in the set. So if you are applying the simple union, it will be -1, and if you are using the weighted union, it will be the count of elements, minus of count of I. So it will be negative value. So let it be -1 greater than 0, it is a false. So now the root value becomes 10. So I am erasing all these things. Now the root becomes 10 after executing this step. After this executing that particular while loop, right? Now what we have to do, we find that root element is 10. Root element is 10. So we are not returning the root because we are collapsing the intermediate elements. Okay. So now while root not equal to 0, root not equal to I, root is here 10. 10 not equal to, what is the I value? 70. True. So what we have to do, you have to go with this one. S is equal to P of I. So P of I means parent of 70. Parent of 70 is 60. So S becomes 60 and P of 70 becomes root. What is the root value? 10. Parent of 70 becomes 10. So here I am updating here. Parent of 70 becomes 10. Right? And then I becomes S. What is the S value? 60. Now I becomes 60. Now what happens? Here this tree has been collapsed and parent of 10, it becomes 70. Okay, we are not stopping here. So again we are collapsing the intermediate nodes of this particular path. Now I becomes 60. Now I becomes 60. So what we have to do? So again check root not equal to I. So that implies root is 10 not equal to I means 60. True. So we have to enter into the loop. So S is equal to P of I. What is the I value here? I value is 60. So here 70 becomes 60 now. Okay. Now P of 60. So which is parent of 60 is 50. S is 50. Now P of I. P of I means here 60. Parent of 60 becomes root. What is the root? 10. Root 10. Parent of 60 also becomes 10. Right? Now the tree structure has been collapsed and 10 will be the another child of 10. Sorry, 60 will be another child of 10. And what happens here? I is equal to S. So I is equal to S means here S is 50. Now I becomes 50. Now I becomes 50. Okay. Now again root not equal to I, which is nothing but root is nothing but 10 not equal to 50. True. Again it will enter into the loop. S is equal to P of I. I means 50. What is the parent of 50? It is 10. And then parent of I. I means 50. Parent of 50 will be root. So root means again it will be 10. So already 50 parent of 50 is 10. Right. Now what happens? The next one I is equal to S. That means S is here 10. So I becomes 10 here. So I becomes 10 here. Right. So now you can observe again root not equal to I. That means root is 10 not equal to 10. False. Then it will be stopped and it will come here. So return root which is equal to 10. See, which is 10. Now what happens? If you apply the same operation multiple times, that means the find operation multiple times. For example, 70 and again find of 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 70. Right? Now what happens? If it is simple find, it requires the 3 comparisons. it requires the 3 comparisons, it requires the 3 comparisons, it requires the 3 comparisons, and it requires 3 comparisons. So total it requires 15 comparisons. 15 comparisons for simple find. Simple find. Now, if it is a collapse find, see, for first find operation, it requires total 3 plus 3, 6 comparisons. Okay, this is a 3 times and this is also 3 times because three nodes are there. So 6 comparisons will be done, and here for the next time it will be 1 comparison, it will be 1 comparison, it will be 1 comparison, and it will be 1 comparison. So total 10 comparisons will be there. Total 10 comparisons will be there. Hope you understood. If it is a simple find, so we are only finding this one, right? That means so total 3 comparisons to find the root. So how many finds we are using? 1, 2, 3, 4, 5. So total 5 times it will go with the 3 comparisons. 5 3 is 15 comparisons. It requires around 15 comparisons. For example, if you implement the same thing using a collapsing find, so for the first iteration, for the first find 70, it requires 6 comparisons because this is 3 and this is also 3. Total 6 comparisons will be taken. But from the next find onwards, it requires only 1 comparison because directly 10 is the parent of 70. Okay, 10 is the parent of 70. So for the next find, it will be only 1 comparison. Second find, it will be only 1 comparison. Next find, it will be 1 comparison, and next find, it will be only 1 comparison. So total 10 comparisons will be there. So automatically the complexity has been reduced. Okay, the complexity of our algorithm has been reduced. So we are also reducing, that means collapsing the tree structure, and we are giving all the intermediate elements as a child to the root node. Okay, so this is how we are using this collapsing find. If it is only one time we are using the find operation, then you can simply use this simple find operation. If it is more than 2 or 3 times, if your logic requires to implement the find operation 2 or 3 times more, then simply we can go with this collapsing find operation. Right? So hope you understood. So these are all the different operations done on disjoint sets. So simple find, simple union, weighted union, and collapsing find operations. Right? So let's stop here. And if you are having any queries regarding this procedure, feel free to post your doubts in the comment section. Definitely I'll try to clarify all your doubts. And if you really enjoy my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.